Morning, Professor Suchandan Pal.
Good morning, Rajendra Singh ji.
Yeah, how are you?
Fine.
Okay, nice to see you. So, how we will go about it is something like this. So, you see, if there are three invited talks and one oral presentation because one oral presentation is dropped. He has dropped out. So, first two invited talks, first one is the video recording only. I have to just display it. Okay. And then the second one, I will do the session chair, and then the third invited talk and one oral presentation, you will chair. So for the third one, Professor Anant Agrawal, I think you have got the CV. So you can
No, not
you
yet.
have got the
I have
CV?
not. No.
Okay. So I will ask Hardyan. Hardyan, have you sent this CV of Professor? Hello, Hardyan.
Hello, sir. I will send, sir, now. You know email ID.
Just you have the email ID, na?
Yes, I request to Manikant Babu, please send.
I'll send it.
You send. Manikanta, you send this CV of Professor Anant Agrawal. So in the meantime, you can go through Professor Paul. You can go through his CV and you can maybe during that time it's a quite extended CV as such. So you can read out the salient points. Okay, not the complete CV.
Okay.
Yeah.
Okay, sure.
Okay. Yeah. So I think within 2-3, we will wait for. I think there is a lecture going on. Manikanta. Manikant. So there is this morning lecture, this going on, the plenary lecture.
No, it's not. I have not seen anything. Maybe.
But there was no lecture in the morning today.
No, morning is that 9:30 to 10:30.
Oh, okay. So that's over.
So yeah, that's already over. So 11 o'clock we can start our session. It seems.
Okay. So now then we can start.
Yeah, 3 minutes.
But we have some participants in because I can see you can see some more participants or.
They may join little later maybe because people are joining after 11.
People are joining after 11. Okay. What we can do is, because you see, we don't need to hurry for this session because Biraram has already dropped out. So we have a good time. And Dr. Shravanti Chaudhary, her talk I have listened, it's exactly half an hour. And since we don't have any question hour session, so we can give good amount of time also, like another few minutes also for these two talks, invited talks and question. Okay, so that we have up till 1 o'clock. So we can start maybe after 5. Yeah, 11:05 or something we can start.
Fine.
Okay. Yeah. Because let other
7
people
minutes
also
more
join.
to start our session.
Yeah. So we can let other people also to join, and you can maybe, if you have link to some participants or somehow you can connect to some people, you can ask them to join. Okay.
Yes.
So I think Hardyan is also listening to it.
Jan is arranging the talk. I think.
Okay. Anyhow, with that, just he has to.
Okay, sir. I can play from my side.
Yeah. So we wait for some time. So first, let a few more people come into this hall, and maybe another 3-4 minutes we will start. Okay, by 11:05.
Okay, sir.
Okay. So where are the students from our group? I don't see them here, or they are logging in through delegate account. Hello, Hardyan?
I think they will log in.
Okay.
Hello, sir.
Yes.
Okay, sir. I am sending again. They have already a WebEx link for all one.
No. Is it like we can see I think all the participants we cannot see here.
Please click participants. Just.
No, I can see only 12 are there. It's more.
Yes,
More are
only
expected.
12 are there.
And even there are 12 students from our group only. Okay, so just 3-4 minutes more. Okay, Let
Okay,
the
sir.
people join. I think people are joining now. A few more people. Okay.
Yes, sir. Yes.
So, hello, good morning, Dr. Harshad Mehta. How are you?
How are you? How are you?
I think you are muted. I cannot hear you.
I'm not muted. It's
Yeah. Hello.
Can you hear me now?
Yes. I can hear you.
Okay, very good. Thank you.
How are you?
All right. How are you doing?
Yeah. So it's quite late in the night.
Yeah, that's okay.
Yeah.
It's
So,
almost, yeah, we are now, yeah. Fortunately, I'm on West Coast, so it's only 13 and a half hours behind. Not, not 10 and a half.
okay.
Yeah.
So still better.
Yeah.
What's the local time there right now?
Right now it's 9:30 p.m.
Oh, 9:30 p.m. Okay, anyhow, I think after Shravanti's talk, then your talk is there.
Yeah,
So
right.
within 1 hour, I think it will be over. So then maybe
Yeah.
you
No
had
problem.
okay.
Yeah.
So in another 1 or 2 minutes, we are going to start.
Sure, no problem. Yes.
So Hardyan, are you ready with the?
Yes, sir. I am ready, sir.
Okay, so just maybe you can upload, and in the meantime, I think we shall start because it's already 11:04. Okay.
Okay, sir. I am uploading, sir.
Yeah. So once I finish with the introduction, so you can then start the video recording. Okay.
Okay.
So a very warm good morning, at least in India, to all the participants, and I think good night in some parts of USA. So it is my pleasure to introduce the first speaker of this session, Professor Shravanti Chaudhary, and a brief CV. She actually did BTech in radio physics and electronics from University of Calcutta, and then MS and PhD in electrical engineering from University of California, Santa Barbara in 2010. And she initially was in, I think, one company, Transform, for almost 2 years or 2.5 years, from 2010 to 2013. Then associate professor in UC Davis, University of California, Davis, from July 2015 to 2018. And since January 2019, she has been working as associate professor in Stanford University. So very briefly, that she has got Sloan Research Fellow Award in Physics from Alfred P. Sloan Foundation in 2020, this year. And she also is William George and Ida Mary Hoover Faculty Fellow in Stanford University since 2019. Very prolific researcher in wideband gap semiconductors, gallium nitride, diamond, power electronics, RF electronics. So we are going to hear from her today, from her video recorded lecture about the wideband gap semiconductors, and then specifically about the diamond electronics, which is another upcoming ultra wideband gap semiconductor. So please. So, Dr. Harshad Mehta, I think maybe you can mute yourself.
Okay.
Yeah. Yeah, thank you.
Dhyan, is there any problem with the voice sound?
I think audio is a problem. I cannot hear.
Dhyan?
Yes, sir.
Audio is not.
Audio is not audible to us.
But okay, 1 minute. सर ऑडियो नहीं आ रहा ऑडियो नहीं आ रहा
So Hardyan, I still see problem with the audio. I cannot hear it. Yeah, maybe restart it.
Dhyan, Jatin is there?
Sir,
Jatin?
Hello.
Yes, sir.
Is there any issue with the video and audio? Because it is a pre-recorded video. The audio is not audible to anyone, even though it is running by Hadyan.
Hardyan sir, am I audible to you?
Yes, sir.
Sir, first you have to stop your screen for
Okay.
audio. Then
Okay.
go back to share screen. There is a pop-up outside
Please stops.
sharing. Then go back to share screen.
Yes.
There is a option optimize
Optimize for
text and images. You have to change.
motion for and video.
Yeah.
Okay. Okay.
And the other side.
Hi, everyone. I'm Shrubanti Chaudhary from Stanford University. I will be giving a talk today on wide bandgap semiconductors. And the theme of my talk is about wide bandgap semiconductors and its role in ramping up the power density that our next generation of electronics look up to. I know you are all at home, and this is going to be a virtual conference. We were not hoping for that, but it is what it is. So I'll try my best to present the topic that I wanted to cover in that, keeping that virtual platform in mind. So again, I just wanted to introduce ourselves. So we are a wide bandgap lab at Stanford. And as you see, I have enthusiastic students and postdocs in my lab. Most of them are here. Still, we have missed a couple of faces. But this is our life these days. We are on Zoom. But we are still able to carry on our research. And I cannot thank my group enough for doing what they do. And today, whatever I will be presenting is is basically a result of their commitment and hard work. Okay, so I will be talking about wide bandgap, and these days we are talking more about ultra wide bandgap. So I decided to add the two together. And if you think about the wide bandgap semiconductors, the four applications that are emerging out of them can be classified into power switching, where you need high voltage and high current from the devices, and devices being transistors or diodes. You are looking forward to be able to beat the record of silicon, is basically why we are looking into wide bandgap materials, right? Silicon has done very well and continues to surprise us, with its newer and newer capabilities in IGBTs and other MOSFETs. But it is well agreed that there are certain material properties of silicon that will not jive for the type of power densities that we are talking about, as well as the kind of operating temperatures that we are talking about. So power switching is an emerging field. Whenever we think of a wide bandgap semiconductor, we are thinking about how does it fit into this power switching figure of merit, and so on and so forth. So that's an emerging field. The other one is microwave or millimeter wave communication. It's not new to us that beyond silicon, there has been gallium arsenide, which was looking very promising and did its part. But now we're looking into combining frequency and power, for which there are other materials that might be more meaningful, and wide bandgap and ultra wide bandgap semiconductors play a role in that as well. The other application area that is gaining attention are sensors and co-located electronics for harsh environment. Silicon for sure cannot handle the harsh environment that we are talking about, which includes high temperature or high radiation levels, as well as maybe stronger chemical environments and things like that. And this wide bandgap class of materials are quite inert to a lot of this harsh environment stimulus, and therefore they basically perform better under those extreme case environment. Last but not the least, which I will be talking a little bit today, is the passive use. Okay, so the first three quadrants that I just covered are more about the active use of the semiconductors. So they're either in form of diodes or transistors, but there are other use of wide bandgap semiconductors owing to their better thermal conductivity. Well, that applies to most of the wide bandgap semiconductors that we are talking about, such as silicon carbide, aluminum nitride, diamond. Diamond has one of the largest thermal conductivity of all materials, but definitely doesn't apply to gallium oxide. But nonetheless, there can be passive use of this wide bandgap semiconductors, and we can actually address some of the problems such as heat dissipation and things like that, which I will be alluding in my slides. Okay, moving forward, let's say, as I said, the title of my talk is How Can We Ramp Up the Power Density? Well, this is the so-called Moore's Law of power electronics, where we see that over the years, we have been able to address the need for providing higher and higher power density, first through silicon by moving from one device topology or device technology to a different device topology and technology, as you can see from the thyristor to BJTs to IGBTs to CoolMOS and other things, right? And then when silicon was plateauing, then we started to try out silicon carbide or gallium nitride. And now these two materials are doing pretty well. I mean, they are heavily researched topics. They are in the industry. They're penetrating the power electronic market. So they have done well, and they have not quite hit the promised space. Both silicon carbide and GaN underperforms compared to their theoretical limits, but nonetheless, they have enhanced the trajectory quite a bit from silicon, right? But then what next? So you can see from this trend that the future will also be demanding more and more output power density. So are we prepared for those, right? Or for those demands? And that's where those new materials like gallium oxide, diamond, aluminum nitride, boron nitride, they come into play, right? So I just want to emphasize that the innovations are happening at every level, system, circuit, device, and material. And we would, even if we exhaust all the circuit-based or system-based innovation, we would still be in a situation that we want more power density. So therefore, it is critical to add new material and add new device platform to this roadmap. So this is something that I won't be focusing today. Actually, most of the time I talk about gallium nitride vertical device, which has been a cornerstone of our research. And I just wanted to leave you with one view graph where basically, as I said, that when you are trying to get more and more power density out of it, you change your device topology or you change the material. So we haven't exhausted all possible device topology in gallium nitride, okay? So there are still more to come, more to offer, and that's happening. as we speak. So currently we are looking up to 20 kilovolt designs in gallium nitride using the vertical topology, and that work is going in its full glory because we have access to better materials now. Okay, so that's all happening in GaN, and there are many flavors in GaN, starting from HEMS to CAVITs to MOSFETs and diodes and static induction transistors and so on and so forth. So you don't have to make a case of a one size fits all for GaN. Actually, you can come up with different styles of devices to address different needs. Okay. Now that was the power electronics portion of it. How about, right? So the same story repeats here as well. What has happened over the time is, this is about millimeter wave or starting from microwave and then millimeter wave communication. We were looking forward to more and more power density in this research as well, right? So what have we done over the time? Well, first of all, HEMS are the perfect device designed to serve this sector of application, which is RF devices, right? HEMS come with the two-dimensional electron gas, which is horizontal in nature, and therefore you use source and drain on the top as well as the gate. And over the time, what people have shown is you can increase the power density by adding different technology nodes or coming up with different solutions such as passivation, for instance, or fill plating, right? Deep recess HEMS, okay, and UCSB, of course, is a pioneer of this technology, and they have shown over the years, along with other significant players in this, that how much you can improve the power density by using the right kind of process step or choosing the right structure, and more importantly, the quality of growth. It has come to the point where now the nitrogen polar gallium nitride shows record high watts per millimeter, and this is definitely promising for RF application. Okay, so I was reminding you the theme of my talk, which is why do we need power density? Well, if you don't have good power density, even if you have the best result that you can make up your day, like this one did back in May 2016, which is 7 kilowatts of power demonstrated by Raytheon at 95 gigahertz. This is a very big news, right? But even Raytheon will also agree that they wish this was more compact and they didn't need 4 people to lift up the cart, right? So what is the message of here? It says that this new class of materials, and this is showing in GaN, is capable of giving you power density and power both in unprecedented measures, okay? And that's very good news. Having said that, the form factor is very important, okay? So the whole goal of moving to higher and higher power density is not going to stop, so that we can reduce the form factor. Often we can reduce the number of components and things like that to get us to the goals or the targets that we have that comes from this application. So what I'm going to do now is I will be actually talking about a material which is basically not gallium nitride, but in my mind, this is an extremely promising time to work on diamond, another wide bandgap, I should call it an ultra wide bandgap material. And let's talk a little bit about diamond before we go into the research results. So diamond comes with a band gap of 5.47 electron volt. If you look at the material properties, it has very high electron and hole mobility, only if you can tap it. But the three other things which are also make it very attractive are thermal conductivity, which is very high thermal conductivity, right? And as well as the breakdown electric field. Okay. When I said three other, I actually wanted to emphasize electron mobility here as well, because you can use some of this mobility for your devices. Okay, so diamond basically presents, as we often call it, the best of every world, but then it does come with significant challenges. How do you grow the material? How do you dope it? So on and so forth. So as you can see, there's a nice comparison of silicon and diamond, where silicon is only 1.12 electron volt, and in comparison, diamond has a huge band gap, 5.47, but it comes with its own penalty. The dopants are very, very deep in diamond, okay? P-type and N-type doping are possible in diamond, just like it is possible in silicon. P-type results with boron and N-type with phosphorus. But both these dopants are quite deep into diamond, which makes it a difficult semiconductor in comparison with silicon. But then though some of these challenges are being addressed as we speak, and diamond can be now perceived as a dopable semiconductor, which makes it useful. And with that kind of a band gap, you can only imagine how power dense any device will be if it is made out of diamond. Okay, so let's see. This is a nice comparison that shows that you would need only 10 micron to hold of 10 kilovolts. If you compare with silicon, that would be 400 micron, right? So that speaks volumes for itself, that you can get highly power dense solutions or highly power dense devices with diamond, owing to its band gap and its high critical electric field. Okay, let's talk a little bit about growth and doping in diamond. Well, diamond occurs naturally, as we all know, and some of us might like it more than others. But the natural way of growing diamond is high temperature and high pressure, which happens in nature. But you can always copy that, which is what people do when they manufacture seeds of diamond, and they are called high temperature, high pressure diamond. But you can do it also in a much more inexpensive way, which is using a chemical vapor deposition tool. And what you can do is you can take the seeds, which are HPHT seeds, and then you can grow CVD diamond on top of that. Okay, this is what we do in our lab. And it grows in a very beautifully and very high quality diamond through chemical vapor deposition techniques. How about the doping? So for the doping, I was mentioning in my previous slide that we have all the regular suspects, as we are very familiar with silicon, boron, nitrogen, phosphorus, but the doping efficiency is really low. And that is because of how deep these dopants are, as you can see. So phosphorus, which makes it N-type, is around almost 0.55 EV below the conduction band, which makes it really hard to ionize under room temperature, right? Boron is 0.37, which is better than phosphorus, but still not great, right? So all of this makes it very difficult to dope diamond. However, boron doped diamond is much more available or much more feasible than phosphorus doped diamond, although in a collaborative work with Professor Robert Nemenich at Arizona State University, we have shown that you can actually dope all the way to 10 to the power 19 or even more with phosphorus. And you can actually launch an electron in the diamond's conduction band using this phosphorus dope technique. And I think that is a remarkable outcome. In the last slide, I was showing you the dopant levels in diamond, and clearly diamond is not an easy material to dope. However, N-type and P-type doping has been realized in diamond. They have been achieved. N-type remains challenging still because phosphorus incorporation in diamond is difficult. And then based on the orientation of the diamond, there are different levels of efficiency in phosphorus incorporation. So here you can see that there are two phases of diamond that are being discussed, 111 and 100. And both of them are quite capable of providing PIN diodes. However, we see that the N layer is more stable in 111 compared to 100. Okay, and also the phosphorus incorporation is higher with more efficiency in 111 than 100. Yeah, as you can see here that the blocking voltage on the 100 was up to 1 kilovolt. That was realized. The forward current density was a decent current density. There has been several works since then. You know, this was published in 2017, so this is relatively an older work, which showed that yes, you can do NIP diodes or PIN diodes in diamond. And one thing I want to point out that the N-type layer in diamond gets typically depleted. So even though you might expect this to behave like a PIN diode, ends up being what we call a Schottky PIN diode, where the N-type layer or the metal attached to the N-type behaves more like a collector of holes, which is evident from the forward characteristics. If your doping, phosphorus doping is very large, you can get the turn-on voltage, which corresponds to the VBI of the PN junction. But in many cases, even though you started with the PIN, you end up getting a Schottky or fully depleted NIP diode, which is a violation of basically a PIN functionality, but it does provide you with the blocking capability. And as you can see here, we have over 1 kilovolt of blocking capability that was realized with 100. So now let's think about some very interesting and very, cool use of this kind of diamond devices, right? So think about a harsh environment. Well, you cannot beat Venus, which is one of the harshest environment because of the chemistry in its atmosphere, full of sulfur dioxide and carbon dioxide, among other toxic gases like carbon monoxide and so on. But also the temperature is abnormally high, right? So if you want to make a prober, Venus prober, okay, which is of course full of electronics and electronically operated, then that electronics need to survive greater than 500 degrees C, right? So that imposes a significant amount of obstacle for silicon's use in these electronics. Diamond can be a great candidate, so is silicon carbide or gallium nitride, but diamond by far has the largest band gap, so it can be more stable, although that there are some, the verdict is not out on that because diamond can become carbon dioxide when heated to a significantly high temperature, maybe 900 degrees C or so. But again, there are pros and cons, and only we will understand after certain amount of research done that can this be a viable solution. But we were looking into diamond devices for Venus probing under a NASA program, more for functionality over performance and stability over reliability. Some of these applications do not require reliability, but do require stability for a certain amount of time to, let's say, capture a picture. So under that work, there were some very good results that were analyzed and collected and discussed. So we can go up to 600 degrees C of operation in a diode. Of course, the leakage goes up as it should, but still there is a decent on to off ratio maintained in this diode. So we went all the way to packaging and then testing this under a Venus gear test, which is basically presents a Venus atmosphere. And then we were testing all these diodes and they look very promising. Okay. Okay. Now to the very last part of my talk, I will just talk about diamond as a passive component or passive for a passive application, and that is the thermal spreader or heat spreader. So as I was discussing under the motivation slides in the beginning of my talk, that microwave and millimeter wave is requiring also for higher and higher power density. But with higher and higher power density or absolute power comes a penalty, and that is the phonon bottleneck. So we always lose to phonons, and these are very good materials, but they produce heat, right? And these materials often are heterostructures, and therefore the phonons do not have an easy way out of the channel into the heat sink. So one of the work that we're looking into is diamond as a thermal spreader or heat spreader. And this little bullets kind of give you an idea that if you are to produce 20 watts of power in millimeter wave domain, then you're looking for almost dissipating 60 to 80 watts out of it, right? That's humongous. That's really significant. So how do you do that? Otherwise, all these good benefits of, again, microwave or millimeter wave transistors is lost, right? So we are looking into growing, and we have done extensive work on this. I mean, there are lots of publications on this topic. If you're interested, I'll be very happy to discuss more. But there are ongoing work, and there are a lot of publications coming out. So I would really, I would definitely request you to look into that if you're interested in this topic, where we are looking into growing diamond as a heat spreading layer on top of argon GaN HEMT. Okay, and once we did that, we were able to show a drop in the channel temperature, right? And then we are planning to make the full devices, and we will understand how effective this is. So diamond polycrystalline grain, when bigger than 1 micron, can almost almost carry a thermal conductivity value, which is about 60% of the bulk conductivity. So that is what we are leveraging in this study. So to summarize, we are well focused on diamond. We are trying to do several flavors of devices, whether it's high power, high voltage, or radiation detectors, or studying the transport properties, or understanding how to integrate diamond for thermal management. It's really, really exciting that one material can have such a large footprint. And what I said is still not the full scope of diamond, right? There are more things that can happen in diamond. So, but bottom line is the material is extremely important, as with all other semiconductors. So we are focusing on the material development in collaboration with other universities and other research institutes. So there is a lot going on in diamond in the US, and in our group at Stanford, we are very excited to bring forward this research to you. So if you have any other questions or comments, please feel free to reach out to me. As a summary, I think as I just said, diamond presents a very wide footprint. Homoepitaxially grown diamond, which is possible, brings us closest to the superior material property that theory predicts. So we are very excited that we are able to unleash this kind of performance. Okay, but again, it's still at the very early stage. So we need to really make this repeatable, reliable, and the engineering scope of this work is not yet not yet complete. Okay, so a lot of science is happening, but a lot more engineering needs to happen to make it into a viable technology. With that, I would end it here. Hope you enjoyed this discussion, and sorry for some of the pauses that might have happened while I was recording this in my home. And if there is any background noise, I apologize for that. If you have any questions, feel free to reach out to me. There are quite a lot of publications from our group. You can always take a look at it and let us know if you have further questions or comments. With that, I would end it here. Thank you so much.
Okay, so let us thank Professor Shravanti Chaudhary for this very enlightening talk on wideband gap high power electronics, and specifically taking us to like the scope of diamond electronics also, and what future holds for diamond electronics. I think it was a fantastic talk. So if anybody has any question, they can either write directly to Professor Shravanti Chaudhary, or they can send an email to me also. I can pass it on to her. So with that, I think we finish with the first talk of this session. So now we come to the second talk of today's session, and this will be delivered by Dr. Harshad Mehta from USA. So as such, actually in this session, all the three speakers are from USA. So this is some kind of a nice coincidence. And a brief outline about the CV of Professor or Dr. Harshad Mehta. He is Chief Promoter and Interim CEO and CFO of VCCon Power Electronics Private Limited. This is actually a new kind of subsidiary of his company in US, and it is now in India. I think going to come for silicon carbide fab in India. And Dr. Harshad Mehta, he completed his BS in Physics, Chemistry and Math and MS in Physics from Vikram University, India. And then he did PhD in Electrical Engineering from the University of Florida. From 1983 to 94, he was the project manager at the Electric Power Research Institute. And then he established actually in 1994 Silicon Power Corporation in USA, and he is presently the chairman, president, and CEO of Silicon Power, this company. And his accomplishments include recipient of 2014 IEEE PES Nari Hingorani Custom Power Award and recipient R&D 100 Award from R&D magazine. He has several patents registered in his name. So today we are going to listen from him about, I think the title of his talk is Right Time for India for Silicon Carbide in Power Electronics. So over to you, Dr. Harshad Mehta. So you have to unmute yourself, please. Yeah.
Thank you very much, Professor Singh. I hope everyone can hear me. So my talk is a little bit different. Though I am a PhD, but I focus more on the commercial side of the technologies. A couple of must for me is I try to believe in manufacturable, usable, sellable technology. And the second is why not? So one may say that, okay, silicon carbide is still a research subject, but I try to accelerate the research, especially in US as well as in India. And we have been doing silicon thyristor work and silicon high power semiconductor work in Baroda since 2000. And now we are going into setting up silicon carbide ecosystem in India as well. So the reason for silicon carbide is very much evident. I think all of you know that we are looking for faster, more efficient, smaller, high power systems. And silicon, I think, is reaching its limitation. in terms of thermal capabilities as well as power handling capabilities. And the next technology is silicon carbide in terms of high field as well as high frequency, efficiency, high temperature, as well as thermal management. So from that perspective, we are moving forward in terms of setting up a silicon carbide ecosystem in India. And I feel that the time for silicon carbide power electronics India is absolutely ripe at this moment. Couple of factors that I see. There is already a large and growing market in terms of
So, excuse me,
Sure.
Dr. Harshad Mehta, sorry for interruption. Can you share your slides?
I don't know if I can. I am low
Okay.
tech, but I did send it to you if it's possible.
Okay. So
I
you
don't
will
know.
be giving. Okay. So please
So
carry on
yeah, right. So
the
I
way
will do
you
the
do.
audio. I mean,
Okay.
as I said, I still prefer to. This is all
Okay.
new for me, but I think I'm gonna try to give
Okay.
uh
Please.
most. Yeah. So I'm gonna try to give you a motivation for why we believe that silicon carbide is right for India right now. As you know, it's a large growing market, not only for India, but at the same time also the leverages that we have seen in India from the perspective of intellectual leveraging, as well as our ability to maintain and extend the life of an asset is incredible compared to Western world. And from that perspective, I think we can make product in India that is not only good for India, but we can also compete globally. Uh, all of the electric vehicle, as well as renewables, strategic electronics, grid, high power electronics, and so forth. I think we plan to go after most of those applications, starting from electric vehicle at about 1200 volt to 1700 volt silicon carbide diode and MOSFET. In 5 years, we will go up to about 25 kV bipolar thyristor kind of devices in silicon carbide for very, very high voltage, very high power application for high voltage DC as well as electric utility transmission applications. The second part, as you know, there are presently no big players or no other players in silicon carbide in India. And Make in India as well as Atmanirbhar Bharat is gaining a lot of momentum, especially in this COVID-related situation with the geopolitical issues. I think there's an urgency in terms of making these initiatives come to reality. I think that's very important. You may have heard about many of the incentives of Government of India in year 2020 in terms of production link incentive as well as advanced manufacturing and so forth. Visicon has been approved for taking advantage of these incentives and setting up silicon carbide epi, silicon carbide packaging, as well as silicon carbide device fabrication over next 3 to 4 years. The target market obviously are electric vehicles, renewable energy, data center, strategic electronics, and we expect, in general, I think the market for silicon carbide globally is expected to about grow 5 times in next 5 years. And we think the market in India always also would be significantly attractive from the perspective of making these devices in India. However, it does require not just idea or a talk, but it requires execution. And the team that we have put together has proved to execute the projects from greenfield all the way to the commercial product very effectively and very successfully. In year 2000, when I took when I acquired GE's, in 94, I acquired GE's high power semiconductor lab in fab in Philadelphia. And in 2006, I transferred that fab completely from Philadelphia to Baroda or Halol near Baroda. And we have been making products all the way to about 6,000 volt, 8,000 volt, and those are 4 and 5 inch single silicon devices that we do all of the diffusion, all of the edge termination, all of the plating, packaging, characterization, everything in India. We start from basic silicon wafer and we provide the end use product for industrial application, as well as we have provided product to US military application, products made in India. So our approach is really a very holistic approach that we want to address the entire link for the ecosystem, and we don't want to leave any weakest link behind. So our plan is to start from silicon carbide epi in phase 1, silicon carbide packaging phase 2, and while we are doing those phase in phase 1, 2, we would also set up silicon carbide fab, most likely in Halol, Baroda. And the Visicon is leveraging significant amount of expertise that we have created over last 27 plus years with Silicon Power, where I acquired a company from General Electric focusing on very high power semiconductor work. And since then, we also vertically integrated in terms of integrating those devices into field systems for electric utilities as well as industrial applications. We also acquired a technology portfolio from Harris Semiconductor, and that is primarily looking at defense application for power silicon-based electronics, and we are moving into silicon carbide applications for strategic as well as defense applications. I mentioned the company for last 20 years in Baroda, and that company is known as Ratan Shah International Rectifier. We acquired that company in 2006. It was mostly doing welding rectifiers, but since then we have grown into system applications for making rectifiers for Indian Railways, as well as making very high power, high components for US military applications as well. And we intend to build Visicon on the foundation of Ratan Shah Silicon Power, as well as I acquired a company in May of 2019 that used to be a fab of microchip in Oregon that is focusing on silicon carbide and gallium nitride. And we plan to do technology transfer from Bend, Oregon to Baroda related to both silicon carbide as well as gallium nitride. The applications as we see is obviously, as I mentioned, the electric vehicle, high-speed trail, renewables in terms of efficiency improvement, industrial application, again reducing losses, high power grid application, and defense electronics. All of the things that we intend to focus on, which are maybe in some case niche market, but they are very high margin, high performance, high reliability sector of the electronics sector that we intend to go after. So in general, I think even we do move very aggressively. One of the things I try to do is I try to ask myself question, why not? And once we decide to do it, for example, we already have placed an order for a silicon carbide epi reactor, and with Professor Singh's help and his students' help, we should be able to up and running in Baroda by June of 2021. The unit would be installed, delivered sometime end of March, and we expect it to be operational in 3 months. So that's our first set of ecosystem platform, which will support global market, and then we'll move from that silicon carbide packaging as well as device fabrication. So we certainly hope that Visicon will accelerate enabling technology future. And even though it's technology, my passion is commercialization, and I try to focus on approaching the entire business of technology in a much more frugal way, in terms of I am not trying to look for significant investment, 100 million, maybe $200 million of investment. So the recovery or return on investment could be a long time. Our plan is about $40 to $50 million investment in the first 3 phases. And we expect to make this happen. Within 3 years, we would have silicon carbide diode, silicon carbide MOSFET, as well as medium voltage and high voltage product out of fab in Baroda or somewhere in Gujarat or somewhere in India. So I'd be happy to answer any question, but sorry, I don't have the slides. I'm low tech, but we will share the slides. I would send it to Professor Singh, and he can share with all of you. If you have any questions, please let me know.
Okay.
Again, the issue is why. It's not why, but why not? I think India is ready for silicon carbide ecosystem, and we are here to make that happen.
Okay. So thank you, Dr. Harshad Mehta, for this very exciting conversational talk. And it's really heartening to know that your company is going to establish the first silicon carbide fab in India. So I hope there is a good future for wide band gap electronics in India, and more things are going to come up in from the manufacturing point of view. And even the government is also investing a lot of money in India, and we think that in manufacturing also there's going to be a kind of change. So I have just one question first. Maybe I can start. So if anyone else has any question, they can also ask the question. So after me. So I just want to ask that what is your take on gallium nitride power electronics? So do you think that silicon carbide or parallel to silicon carbide, maybe in association or in collaboration with government or support of the government, we shall go for gallium nitride also?
Absolutely. I think I feel it's not one or the other. I think it's complementary in terms of the application specific. For the RF high reliability kind of product, I think gallium nitride makes a lot of sense. And my company in Oregon, I call it Sycamore, which is silicon carbide and more. That means silicon carbide, gallium nitride, at least definitely, and plus something else. So I do believe that would happen, and we intend to pursue this in parallel.
Okay. I think that's a great news for us. So from the participants, anybody would like to ask a question to Dr. Harshad Mehta? Okay, so maybe if there is some question, you can pass it on to me also, and I can then send it to your question to Dr. Harshad Mehta. Some information I also have about this company, since we are working in collaboration. So I would be happy to share whatever information I have with the permission of Dr. Harshad Mehta.
Sure.
So thank you. Yeah. So thank you, Dr. Harshad Mehta, for this very nice and interesting talk. And hopefully in future we are going to meet sometimes in the coming year.
Soon, right?
Okay.
Soon.
Yeah.
Absolutely.
Okay.
Thank you.
Yeah. Okay. Okay. Thank you. Now I would like to hand over the session chair to Dr. Suchandan Pal from Siri Pilani, and a brief CV that he did his BTech in 1992 and MTech in 94 from Institute of Radio Physics and Electronics of Calcutta University, and PhD in 2004 from City University London. So he joined CSIR as scientist in 95, and his research area is 3 nitride devices, blue, white, and UV LEDs, integrated optics, nanostructured photonics, waveguide gratings, etc. So they have is in is wide band gap based optoelectronic devices. So the session is over to you, Paul.
Thank you, Dr. Singh. It's a great pleasure to be part of this program.
Yeah.
The remaining session, we have one invited talk that is from Dr. Anant Agarwal and another contributory talk. So before the talk of Dr. Anant Agarwal, I just want to introduce Dr. Agarwal. Although his CV is long, I just cut it short. Dr. Agarwal joined the Ohio State University, Columbus in August 2017. But before that, he was in US Department of Energy during 2013 to 16 and was involved, managed 4 programs related to wideband technology and their applications, including Power America, Next Generation Electric Machines, etc. He also was the director of R&D for wide bandgap devices at Cree Incorporation, where he was involved in developing and commercialization of silicon carbide diode and MOSFET power diodes. Before that, Dr. Agarwal was a fellow at Northrop Grumman Science and Technology Center, Pittsburgh, during 1990 to 99, where he led research activities on radio frequency silicon and silicon germanium transistors. And before that, during 94 to 90, he was associated in various organizations, including associate professor in Allahabad, in India, member technical staff in AT&T Bell Laboratory, New Jersey, where he was involved in developing gallium arsenide digital circuits and fiber optic communication. He received his PhD degree in electrical engineering from Leh University in 1984. He holds more than 60 patents, co-authored more than 300 research papers, with a book on silicon carbide technology, co-authored 5 book chapters, and was elected as an IEEE fellow in 2012. With this brief introduction, I request Dr. Anant Agarwal to give his talk, that is the road ahead for silicon carbide beyond 2020. So I request Dr. Agarwal.
Thank you, Dr. Pal. Can you hear me?
Yes. Very much.
Very good. I appreciate the introduction, and I will share my slides now. I'm going to go into the slide mode for a second, see what happens.
Yes, it is visible.
All right. So let's get started. So the title of my talk is The Road Ahead for Silicon Carbide Beyond 2020. I'm Anant Agarwal. I work at Ohio State University in Columbus, Ohio. I have also given you a link for my video courses on the subject of silicon carbide. Here's the link. You can use these talks are free. There are about 28 lectures on silicon carbide. And you just heard from Harshad Mehta. He is, I would say, he's a real industrialist, and he would make this road happen for silicon carbide beyond 2020. So I'm pretty much counting on him. So let's step back and just look at the big picture. We have silicon PIN diodes and IGBTs that are being used in 600 volt to 6.5 kV range in silicon. And these devices are bipolar in the sense that they have both electrons and holes participating in the transport process. And therefore, these devices are slow because you have to remove the minority carriers from a device to turn it off. I'm sure you have heard about IGBT current tail. Now, if we replace these devices with silicon carbide Schottky diodes and MOSFETs in 600 volt to 12 kilovolt range, these are unipolar devices. That means only electrons participate in the transport process. You can reduce the switching losses at very high switching frequency. And as a result, you can get 3% higher efficiency per power converter. So if you have two power converters and the power is going through both of them, then you'll get 6% efficiency advantage. Now, the bipolar devices in silicon carbide, such as PIN diodes and IGBTs, are not very reliable due to a defect known as basal plane dislocations. It may take another 5 to 10 years to solve those problems. But in the meantime, we have Schottky diodes and MOSFETs that would take us up to 12 kV.
Professor Agarwal, can I interrupt you for a minute?
Yes, sir.
What we are seeing on this side is the presenter view, not the entire slide. So we can see both the slide you're presenting and the next slide that is going to come up.
Let me see if I can swap the displays here. Is this better?
Now it is
yes,
okay.
that's perfect.
Okay, sorry about that. So silicon carbide, at least at this point, is well established. I started working on it in 1995. And after 25 years, this technology is now commercial. For some reason, every semiconductor technology takes about 25 years to become commercial. So you can see a lot of suppliers for substrates, epitaxy, and devices. What is happening in this device world is there are vertically integrated companies such as Cree and Infineon who are making everything from substrates to epi to devices. But also in the meantime, a foundry model has emerged, just like silicon, which is actually a very, very useful way to make silicon carbide devices, as you will see. There are number of foundries that are available worldwide to make silicon carbide devices on 4-inch and 6-inch material. XFAB is one of the primary ones we established about 3-4 years ago. That's in Lubbock, Texas. And then we have Sycamore, that is mentioned by Dr. Harshad Mehta. Sorry, this keeps switching on me. A number of other foundries in Asia and Europe. So the silicon carbide foundry business is expanding, and as a researcher today, you can send your designs to, for example, Sycamore through Dr. Harshad Mehta's company and get your devices made that way. So in doing so, you have to know nothing about silicon carbide device processing, but should be good in designing the devices. So this model is now bringing a lot of people into the tent, so to speak. The next big market for silicon carbide is going to be electric vehicle. And the reason is that the round trip efficiency advantage, because the power has to go from battery to the wheel. And when you brake, the power has to come back from a wheel to the battery. So that's called round trip efficiency. And that's about 6 to 8% over silicon. So that's a huge advantage. And everybody is adopting these devices today. And these devices will be adopted in 600 volt to 1200 volt range. For very heavy duty vehicles, even 1700 volt devices would be useful. For trains, 3300 volt to 6500 would be useful. And for the grid, you're thinking about 10 kV and higher devices. So if you look at some market reports, the biggest market today is essentially silicon carbide hybrid and electric vehicle. We started out with power supplies for the server market and then the PV converters. The next big market is going to be hybrid and electric vehicle market, which is really going to reduce the cost of silicon carbide devices and improve the performance. So no technology will be adopted unless it is affordable. So here is a look at retail pricing through DigiKey in the dollar versus the current for various silicon carbide devices from different manufacturers. And here we have in red the silicon IGBT from Infineon. And you can see there's a wide variation in silicon carbide devices cost, and that's because a lot of these manufacturers are fabricating devices in different parts of the world where the labor cost may be different and the substrate and epi costs may be different. So what we did is to look at the retail prices. This is the line in yellow, in blue. And you can see that if we take an average retail price, a retail price means you look up a DigiKey or Mauser, and you plot dollars per amp versus various vendors, you come up with an average price of maybe 40 to 45 cents per amp. And this is for 1200 volt silicon carbide MOSFETs. So, see if I can get a pen. Now, the retail prices tend to be at least 3 times the high volume prices. So in red, we have plotted the high volume pricing by basically dividing the retail pricing by a factor of 3. And you see you are now in the range of 15 cents per amp, which is still very, very high. So if you look at silicon IGBTs, that's about 3 to 4 cents per amp. So we have quite a ways to go before we become competitive. It's nice to have 6 to 8% higher efficiency in silicon carbide, but certainly it's not going to be adopted if it is at 15 cents per amp. We need to get down to below 5 cents an amp to be competitive with silicon. Okay, seem to be frozen here. Here we go. So in 2015, the reference is given here. This talk I had given at Ice Cream conference in, forget the venue, but it was published in Material Science Forum in 2016. I estimated the silicon carbide device pricing in a high volume market. And here is 1.2 kV devices. I did this analysis all the way up to 15 kV, but let's focus on 1.2 kV. And the details you can find in this paper here. But assuming $800 for silicon carbide substrate plus epi layer, which is going to be a 10 micron epi layer, a wafer processing cost of about $800 US dollars per wafer, which is slightly on the high side. You know, silicon IGBTs are processed at $300 per wafer. But even then, packing factor simply means you're trying to fit square chips in a round wafer, so you get some inefficiencies that way. Assuming an yield of 85%, which actually is very conservative yield, and assuming 6-inch wafers, and adding 50% gross margin, you get a cost of 4.7 cents per amp, which is definitely below 5 cents an amp. And this analysis has been done assuming 6-inch wafers. By 2022, we will have 8-inch wafers. So I'm certainly very sure that these prices for 1.2 kV devices are headed down to 4 cents an amp. The biggest issue, so we can make devices all the way up to 1.7 kV. Epitaxial material is easily available. However, to make devices at very high voltages where we can get into grid applications, renewable energy, trains, and so on, one would need higher thickness of epi, and that is today not very easily available. So I'm very excited to hear that Dr. Harshad Mehta is establishing a reactor in India where he would be growing epi. Perhaps he would be able to supply thick epi for 3.3 kV and higher voltages. And then this market will also take off very easily. So you can certainly see that the fundamentals of cost structure are there to compete with silicon. And I think the EV market will simply make that happen. Now let us look at let's look at a full silicon carbide DMOSFET cell structure. This is a 1700 volt cell structure where we are using a 16 micron epi doped at 5.2 E15. Here is the typical cell. You can see N plus source, P well, which is higher doped at the bottom and lightly doped at the surface to adjust the threshold voltage. N-type JFET region. Here, this is N-type JFET region. And as gate oxide of 50 nanometer, polysilicon, which is doped N-type, ILD, silicon nitride in the top metal. In my tutorial session where this talk may be available, I described how to actually make this structure process-wise and layout-wise, so you can get the details there. But most of the problems in this device are coming from the gate oxide. And that's because our inversion layer mobility in the channel is very, very low. It's of the order of 15 to 20 centimeters square per volt second. In silicon, as you know, it's about 400. So we have a long way to go. 15 to 20 is adequate for good performance, but not good enough. So what people have done is made the channel length to less than 0.5 micron and gate oxide of 50 nanometers or less, even 40 nanometers, to improve the channel resistance by thinning the oxide and making the channel length smaller. And these things give rise to other problems, as you will see. So our group is looking at commercial devices with respect to reliability issues, and I'll be talking about some of these results to you today. We basically buy commercial devices and look at various aspects of performance and reliability. As you will see, most of them are related to gate oxide reliability. So what is the problem with gate oxide? The problem with gate oxide is we have high density of interface states. And as you know, the states below the Fermi level will be capturing an electron, and these electrons will come from the inversion layer. So once you capture these electrons in these high density of states, you have very few electrons available for conduction in the inversion layer. So as a result, your effective mobility of electrons, the field effect mobility is very low, about 10 to 20 centimeters square per volt second. This has been a problem for a long time because of the carbon inclusion in gate oxide when you do thermal oxidation. The current recipe for thermal oxidation is thermal oxidation at 1300 degrees C with post-oxidation annealing nitric oxide or N2O. Some nitrogen is delivered at this interface, which reduces this interface state density. On top of it, you have a lot of fixed oxide charge. So you can now imagine negative charge in the interface states, positive fixed charge in the oxide. The difference between these two large numbers will set the threshold voltage of your device. And that's why when you measure these devices, you find wide variety of threshold voltage. But before I go there, this recent paper this year was published by Professor Kimoto's group at Kyoto University. And they seem to have solved the problem with interface states. So what they did, you have the reference here, you can look it up. They do in situ hydrogen etching. They deposit silicon without breaking the vacuum. Now they can break the vacuum and oxidize silicon at 750 degrees C so that it will not oxidize silicon carbide. So the trick is not to oxidize silicon carbide. And before you start, you do hydrogen etching of the surface and then deliver nitrogen at very, very high temperatures. At very, very high temperatures. I'm getting this message from Ashutosh Kumar. I don't know how to respond to it, so I'm going to ignore it. So by delivering nitrogen at very high temperatures, you can reduce the interface states. okay, so sorry, I had some technical. There was some message from Mr. Ashutosh Kumar. Anyway, so one, you can see the DIT now can be reduced to 10 to the 10 per centimeter square per EV, which is very, very similar to silicon values. And I just looked up a paper which was presented in Japan. I couldn't read the paper, it was written in Japanese, but you could see a mobility number of 85. So that's a big improvement from 10 to 20 number. So I feel now we have made a big breakthrough in silicon carbide gate oxides. So as I was saying, the threshold voltages are adjusted by the difference of two large numbers, positive charge and the negative charge in the interface states. So if you look at a vendor like C, even one vendor, you measure 100 devices, the threshold voltages are changing. You can look at this vendor E prime. The voltages are changing all over the place. So for some vendors, the threshold voltages from device to device are very stable, but you can also see there's a big variation in the threshold voltage. And that's because of the interplay between large fixed oxide charge and large amount of DIT in these samples. So another evidence of that you get if you take sub-threshold characteristics of these devices. So here are three vendors, C, E prime, and I, and we have measured it from room temperature to 200 degrees C. Drain source voltage is 0.1 volt. We have swept the gate voltage versus drain current. You see sub-threshold characteristics here. And you can see very high slope in vendor C. That means they have very high DIT. Green is a little better, E prime. It's probably the best of the lot. If you look at the sub-threshold slope, and then you look vendor I, which is slightly higher. And that will reflect if you measure the threshold voltage versus temperature, because at higher temperatures, the electrons will be emitted out of the interface states, and therefore the threshold voltage will drop because you're reducing the negative charge. And you can see that these devices have a huge fall in threshold voltage versus temperature, which is an indication of high DIT. You can see that device E prime and I, which had a steeper slope here, also have very reasonable threshold voltage drop at high temperatures. Then you look at threshold voltage instability. Here's a vendor I. We basically, red curve is a measurement of subthreshold characteristics before any stress is applied. And then the green curve is after 10 volt at 250 degrees C at 30 minutes. And then the blue is minus 10 volt at 250 degrees C for 30 minutes. And you can see you can move the threshold in either direction by applying the positive and negative stress. You can do the same on different vendors. Vendor D prime obviously looks very, very bad compared to vendor E prime. And there are much worse examples. So what is going on here? One would ask. So what is happening is that there are lot of defects in this oxide, probably related to carbon near the interface. And these defects can accept electron by direct tunneling and under the positive bias case and move the threshold positive, or these electrons can tunnel back under negative bias and move the threshold negative. So the presence of these high near interface traps basically indicate that we have a lot of defects in these oxides, perhaps related to carbon. The other thing I would point out that we measure time-dependent dielectric breakdown because we want to predict what would be the lifetime at 20 volts of gate voltage, which is our operational gate voltage, and we want at least 100 years or higher for automotive application. But most people measure devices at very, very high voltages, above 8.5 megavolt per centimeter in the oxide. And what happens, you have impact ionization in the gate oxide, which creates holes. Holes travel to the interface and get trapped, and trapped holes increase the electric field there and reduce the lifetime. So when you project it with the dotted line, you project very, very high lifetime. But however, if you measure the lifetime at lower fields, below 8.5 megavolt per centimeter, as shown by these points and these points, you can see that now you can predict a more reasonable lifetime for these devices. These devices are from 2 different vendors and they have different gate oxide thicknesses. So therefore, it's not easy to compare them, but you see this behavior very clearly. So the idea is one should do the time-dependent dielectric breakdown measurements at lower voltages. The downside of doing this is you will have to wait for months to 6 months to a year to take data points, because at high voltages they fail faster, at low voltages they take a long time to fail. So that's a disadvantage of this method. There is another defect in these devices, and that is basal plane dislocations. So basically, you see these basal plane dislocations, which are running at 4 degrees off. And as we forward bias this body diode, so if we forward bias this body diode here, then electron holes recombine and this basal plane dislocation becomes a stacking fault, which is a huge defect. And if there are many of these basal plane dislocations, as shown here, they originate from the substrate into the epi, can be process induced also for room temperature implants. There's several papers here, you can read about them. When that happens, then the performance of the device changes. So here are 3 vendors which have 1700 volt devices. You can see that we have stressed them up to 100 hours. And this vendor D prime, you can see the body diode. This is the body diode characteristics. Changes quite a bit in 100 hours. Here for vendor G, only small change, and vendor E prime, no change at all. So I think vendor D prime is using room temperature implant and causing a lot of defects, which result in basal plane dislocations. So when that happens, you can see the vendor D prime has degraded the on state characteristics quite a bit. It goes from low resistance to high resistance, and that's because majority carrier conduction is affected by those stacking faults. So let's keep moving here. One of the key parameter that we should measure is the short circuit time. So here, by short circuit, we mean if you are sitting at 800 volts and for some reason you turn on this device, you're going to have a lot of current flowing and a lot of heat dissipation, and that heat dissipation will destroy the device. The question is, how long can this device last before you destroy the device? And the standard is the device should last at least for 10 microseconds. So important thing to do in design is to reduce this current, which is at full voltage of 20 volts at high voltages on the drain, like 800 volts. You can see that you can put a high P shield region in the bottom of the P well, and for a 0.5 micron channel length, that is going to reduce the output current by at least 30-40%. So then you can improve the short circuit time by 30-40%. If you measure these devices, commercial devices from these three vendors, short circuit time at gate voltage of 20 and drain voltage of 800 volts, you see that short circuit time is widely varying, but it's from 2.2 to 5 microsecond. Now, 5 microsecond may be enough, but 3 or 2.2 microsecond is not enough, because the gate driver has to sense that a short circuit has happened and then turn off the gate voltage on that device. And that's why we provided dead time in our PWM schemes. You can obviously improve the short circuit time if you go to lower and lower gate voltages. You can get as high as 8.8 microsecond, but at this point, you please realize that by operating the device at 14 volts, your on resistance has gone quite a bit. So the device is not conducting as much as you would like it to conduct. So the other easier method is to put some kind of source, some kind of resistance in this source contact. And if you put the resistance in the source leg, then as the current flows through this resistance, the gate source voltage is automatically reduced. And you can see that example here for channel length of 0.5 micron, the output current can be reduced substantially by putting a resistance of 10 to the 4 ohms. If you put 10 to the 5 ohms, it will reduce even more. So this is an effective way of improving the short circuit time. Here for vendor D prime, we did this exercise. We put an external source resistance of 50 milliohm. And you can see this this is the current trace. This goes all the way up to 142 amps for 10 microsecond in this device. Short circuit energy that is dissipated is 110 millijoules. That, after putting the source resistance, can now be reduced to 98 amps, and the energy is reduced to 85 millijoules. So I think the device can withstand longer short circuit times if you have a source resistance. So in summary, I would make certain points. I would say that commercial silicon MOSFETs are generally very robust and reliable, but reliability can be improved by design and process. silicon and silicon carbide commercial foundry model and demand by the EV market will drive prices to within 30% of silicon and $10 billion annual revenue within a decade just for one application. Silicon carbide wafer diameter is headed to 200 millimeter, which is 8-inch by 2022, which will further lower the prices. One key problem of low inversion layer mobility has been solved, as I described by Kyoto University, which will allow silicon carbide power devices to penetrate the high volume 600 volt market. This is a very important point. So far, we have not been able to penetrate this market. We have stayed at 900 volt and above, but now after having solved the inversion layer mobility issue, we should compete very, very solidly with gallium nitride. In fact, I can predict that a lot of power applications at 600 volt gallium nitride will be replaced by silicon carbide. With that, I would encourage all the EC departments in the world to expand their curriculum to include silicon carbide power devices and silicon carbide based power electronics in their curricula, because silicon carbide is here to stay and it will slowly replace silicon from a lot of power electronics application. So with that, thank you, and I would be happy to take questions.
Thank you very much, Dr. Agarwal, for your very interesting and enlightening talk. Obviously, it is futuristic, particularly in Indian scenario. It is futuristic. We hope that in India also we can take up some of the problems to make it and commercialization, because the electrical vehicle is also is taking initiative for this. But again, all depends on the government policies, everything, what are the issues available. So now it is the some couple of questions if anybody has.
So Professor Paul, can I ask one
Yes.
question? Rajan.
Yes.
So Professor Anant Agrawal, thanks for very nice and interesting talk and on silicon carbide and showing the way forward. So definitely, I think in India also some efforts are being put also to include silicon carbide in the curriculum, and maybe we also need help from experts like you. So thank you for again for your this nice talk. So I just have one question, that when you typically measure the interface trap density in silicon carbide MOS devices, so what is the preferred method? Is it the CV method or the GV method? Is conductance voltage, or which method is adopted usually? Which is more accurate?
Now both methods are good. CV method, high-low technique is very useful as long as you apply some corrections, and those corrections have been described by Professor Kimoto.
Okay.
From Kyoto University. In his paper might be 3-4 years old. And also the conductance technique is also used. We prefer using the fabricated MOSFETs to measure the interface state density.
Okay. So thank you.
Thank you.
May I ask one question?
Yes, please.
Yeah, hi. So I'm Ashutosh. So thanks, Professor Agrawal, for giving a nice talk about the future and the current status of the silicon carbide. I have one question, like probably very common between the competition between GaN and silicon carbide. In last couple of years, the people have shown 4 kilovolt and last year 5 kilovolt vertical GaN device. So now where you see that typical competition between gallium nitride and silicon carbide for the high power, because people have started to showing 3 kilovolt, 4 kilovolt, 5 kilovolt GaN devices now.
That's a very good question, Ashutosh, and I have a very clear view on this, which I can share with you. I think vertical gallium nitride devices are good for research. They will never become commercial. And the reason is gallium nitride is at 2 inches today, silicon carbide is 6 inches. You go to 4-inch and gallium nitride will be at 10 inches. So it will never catch up with silicon carbide in terms of cost.
Okay.
The second problem is they don't have a native oxide, so the devices will be normally on. And then you have to cascode them with silicon MOSFET or something else. Cascoding for high voltage, high current is a very dangerous thing. So I don't see any future for vertical gallium nitride devices. I'm sorry to say that.
No, it's okay. Like, but like means I have seen Infineon putting a lot of efforts on 8-inch GaN on silicon. So let's see where it goes. So
so that's
thank
a
you very much.
lateral. That's a lateral device, right? GaN on
Yeah,
silicon.
that's kind of the semi lateral device. Yes.
Right. That's for 5G market.
Yeah. Okay.
Okay,
Yeah.
thank you, Dr.
Thank you very
Ashutosh.
much.
If there is any other question, just a very quick question. Otherwise, we can go ahead.
This is Vasu here. I had a quick follow-up question on this GaN versus silicon carbide thing. So, Dr. Agarwal, assuming that mobility was the problem with silicon carbide and breakdown and reliability are the problem with GaN, and let us say both of them get solved in both systems, which one do you think would be the favored? Because band gap wise, even GaN is 3.2, silicon carbide is around 3.2. So get rid of the defects, let's say breakdown and reliability improve, but mobility is higher. Which one do you think will win out?
Right. So that's a good question. And let me put it in context. Let's compare 600 volt to 900 volt market. And let's think about lateral GaN devices. And that's where if you solve the dynamic R-on problem, and if you solve the breakdown voltage problem and avalanche problem, you can make some inroads into low power applications up to about 10 kilowatt. I think the problem is at very high powers, gallium nitride being a lateral device, you have to parallel a lot of them, and that introduces a lot of inductance in the circuit, and with inductance you get a lot of LDI-DT type of issues. So I think low power 5 to 10 kilowatt is probably good for lateral GaN, but other than that, I think silicon carbide would have to handle higher power applications. Now,
any quick
in terms
comments
of
on next gen?
Next gen what?
Next gen is the startup making vertical GaN power devices. I think it's a follow-up of Avogene.
Right. I am going to support everybody who's trying to do technology development, but when I put my industrial hat on, I see no future for vertical GaN devices.
Okay, thank you.
And if you can write to me, we can discuss this in more detail.
Yes, I will. Yeah.
Dr. Suchandan Pal? Okay, if there are no questions, just we'll move to the next.
Okay. So I think the next talk, Dr. Manikant Babu, you yourself are giving. Okay.
Yes, sir.
So
Yes.
you please upload your presentation.
Yeah.
Yeah, Dr. Suchandan Pal, you are muted. Please unmute yourself.
Okay, okay, okay.
Yeah.
Yes, yes, yes. Yeah. Now, next presentation will be made by Dr. Manikantu Abu, and the title of the presentation is Exploring Current Conduction Mechanisms in 6 millivolt silicon 3 plus ion irradiated in gold, silicon oxide, boron doped gallium oxide, metal oxide semiconductor devices. So, without much delay, I request Dr. Manikantu Babu to go ahead his talk.
Okay. Are you able to hear me?
Yes, it is.
Yeah,
Your
thank you.
also visible, and you are audible.
Yeah. Thank you very much for the introduction. So I'm Manikanta Babu from Metal Science Group, Indira Gandhi Center for Atomic Research, Kalpakam. So this talk is about the gallium oxide based metal oxide semiconductor devices irradiated with 6 MeV silicon ions. So this work was carried out when I was at Indira Gandhi Center for Atomic Research, Kalpakam, as a National Postdoctoral Fellow. Later, I moved to IIT Delhi and working with Professor Rajendra Singh as a postdoctoral fellow. So this is the outline of the talk. Starting with the technological significance of beta gallium oxide and the radiation response of the MOS devices that we have fabricated with the silicon dioxide, and exploring few tunneling mechanisms, and followed by some conclusions. So coming to the silicon-based devices, moving to the because of the constraint of the band gap and the breakdown field, and moving to the silicon carbide and gallium nitride-based high-power devices, the huge market of the power devices has been taken over. You can see the life cycle of power device technologies from 1970 to 2020 in both the unipolar and bipolar devices, and the frontier materials, frontier wide band gap materials of silicon carbide and gallium nitride has taken over in such a grand fashion. However, the limitations of the breakdown field and the band gap of 3.2 electron volt, people are trying for the other materials which can have a higher band gap and the higher breakdown field. In such a context, gallium oxide has become one of the leading contenders of the power electronic devices, which can be fabricated at an ease and with a low cost to the substrates. So, based on the gallium oxide the wafers, we are fabricating a few devices of Schottky diode or MOS devices detectors. These are widely reputed in gallium oxide community. Since this talk is on MOS devices, the trade-off between the energy band gap and the dielectric constant is has a much critical role in these newly emerging beta gallium oxide MOS devices. So starting with the silicon dioxide, the traditional gate dielectric with the silicon technology, which has a 9 electron volt, the highest dielectric constant of titanium oxide, which is close to 60. There are a wide variety of oxides that are available to be implemented as oxides in beta gallium oxide based devices. This we are studying the radiation effect. Just I want to just quickly turn to the this slide, which has the picture of the Earth's magnetosphere. If you can see the if you can see the here two radiation belts, which are known as Van Allen belts. The first one is the inner belt, and the second one is the outer belt, which are separated by a slot region. These are the radiation belts which contains very highly energetic protons and electrons and the heavy ions. So the entire radiation spectrum, if you see, the 85% of the proton radiation and 14% of the alpha particles and 1% of heavier ions will be shared and continuously bombarding its magnetosphere. So when the space electronics are concerned, and whenever the low Earth orbit satellites are concerned, this is a major issue. So in terms of this beta gallium oxide based devices, the radiation response in various radiations, electron to proton, neutron, X-ray, alpha particles, and gamma rays, around the globe, people are working on various devices, and especially MOS devices. People have tried very effectively using the gate oxide, using some various methods, HFO2 and Al2O3 and SiO2. So in our case, we have fabricated beta gallium oxide based MOS devices using silicon dioxide. This silicon dioxide has been deposited with the operation, and gold and titanium gold are used to be Schottky and ohmic contacts. We have used a facility at 1.7 MB 10-electron accelerator facility at Indira Gandhi Center for Atomic Research. We have used 6 MeV silicon with ion fluences 1E15 to 516 ions per centimeter square, with maintaining the current of 200 nanoamps. The estimated electronic energy is 3.44 keV per nanometer, and the depth is something around, it will go across the silicon dioxide of 3.3 microns. So in order to study these devices, some of the few challenges in fabrication point of view, like band offset interface engineering, Fermi level pinning, and charge trapping, which comes generally with the type of deposition. If you have ALD, then the charge trapping will be less. And the shallow traps, indeed, within the conduction band, few electron volt from the conduction band of the gate dielectric. On the other hand, few phenomenon from the irradiation point of view after fabricating a reliable device. So we have some models to understand what kind of irradiation effect that can takes place in the fabricated devices. Irradiation-induced phase transformation is a possibility. If we have high energetic ion interface mixing across the beta gallium oxide and the gate dielectric is also possible. People will think about radiation damage whenever we talk about irradiation, but also one interesting aspect is the thermal annealing of the devices. So in that, the pre-existing defects can be annealed out at a particular fluence. We just name it as a critical fluence in such a case. So this is the MOS capacitor, the preliminary study we have carried out. We have used this, we have fabricated with the SiO2. So when the ion passes through the SiO2 interlayer, create point defects. So this electronic excitation induced defect, electronic induced traps, attract the electrons and holes together during the electrical measurements and causes some variations and create defect levels also. So coming to the tunneling mechanisms, we have explored with the tunneling mechanism. There is a one order of difference in leakage current from the pristine to higher fluence sample of Phi-16. So we have explored the injection case with the Fuller-Nordheim tunneling, and the Fuller-Nordheim tunneling has been completely disappeared at Phi-16 and has been taken over by the Pulle-Frankel mechanism. The Schottky barrier height has been estimated using the so ln j by e square versus e by e. It was found to decrease with from 2.5 to EV to 1.83 from the pristine to high fluence sample. So if we clearly see the first graph of this, so there is a clear variation of the current with respect to the voltage, and as the fluence increases, it starts fits very well. It starts fitting very well with the PF tunneling mechanism, which deals with the defects and traps. So after the -5 volt, the current conduction mechanism has been completely taken over by the PF tunneling mechanism, and which is very much dominant at the highest fluence sample. So the electron trapping can be happen with the neutral oxygen vacancy as a platform. The injected electron can be trapped either one or two. Depending upon that, the oxygen vacancy or single vacancy or divacancy can be estimated. From the PF emission, the estimated trap is 0.4 electron volt from the conduction band edge of silicon dioxide. So since we have used a silicon dioxide of 10 nanometer, which is very less, so we have turned to dig into the direct tunneling also to see the effect at very less voltage region of 0 to -3 volt. It is fitting well. After that, it is completely taken over by the direct PF tunneling mechanisms. These are the overall conclusions of the work that has been carried out. MOS devices with silicon dioxide as a gate dielectric of beta gallium oxide has been fabricated and irradiated with silicon 6MA silicon 3+ at various fluences. Various current conduction mechanisms have been explored, and the PF emission is quite dominant at 569 per 10 power 69 per centimeter square. The average depth is close to 0.3 electron volt. The barrier height is also reduced to 0.52 to 1.83. So I'd like to thank the collaborators, Professor Rajendra Singh from IIT Delhi. Of course, in fact, I joined with him as a postdoctoral fellow right now. I carried out my work with Dr. B.K. Panigrahi and two the people, and Dr. Biatek for his help during the deployment of the contacts. Now looking forward to work with Hadian. And thank you all for the.
Thank you, Dr. Manik Babu, for your presentation. It's a good presentation. Now it is forum for if there is any question. Dr. Manik Babu, I have a slight small question. That you have fabricated the device the material. You have grown the material, deposited the material, or
the commercially available beta gallium oxide substrate. On top of that, we have grown silicon dioxide using electron beam evaporation.
Okay. So that is standalone substrate, beta gallium oxide.
Is the standard substrate that we have got it from Tamura.
Okay. Any other question from anybody? So if not, then I thank you for his good presentation and for the work you have carried out. So it's the end of the session. So now I hand over to Dr. Rajendra Singh for the next formalities.
Okay. So thank you, Professor Paul. And I would like to thank all the speakers, invited speakers, and Dr. Manikant Babu presentation. It was really a very nice and informative session. So with that, we come to the end of this session, and we are now closing the session. So we are going to meet again at 2 p.m. and where the next session will be chaired by Professor Srinivas Raghavan from Icee Bangalore. Okay, so thank you. Bye.
Hi, Sudhiranjan. This is Vasu here. Can you hear me?
Yeah, can you hear me clearly?
Yeah. You want to put your presentation up on the screen?
Okay, okay. Just check now. Can you see?
Yeah. You want to put it in full screen mode? Yeah. Looks
It's
good.
full screen, right?
Yeah. Great.
Everything all right, right? Okay.
Yeah. Looks good.
So do I need to show video? No need, right?
No, up to you.
That's okay. Okay.
Up to you. Yeah.
Okay. So this is clear, right?
Yeah. It looks good. Great. How are you otherwise?
Fine, and we are still, in a very difficult team A, team B mode, and then just now we are back to operation in September.
Acha.
Right now there are no COVID cases here. It just happened day before yesterday. There were 2 cases,
I see.
and for a month there were no active cases. They were all import cases. So still we are not sure what is the status. Anyway, 1 year we could not travel, so that's a major issue to go home.
Right.
Yeah.
Interesting. Hopefully the vaccine will soon come, and I think things will normalize hopefully in the next 6 to 2 months, what I'm guessing.
Crucial.
It'll take.
Yeah, crucial. Yeah.
Yep. So we have about 5 minutes to go. I see that you are here. I don't see any of the other participants yet. Arnab is not yet.
Yeah, mine is first up, so I have to enter first, right?
Right.
So it shows my full screen. Okay, laptop full screen.
Yeah. Everything looks perfect. Yeah.
Okay, that's just an introduction slide I put so that people can come and look at.
Yeah.
Dr. Masataka is speaking today, right?
Yes, the third talk, I think, or the second one, I don't know. Arnab, Masataka. Yeah, you, Arnab, Masataka, and Mukesh Kumar from IIT Ropar.
Okay, perfect. How is the GAN fab coming up?
I was wondering when you would ask me that question.
Because 5 years, I have been waiting for 5 years,
So have I. I have lost hair and it has become white now.
And Professor Anand pushed me to silicon carbide, and then
Right.
we have to see how fast we can catch up.
Right.
Because it just started last week.
Anant Agarwal, is it?
Yeah.
From Ohio
He
State.
said Ohio.
Okay, he just gave a talk in today morning.
Yeah. I have all his information, slides, what is going to present.
I see.
He's like a mentor to everyone.
So he was in India before he went to the US, is it?
Yeah. He is now closely associated with our plant, so that the reactor going to Gujarat and all this is a replica of what we are doing, the first one. Second one is the 8-inch one we have. So 6-inch that reactor can produce 4-inch, 6-inch, all the things in India. So that is a good thing that Icee, all they can work together with Dr. Data. Yeah, so we are aware of the plan, so that backup is here in Singapore for the supply chain.
I see. So you are part of the team that is implementing?
No, because from institute I cannot participate. We will do any technical development training here. That can be in SPIDA. So Professor Anant is also involved in somehow. So the Sycamore fab that we're going to use also for our next year plan, the grant coming for us to prototype. So right now 4-inch, they are going to 6-inch next year. That's the plan.
Okay.
So that is where we have to prepare our roadmap. So we created a roadmap, and that's how things move.
I see.
Which is good.
Okay, so we have 2 minutes to 2. I think what I can do is I can get you introduced and get started. Okay.
How many participants? I can't see.
So, see, I just checked, and on the Cisco WebEx platform itself, there are 13 participants. But then there is also this other online, you can log in through Chrome and Edge, and I don't know if everybody is visible here.
Oh, I see.
Because it appeared that, yesterday I had logged in through that Chrome interface for another talk. And so when I had posted a question there, it didn't get relayed here. Then, so I'm hoping that there are two modes. I don't know. Currently in this window, there are 13 participants, including the two of us.
Okay. Yeah, but nicely organized. Thanks to everyone. The team of Dr. Rajendra Singh and his team, Professor Khare, the whole IIT Delhi team has done extremely well.
Right. I mean, yeah, given that you had to make this transition in between, and it's always you started doing it one way, and then all of a sudden you're asked to stop and doing it some other way. It's always a challenge.
And your friend watched your presentation, huh?
I'm
your
sorry?
Your friend watched your presentation very nicely. We were looking at your talk from the office.
See, that is what I was saying, right? So when I was presenting, I didn't see you in the list here.
Yeah.
So I don't know. I think let's get started. It's 2 o'clock.
Okay, let's start. Yeah.
So let's get started here. Good afternoon, everybody. My name is Srinivasan Raghavan. I am from the Indian Institute of Science in Bangalore and the chair for this afternoon's session, the last one in Icee. Thank you all for being here. It's a cold and rainy day in Bangalore. And we have 4 speakers, 2 from India, 1 from Singapore, and 1 from Japan. They all need no introduction. So in the best interest of time, I think we could get started. The first speaker is Dr. Sujirandan Tripathi from IMRE in Singapore, and he will be telling us about GaN, and I'm guessing also silicon carbide for power applications. Is that correct, Sudhir Ranjan? Yeah, power electronic applications. So with that, Sudhir Ranjan, you can start.
Okay. Thank you, Dr. Vasu, and Namaste, India, and especially I meet IIT Delhi. So this is my 20th year in Singapore. So I started 20 years back my journey from IIT Delhi to Singapore in US and then IMRE. Okay, so just to introduce today, I think Professor Anand, Dr. Mehta, and there are many nice talk by also Srabanti gave an introduction to silicon gallium nitride and diamond. So if you look at the industry driver at this moment, silicon superjunction to be replaced to some extent by gallium nitride. Those are gallium nitride HEMT, but silicon carbide trench MOSFET is gaining momentum because of the EV market. A lot of work is going on now in the gallium nitride vertical devices, and the cost is an issue here. I think beside the cost, I don't think performance-wise any issue, but gallium oxide now catching up. So the cost is medium, but if they want to scale up to 6-inch, they can outperform gallium nitride vertical devices. That's what we think. But it's a long way to go for gallium oxide because of thermal conductivity issues. But HEMT at this moment is mostly GaN on silicon. That is cheaper option to go to 650 volt. And today I will share you, we are moving towards 900 volt E-mode devices. And gallium nitride can compete in this space, but the ultimate power devices for gallium nitride application will be 1200 volt, 20 amperes using GaN on silicon platform. So there where we have to put our research efforts. And I think silicon carbide is, I think, is opening up a big way now. And today I will also share why it is important to go to 200 millimeter rather than 150 millimeter platform. So this is where I think the two material family, gallium nitride and silicon carbide, will dominate in SDK. And this is good news for gallium nitride community at this moment. If you look at just the power market, it was really a very big hype before for gallium nitride. Now it was just $9 million. If you look at your market only for power, I'm not considering the GaN on silicon carbide or GaN on silicon RF by MACOM. So if you look at from 9 million, it is going to jump to 350 million. That is the nominal scenario, the right hand side, if you see the market report. But if it's a bad scenario, if it happens, all the consumer electronics, like all the mobile phone chargers, the laptop chargers, Oppo, Vivo, all the companies are now implementing gallium nitride power converters. So it is going to reach 750 million within, I think, 5 years' time. So there's a road ahead for this, I think, decade. If you look at up to 2030, how much data center penetration would happen for UPS, I think gallium nitride has to work at 1000 volt plus. And this is where I think a lot of our research community need to closely look at. We should not create hype on gallium nitride, but try to put all our energy to solve the problem in gallium nitride and make it more and more perfect so that it can displace some of the silicon and silicon carbide, the low voltage design. And if you look at silicon carbide, I think it's a $10 billion market coming up within 2027. And this is, I'm talking about only front-end chips. And it has improved the efficiency. The commercialization is in a big way. So research component is very low. So if we want to focus on silicon carbide, it will be more like downstream research, but device design, solving some defect issues in the material family. I think that is somehow we can say upstream research for academician, but it is a purely commercialization game now. So if you look at typically silicon carbide MOSFET, you can buy now in big way 20 cents per ampere. It's already available in a big order for 1200 volts for automotive application, but still it has to go down to 4 to 5 cents per ampere. So that's where we have to reduce the cost of silicon carbide substrate, scale the substrate from 150 millimeter to 200 millimeter. Also, the epitaxy cost has to reduce. So how fast you can deposit the silicon carbide, run-to-run operation, how you can reduce the cost, that is also important. And also some of the activities that high temperature implants, they can bypass few steps and use low temperature implants to reduce that cost. So these are some of the areas that A-STAR program is going to address, and we are focusing on substrate epitaxy, and we will work with our sister institutes and our commercial foundries to produce GaN silicon, silicon carbide MOSFET and silicon carbide substrate. So at this moment for the team now, we are just targeting how we can do good epitaxial wafer development that can go up to 10 kV MOSFET potential. This is the goal of our team from IMRE. And as Professor Anand gave a very nice presentation today. So if you look at his vision, right? So silicon carbide moving from unipolar device, it will go to bipolar device, as Dr. Harsad Mehta also spoken. The big goal is to go to 50 kV in future for IGBT and thyristor. So if we're talking about up to 10 kV MOSFET using silicon carbide and silicon carbide, the research to start now how to scale up the IGBT platform. So the IGBT require P-type silicon carbide, not N-type silicon carbide. So there are a lot of things, whether you have to do freestanding P-type silicon carbide or some kind of smart cut of silicon carbide, but P-type is always highly defective material. So if you produce on 2-inch and 4-inch, it's very difficult to compete in terms of cost. So it has to be scaled up to 6-inch and 8-inch platform in future. So that's where I think Professor Anand was also we are having a road mapping exercise, how to move this direction forward, and how this N-type substrate cost will reduce and qualify the reliability test. So that is where a lot of research is going to happen in this domain. But GaN definitely going to up to 1 kV, so up to 1000 volt to 1200 volt, GaN to dominate the market. So right now it is silicon carbide trench MOSFET for 1200 volt, but for me, I don't think trench MOSFET is necessary. A 1200 volt or superjunction is necessary for silicon carbide. I think simple planar MOSFET with a good reliability is fine for 1200 volt automotive application. And then from 1.7 kV onwards to 10 kV, there I think we need to do a little bit of upstream research in terms of reduction of cost and the defect reduction, so that when you do high temperature implants, how much defects you can reduce the PFR during the growth and also during the processing. So typically, if you look at Professor Anand's viewpoint, I think if you look at where the GaN is going to be applicable and where silicon carbide is going to be applicable. So if you look at the GaN, it is already making very good progress on the home appliances, laptop chargers, phone chargers. So this market is actually very big. So I think this market will be $1 billion within 5 years' time. So there is no issues with gallium nitride research or foundry development. But yes, we need to perfect gallium nitride on silicon or gallium nitride on silicon carbide further, so that we can compete in terms of cost. This is what the gallium nitride from the power side, but RF looks good. I think no need to worry. The GaN on silicon carbide is going to open up in a big way when we are moving from 5G to 6G application. So there is where I think we need to do a little bit of research on how we can make short channel short gate and devices like sub 50 nanometer transistor to move from 5G towards 6G application. The market is very big. So there's a $1 billion market already for the RF devices. So the GaN on silicon carbide, GaN on silicon, both going to compete in this space. GaN on silicon up to 120 gigahertz, maybe band hams. But if you're talking about H band hams and 300 gigahertz application, I think it has to be GaN on silicon carbide to displace the indium phosphide gallium arsenide materials family. Because the indium phosphide gallium arsenide, even they can go up to sub-terahertz frequency, but in terms of power performance, it's not as good as GaN on silicon carbide. So this is how I think looking forward, and this is what I was talking about GaN, basically GaN going to a 6G application, 2030, where are the frequency bands? So we're talking about sub-terahertz, terahertz band, and where exactly is 140 gigahertz, 73 terahertz, gigahertz, or 300 gigahertz, what kind of transistor we are going to make that is going to open up the market for gallium nitride devices. So this is where GaN beyond 5G, that is what one of the major topic of research interest here in Singapore as well. So now, so this is where I think the talk of my presentation just to start. We are focusing on large wafer area wide bandgap power electronics, so mainly on gallium nitride on silicon, gallium nitride on silicon carbide, and silicon carbide on silicon carbide epitaxial wafer, so that we can produce devices with high production yield and also low cost. And looking into our application, what we are now going to cover is GaN on silicon epitaxy. It will be update what we have done before and what we are working with the foundry to again GaN power devices. Indium aluminated GaN RF application, we did some of the materials development very early. We are redoing this work again to translate this to silicon carbide substrate. Also, we are doing indium aluminum gallium nitride quaternary barrier or aluminum nitride 6 nanometer barrier for this kind of RF test on silicon carbide. And also for a silicon carbide wafer development power electronics is the key, although this is a downstream research in Singapore, but I think for self-reliant mode, this has to be supported well so that we can supply the epitaxial wafer to our foundries here who need at least 200 millimeter wafer for processing in the silicon CMOS line. And what is the outlook for our program also I will try to share so that there will be more collaborative efforts among device makers and also the epitaxial development team. So this is the new group at Form at IMRI. I think we're looking at next 5 years plan. We just formed a new group called Wide Bandgap Semiconductor. And these are all my team members where we are working with 2 of our startups here. Waferlet is a startup that is within the IMRI joint laboratory where we are focusing on silicon carbide development from wafer epitaxy to on-oriented semi-insulating silicon carbide. IGAN is already well known. They are now scaling up with 8-inch reactors here. MOCVD investment has started, so they are going to focus on 1 millimeter GaN on silicon, and also they will provide all kinds of customized substrate to materials development for the material needs. And the team looking at, if you look at our expertise, it is cutting across defects analysis, defect studies, modeling, materials development from bulk to epitaxy. We have a lot of metrology testing tools at IMRE to complement our materials development and also to support our device development team. This is the team of researchers with our waferlet development team led by Dr. Sunil, and I think he's in touch with many silicon carbide foundry as well to co-develop the silicon carbide devices, also helping us to set up the value chain, industry value chain in Singapore. And with this, I think the R&D focus of our group now at this moment, as I mentioned, for GaN and silicon carbide for power electronics, especially looking at GaN on silicon, silicon carbide on silicon carbide. For 6G application from 5G to 6G, GaN on HR silicon. I think now I haven't shared, but some of the research already started GaN on 200 millimeter hard resistive silicon at this from our group. And silicon GaN on silicon carbide electronics also we started in-house, means in-house silicon carbide and then GaN on silicon carbide in country 6-inch development. That will be scaled up to 8-inch within 2 to 3 years time. And diamond and other gallium oxide also we are looking closely, the ultra wide bandgap family. So I think in near future we will focus also on gallium oxide to complement what we are developing on silicon carbide. So here we need a lot of support from the Japanese companies and Japanese agency and experts so that the silicon carbide family will support our ultra wide bandgap platform and we can integrate with diamond and all this as a thermal management discrete device needs. Not focusing much on the gallium silicon diamond at this moment because cost is an issue and scale up is also an issue at this moment. But yes, research will continue. And also all of you might be knowing that yes, majority of our research work is just to share in the public domain very less and 60% of our research data unpublished. But if you have interest to work with us, I think we can share a lot of results from our group and a lot of prototyping work that we do in our laboratories.
So 2 startups are helping at this moment to scale up our activity in Singapore, and I think in near future all other foundries will join and co-develop the GaN and silicon carbide activities in Singapore. And if you look at the key event timeline, I think I can skip because majority of you know that 20 years of research when we were started gallium sapphire, we're focusing on LEDs, producing LEDs on the lab, then into vertical chips, photodetectors, photonic crystal, then we got scaled up funding around 2010 onwards, so that we moved to GaN silicon 8-inch. We developed the IP to start this gallium nitride epi foundry in Singapore. So we translate all our IPs to the company. They did exclusive licensing, and they worked with our NTU for collaboration for prototyping work, and also the Siltrop fab in Malaysia. They also scale up the device process, and they are generating now some kind of revenue, but they're mostly on the pilot scale operation. Now they're moving to, I think, toward 200 millimeter multi-wafer epitaxy in Singapore, and that will help a lot of companies to prototype their GaN hemp needs. And then around 2019, we started this silicon carbide activity in Singapore. But before that, there was no silicon carbide growth activities. The first project that we started at IMRE with collaboration with the sister institute, and then there was a startup launch within the institute. The startup and English joint laboratory developing all this epitaxial bulk and epitaxial growth platform. This is where we will integrate, as I mentioned, to the ultra-wide. So here we would like to focus on how to work with foundries, integrate the GaN and silicon carbide. As a foundry coming up the other side, I think we can also collaborate in future. For the material side, if we look at our gallium nitride development work, so we develop all the buffer control in situ techniques, and most of the results are published very early. If you look at 2012, 2011 time, we started the GaN on 200 millimeter wafer. So today we have all the process development within the institute side, within situ silicon nitride, iron doping, carbon doping. Now we are doing propane induced carbon doping for high breakdown voltage buffer structure. So now we can easily produce 650 volt power HEMT. That is what already in the commercialization stage. So both D and E mode HEMT prototypes are now developed in collaboration with our industry partner as well as in-house work. And also some of the prototyping work, our students and our research staff scaling out on RFM. Basically, they're trying to make short-cut line devices with our university colleagues, and then they can showcase some good performance, RF performances from these wafers. So we collaborate with the NUS team and also the IGAN researchers in this activity. So we have close collaboration with all those researchers within Singapore ecosystem. And just now, so this is the main focus of the talk. If you are talking about GaN on silicon, what are the problems? I think I don't need to tell because you have already explained yesterday. I think most of your presentation was, I think your presentation Devi yesterday was just nice. So if you do gallium nitride on silicon, I think one is a thermal mismatch, lattice mismatch, and how the interfaces are controlled. So the main problem is with aluminum nitride silicon interfaces. So if you make a good aluminum nitride, perfect aluminum nitride, and you can control the defect propagating to our upper layers, I think that is the key for the success. And today I will show you the reverse way, which you may not have seen before. And so what is the issue that if you do a 2-inch and 4-inch level device work and you show it to foundry and they say I have fantastic breakdown voltage in research papers will claim that with a lot of nice results, but what happens when you talk to foundry, they ask, is it on 200 millimeter? Is it on a big wafer? Because as you move from 2 to 4 inch to 200 millimeter or 300 millimeter, the killer defects are many. So the defect density is increasing as the wafer size is going up and up, going up to 200 millimeters. So that's why we need to find a way. So superlattice buffers are now people are trying. And today we are also showing the dual stack superlattices people tried. When they do the dual stack superlattices, they also put aluminum gallium nitride into their transitions. But what we found out that the major problem of the gallium nitride HEMT to the step grade buffer was within these aluminum gallium nitride layers. So most of the trapping and the leakage happens within this term. Why the GaN buffer was always perfect, everything was so nice to so good performance and devices. So if you look at our activity, like from LED, we moved to power transistors and how the Boeing curvature control during the in-situ growth. So they are all optimized. So this process that we develop on GaN on silicon has been now translated to GaN on silicon carbide as well. So how you control these interfaces? Each interface has to cut down the defects and you try to reduce the dislocation to propagate to the channel. So these are the key technique and know-how that is related to the MOCVD. This process was there with us long before, but now we are a little bit changing and tweaking it, because we are the first when we are doing the 200 millimeter LEDs. So if you know LEDs, how broad we can make on 200 millimeter, I think we can do it very well on silicon carbide or any kind of substrate for the gallium nitride epitaxy. So I can skip this one because this is very well known in the past that we can grow 200 millimeter wafer with the low bow and also very high breakdown voltage with a step graded, but the problem was always on the reliability that is happening at these interfaces. So today, what we are going to share, what we are now doing is like typically how to improve those interfaces and also come up with a very nice, smooth hand surface that you do not require in situ silicon nitride as well. So if you can have like 26% aluminum, you can get a very flat RMS 0.1, 0.2 nanometers. So that helps a lot. And so same platform you can grow indium aluminum nitride. And then when we grow, typically superlattice for long period and short period superlattices you can try. So you can do aluminum nitride, aluminum gallium nitride, or you can do aluminum nitride, gallium nitride superlattice. And here, if you can see the contrast, you should know what I have done here. Basically, we have to little bit tweak the transition layer so that you can change the band continuity, the GaN buffer, and the superlattice junction. That will help you to reduce a lot of leakage. So this is how this superlattice stack was used, and then foundry was processing a lot of wafers in the past, and the demode hemp, like typical MISIMP, was already demonstrated. So today you can get 650 volt wafer at your at your design. If you want certain layering to be done, buffer layer, and what kind of tweaking you need us to do, we can do that. So this is typically 600 volt at 1 micron per millimeter, the typical breakdown, vertical breakdown of the wafer, and you can go 800, 900 volt for hard breakdown reaching more than 1000 volt at 1 milliamp per millimeter. And this is typically the process in the MISIMP found with the process on the short 3-terminal devices. So at the LGD of 40 to 50 micron, they're able to get 750 volt, 1 micron per millimeter, typical scaling compliance. So this is now periodically they're doing it, but research has demanded this one. But right now, that research they moved to the P-GaN HAMP epistack. So where we are trying to prototype P-GaN HAMP and the process tweaking in a way that, for example, if you look at the standard HAMP here, the breakdown voltage you can manage with the buffer that you grow. But on the top, when you put P-GaN, there is not much difference with the buffer. But a lot of process, it's a process-related issues, how you passivate the P-GaN and how you can do P-GaN, how you can reduce the P-GaN deactivation. So that is where the challenge was for the process stream, so that they can come out with 800 volt, 800 volt breakdown devices with more than 1.5 volt threshold, 1.5 volt threshold voltage. So this was demonstrated, but I think the problem was always you can start all the process with the L2O3 silicon nitride LPCVD, but LPCVD temperature is higher. So then we give up silicon nitride, we give up L2O3 now. So we said, okay, let's change the whole process now. Look into low temperature deposition of the passivation on P-GaN and solve the major issue at the P-GaN side. Buffer side we can take care by tweaking our architectural structure so that we can go to 1000 volt in future. So this is what the process boundary gave us, all the what you call feedback loop. And now they are going to showcase that yes, now it is possible to purely CMOS boundary-based 200 millimeter wafer with 900 volt devices. So this is something, as I mentioned, sometimes you do not age the P-GaN properly and the thickness is varying, then you end up with the low drain current because of the excess resistance is high. But now periodically, if you improve the process, you can come up with 310 to the power 19 P-GaN doping with 120 to 130 or 100 nanometer on top, and then you can create P-GaN EMO devices that is so that will show you a low RDS. So right now RDS1 was a big challenge for dynamic RDS1, but gradually the things have improved now on the process side. But one beautiful thing is that in the P-GaN HAMP, what we did, the tweaking of the superlattice structures, what you do, then you can always see a breakdown voltage, very high vertical breakdown voltage, but then you end up with a very low, slightly lower vertical breakdown voltage at 1 micron per millimeter square, but you end up with a lateral device with the P-GaN HAMP normally off, even at more than 1.5 volt threshold voltage, 900 volt HAMP devices. So this is now something like what we are calling, we are now at the 900 volt E-mode HAMP demonstration. So reliability is already improved. And now our plan how to tweak the threshold voltage further to 2 volt, because that's depending on our P-GaN activation. So what temperature we do this P-GaN activation in the MOCVD chamber or in situ, how we process the passivation. So that's the two things we need to work together, and then we can go to 2.2, 2.5 volt. That is what previously achieved. So that's a little bit of process tweaking going on. If you look at the buffer tweaking, this is a typical pig and ham that is with all the field plate and all our process line with CMOS that is shown from a foundry side. So what we tweak here, this is super lattice. So we remove all the Algen buffer layer. Now you see what is there. It's a GAN buffer. You can put even little bit of aluminum inside after tweaking, and this is the typical dual layer super lattice. So people started to make Algen transition layer, make a super lattice buffer, put a GAN, then you go another super lattice, then you put the GAN in channel. Despite the defective, you can still get 900 volt devices. This is where the aluminum nitride to Algen transistors are removed and the very thin layers of lattices have grown. Two types of super lattices have grown in a way that you can get LGD 15 micron 900 volt devices. So this is how the two typical razor. This is super lattice structure 1 and super lattice structure 2. We are talking about 2 nanometer aluminum nitride here. With the gallium nitride of 4 to 5 nanometer with the first layer, and the second we are just doing standard 25 nanometer kind of super lattice. So there are two types of super lattice that helping us. So this is reducing our buffer breakdown, so we can further improve the by doing some kind of transitioning here, so that we feed that form of the aluminum nitride, the first super lattice period. That is where the tricky part here. So this one we can keep a little bit higher, or what we should do now, so that we can go to 1200 volt easily. So that's all the story within the aluminum nitride in the first layer transition. This is what we are focusing at this moment. And then this is the key to go forward for the remote devices. And this is some of the results for the, if you want to know what the contact and all this aluminum TIN type of standard CMOS boundary contact. So periodically they have optimized all those layers so that they can come out with a nice vegan stack with the metal stack that is showing a very low leakage. At the same time, we can do very nice ohmic and typical aluminum TIN field plate structure, so that you can go to ohmic and all this. So this is typically our fundamental studies that we do tweak for the field analysis. So how much is the etching of the pigment remainder? So we can go to 15 micron depth here. So the Algen is 15 nanometers. So the 15 nanometer removal of Algen is very crucial. The control of the edge depth is much important, and also the profile. So if the profile is sharp, then it's much better. And what is the angle of the profile where you put the ohmic contact? So these are little bit of thing that we are now trying to resolve, so that the foundry can produce high voltage 900 volt mode with high reliability. So this one I can say, yeah, I have less time, right?
You have 5 minutes left.
Okay,
no, you have 5 minutes.
Yeah. So stress-induced morphology we started. Just I want to share with you the beyond 5G we are doing HR silicon growth. So I can skip that part because that's not much important. And indium aluminum nitride also I can skip. Those are information available. And if you need to discuss with me, I can provide all this what we are doing recently on the indium aluminum nitride on high resistive silicon. This is basically transferring the process with the INGAN back barrier from silicon to silicon carbide now. So this research is now ongoing. Okay, now the silicon carbide, I can focus 5 minutes. So what we are doing now, we are combining bulk growth to process tuning.
Sudhir Ranjan, can I interrupt you for 1 minute? We have 4 minutes to 30 minutes. So maybe if you can wrap up in 2 minutes, we'll have 2 minutes for questions at least.
Okay. So the wide bandgap silicon carbide that what we are developing now is a 150 to 200 millimeter substrate. There's a bulk growth with resistive heating and as well as RF heating. The silicon carbide epitaxy is also hot wall CVD that you can go up to 725 degrees centigrade. So this is our ongoing effort on the bulk and the epitaxial wafer. Defect science I can improve, so we can discuss that later, but we have done a lot of downstream research, how we can control the defects and how we can come out with a nice surface for epitaxy silicon carbide N type. So from N type, we will move to semi-insulating, but it should be much smooth, like for 0.1 nanometer for the silicon surface and less than 3.3 nanometer for the carbon surface. So this is how we do. So standard wafer, if you buy from the market epitaxial wafer, the defects looks like triangle, diagonal, all these large speed defects that you can see. But if you do in-depth study with the laser, you will find out, oh, these defects are different. They're already starting force in the layer. So when the foundry are supplying the material, they just do a Sika imaging, but you need to do your own imaging to know what exactly those defects are. When you make devices, you can isolate and you can tweak your process. But this happens because the temperature was not very good or growth was not very uniform. But what we have developed now in our lab is the 200 millimeter, 150 millimeter epitaxial system that can go very high temperature. This is where we are producing state of the art now. So now that system can demonstrate about less than 0.5 in the thickness uniformity and less than 1% thickness uniformity 32 micron stack, and this is 16 micron stack for 1700 volt, and this is for 3.3 kV application. So this is how we are trying to optimize so that we reduce the surface defect density less than 0.1 centimeter in future. So this is how our plan to move to the architectural development, and there are a lot of work also going on the silicon carbide MOSFET, silicon dioxide, silicon carbide interface, so how we do the silicization and how we can control the gate. So we do a lot of TM studies to reduce the defect, the interface, and how the room temperature implantation regrowth is done, and what kind of defect it forms, what it has implication in the device process. We have to work together in future with the device design team. So I think all the silicon carbide, silicon carbide MOSFET related work, this will be more closely, we will work with the foundries and try to resolve all our analysis for the MOSFET. So this is the last slide where we are going to share with you that what the platform that we are now talking here, that silicon carbide for 3 different applications: silicon carbide and silicon carbide MOSFET for high voltage, silicon carbide on oriented, and also the carbon phase highly CMP for GaN on silicon carbide beyond 5G, silicon carbide p-type development for long term, and also N-type for other research to integrate the ultra wide bandgap material family. So this is our typical focus, and if you want to share, this is the typical gallium nitride power electronics roadmap that we are talking at this moment. GaN on GaN, this is for academic research. GaN on silicon, it will be mostly led by the industry because the maturity of GaN on silicon process now, so moving from 600 to 1200 volt. GaN on GaN is looking at the high voltage devices, 100 ampere current, but if you're talking about more than 100 ampere current, it will be silicon carbide. And the GaN on silicon carbide for beyond 5G. So these are the typical what we call 5 years roadmap plan that we did. And with this, I would like to end my talk. I can take questions.
Okay, thank you, Sudhir Ranjan, as usual, for a fantastic overview. We have time for 2 questions. Okay, if there are no questions from the audience, Sudhir Ranjan, maybe I can get started. For your really thick GaN on silicon 8-inch wafers, where you grow these thick epi stacks, what is the thickness of the silicon you are using now? Is it still 1 to 1.2 mm or is it thicker?
725 micrometer E-mode, the MISM to 725 micrometer. Superlattice buffer you can use up to 5.2, 5.3 micron stack. And 1 millimeter if you use, you can use 5.6 micron stack. Dual superlattice. 1 millimeter. So standard wafers are 1 millimeter for 900 volt devices that I showed you here. 111 silicon, and 725 D mode. If you want to cascade all kinds of integration, is available at 725 micrometer, but single stack. Okay, that's a single stack. So some of the new growth has started. So the 200 millimeter wafer is multi-wafer tool. They have started now looking into 725 micrometer solution. So I do not know 1000 volt, 1 millimeter or 725 in the end, but I'm more comfortable with 1 millimeter. Silicon. So
hello, Vasu. Can I ask a question? Ashok
yes,
Kapoor?
Please go ahead.
Yeah, Sudhir Ranjan, I want to know what is the key parameter in controlling resistivity in the bulk silicon carbide growth?
Bulk resistivity, N-type, we are doing the N-type growth. N-type, you have the nitrogen flow control, very nice. You are talking, do you want to know about the semi-insulating?
Yes, semi-insulating.
Yeah, semi-insulating, what we are doing, we are buying the high purity powder. First, we started with vanadium and we prepare the vanadium drop powder. So I think the vanadium drop silicon carbide, the raw material will reach to some of your colleagues, maybe if they are interested to start looking into those qualification of the powder for semi-insulating. And then
yes,
you can get, yeah, the vanadium dope, one will give you 10 to the 5, much easier. If you do high purity, it looks like high purity silicon carbide, but we found out when we do iron doping in the GaN buffer, we also found out reliability issues. So I am not sure, but Cree has its own patent and all the know-how to produce. But we are right now, we are using vanadium dope. We started not N-type, very high resistive powder, and we are mixing it to make our semi-insulating. For N-type, it is just and you flow very high argon. Huh? For the semi-insulating one, you have to control with the argon flow in the chamber. So our chambers are 8-inch and 6-inch. And so what we are doing, we are trying to put a smaller crucible for 4-inch development if there is a requirement. But then we decided for semi-insulating better to do 6-inch and cut to 4-inch and give it to whoever wanted to pilot test. But you need to flow very high argon in the semi-insulating chamber and use a high purification, high nitrogen purifier before the nitrogen enters to your chamber for N-type doping.
Okay.
Good.
That's a very good suggestion. Thank you very much.
Yeah, thank you.
We have Arnab, if you want 1 minute, you can ask your question.
Yes. Sudhi, thanks for the overview. Very
Thank you.
good question. When you put 3 into 19 or 2 into 19 magnesium, does it impact your surface morphology? I mean, you have brilliant surfaces on Algan.
You saw the surface, right? You saw the diffusion of the metal, right? This is state of the art at this moment. I go back to you see the TM get stack, right? We has a 120 nanometer, it's 130 nanometer, but let's go back. You can see the control here, huh? Okay. So do you see any problem? What you see is the dislocations only, right? This is from TEM.
Yeah,
Okay.
I'm just looking at the surface morphology. I mean, if you say it's great, it's great. I believe you, no problem.
Smooth, very smooth, ultra smooth, and you can see the TIM formation here. Nice transition, huh?
Okay.
Okay. So
Stop there.
Yeah. So
I apologize. Yeah.
pitting is not an effect, huh? Pitting is not there much. So the typically PGAN, when you grow LED, right? When you put the P plus layer, you see a lot of the pitting of the PGAN surface. But that one is controlled because your GAN buffer, GAN channel is very good, and we don't have any quantum well. So when you have quantum wells and you grow your PGAN and P plus GAN, then you have problem. Okay, in the PGAN surface. But this is even you can put very high doping, you don't see any problem.
Okay, thanks. Thanks.
And this works well, and 3 10 to the power 19 is helping us to get 2 volt plus threshold voltage.
Okay, great.
And you don't anneal inside your in situ chamber very high. Huh? Suppose you are doing LED and you grow at 980, 960, and then you start to reduce it to say 800, 790 or 820, 30, right? So the temperature is very crucial to control the morphology of the peak and ham surface. That is also a emulsivity play. Okay, it's a growth play.
Sudhi, I hate to do it, but we have to call timeout here.
Thank you.
Okay. So without much further delay in time, the next speaker is Professor Arnab Bhattacharya from TIFR in Bombay. He also needs no introduction to this community. And with that, Arnab, it's over to you.
Yeah, just waiting. Okay, can you see my screen?
Not yet. Okay, now it's there. Go ahead.
Okay, I cannot see myself, but that's okay. I guess it doesn't matter. So thank you very much for this unique opportunity to present a talk online. And, it's been fascinating to hear some of these presentations. I must really say one of the biggest advantages, even though I've not been able to catch up on it in real time, I've been able to watch it, later, which is really nice. I was almost not going to give this talk. I was trying to convince Rajendra that could I drop out, but then he insisted that no, whatever we have, we should. And the reality of it is the work that we've been doing on both growth of gallium oxide as well as growing MOVP gallium nitride on top of it has been sort of completely on pause since March because our labs were all shut down. And there is really very little that is going to be new, though there are some new things that I will definitely talk about. Now, the good thing, of course, is that being a crystal grower, we are very used to dealing with heating stuff. And in particular, things like temperature gradients, temperature uniformity, that's part of life. It's usually been temperature gradients for gallium nitride or other materials. But in the last 6 months, I'm really happy to say that our lab members have transitioned. We've been heating not gallium nitride, but N95 masks. And we've actually set up 2 systems at Tata Memorial Hospital, et cetera, et cetera. So it's been a very different life over the last 6 months. And I'm glad that I have a chance to go back and talk about gallium oxide and gallium nitride for a change. So, we've seen, of course, Sudhi gave a talk on gallium nitride, but even gallium oxide, I'm hoping Masataka after me will probably give us the latest that's happening on the gallium oxide front, and then we'll see the results from Roper on photonics, etc. So I'm very, very happy to see this. There's also been a lot of work on gallium nitride on gallium oxide, and so the main reason that we got into gallium oxide from a growth perspective, though the material seems to be a very sort of crazy material that people don't know if it is whether it's you see band edge luminescence or not. People haven't got it p-type. There are serious problems, but still, from the perspective of crystal growth, it's really a fascinating material, simply because it is the rare high band gap material that can be grown from a melt. I mean, typically you have large crystals available of silicon, gallium arsenide, etc., which are low band gap. And if you go to silicon carbide, you just saw Sudhi's work that you don't really get very big crystals there. But gallium oxide is one thing which you can grow from the melt. From, of course, making large diameter substrates is always a challenge, but it's not that difficult to grow. So we thought we should dive into this and try and see what we get, and that's how it started. So of course we started our work with flux growth, and though most people know that we do optical floating zone growth for the most part, it is true that probably haven't even shown this earlier. We actually tried to do a good bit of flux growth work on gallium oxide. You can get the melting point of gallium oxide down from its value around 1800 to something which is still very high, 1400, but still 1400 is a lot more tractable than 1800. Unfortunately, you require mixtures of lead oxide and lead fluoride. That seems to be the material that works best as a flux. And if you just heat it up, melt it, cool it slowly, you can actually get reasonable crystals. The crystal quality is very good, except that these crystals are, gallium oxide is a monoclinic system, and these crystals are thin needle-like crystals, which are really not very useful for the typical semiconductor work where you would like to make substrates or have something which is a large diameter crystal. So we abandoned flux growth pretty soon and moved over to optical floating zone growth. This is a system where we have a two rods which can be melted using focused light from 4 halogen lamps. We have 4 1 kilowatt lamps that can be focused. It melts a small region. You put a seed crystal, and then you slowly pull the melt down and allow the feed rod to sort of melt and recrystallize. And depending on the parameters that you tweak while doing this, you can have a lot of control on the growth. It's surprising that the handles you have in such a system. This has been around for a while. There is, of course, no comparison with the problem with the floating zone is it's easy to get something like a centimeter or maybe even 2 centimeters, but pushing it to a wider, larger diameter would be difficult because of the inherent nature that you're trying to focus the light at a point, and it's not easy to get it uniformly. You can defocus and try, but then you need a lot more power. So for starting off research, it was very nice. We started with this. This is a picture of our system where we do, and you notice on the left side, what you see is a very clean glass rod. It doesn't remain that way depending on how you play with the parameters, as I'll show you in a bit. And we actually had to learn a lot of things. I mean, once you start this, even how to make a decent seed rod, how do you pack a powder? You start off with a gallium oxide powder. If you want to add dopants, you will add dopants to it. How do you just make sure that when you evacuate this and try and sinter it and densify it, it's not going to crack? I mean, it took us a long time to figure this out, and it took us a long time. I've spoken about this earlier at conferences, so I'll skip all this. Our entire optimization process from starting off till we could get long transparent crystals, and these crystals can then be cleaved to give us about 1 centimeter diameter wafers. These just hand cleaved with a scalpel. So they're about 500 microns thick. That's about the thinnest we can cut reliably. And these are what we use for the growth, MOVP growth. Now, the crystals that we've grown are all 100 oriented. They are pretty high quality. we can get very narrow half widths, rocking curve widths, etc. Sometimes we do see twin defects and things like this, but usually these crystals are high quality. Now, one of the biggest challenges is to try and optimize the background carrier concentration and get long crystals. So the idea is, if you of course put oxygen in the environment, you will suppress the formation, the decomposition of the gallium oxide. There are less bubbles. You get less free carriers because you don't have oxygen vacancies. You get nice transparent crystals. If you mix it with argon, or if you use air or something like that, you can play with the oxygen carrier concentration, but then you also have the problem that a lot of gallium oxide powder gets deposited on your tube, as you see, and you cannot grow long crystals this way. So it's a trade-off, and intrinsic doping is a problem. Of course, you can do it by playing with the background gas, depending on air. The red box out here, you can, or if you play with 100% argon, you can get these bluish crystals, which are sort of highly doped, or you can get transparent crystals. In oxygen also, you will get a nice flat thing. You don't have free carrier absorption in the infrared. So you can play with this with the background doping. Now, can you controllably dope it? And this is where we started saying, how much can we tweak this process? And you can, of course, make very drastic changes. So a drastic difference is like if you put a very tiny amount of hydrogen. If you put a very tiny amount of hydrogen, this sort of literally scavenges any oxygen that is there. It is very difficult to grow long crystals because the material is decomposing a lot. But you get very highly, they're almost, this thing which looks black from the side is actually a very deep blue. There are deep blue crystals, and we've actually seen some very interesting Raman structure in this, which we do not understand as yet, some new Raman modes, which nobody seems to have seen. But this is, again, not a reliable method of growing long and doped crystals. So currently we are working on trying to introduce silicon and other transition metals into these gallium oxide, into the melt, so we can try and get doped crystals. Now, doping in float zone is also not an easy thing, because you remember float zone, you use float zone refining to purify silicon. It's like a zone refining process where the dopants will move away. But here you want to incorporate the dopant. So you have to be sort of careful on how you grow it. We have made recently some silicon crystals doped with silicon dioxide. These are, of course, light bluish. Hall measurements give us a value of somewhere in the low 10 to the 18s per centimeter squared. But then you can have, these are the silicon crystals. What we are trying right now is to put some magnetic elements into it, both F block as well as D block transition metals. So we've tried with things like cerium, gadolinium. Also, you can put vanadium and chromium. And just an example, I mean, it's the same amount of gallium oxide, the same amount of vanadium oxide and chromium oxide, but the rods look very different, just because when you try and make these rods, just the process, this is not even melting it, just making the rods, densifying the rods, you have a different, the oxides have different volatility. They sort of, they evaporate at different rates, and it's not a very easy thing to control it. So we are still learning, but we will figure it out. The other thing is, once you have these dopants, the same conditions that you would use to melt your rod seem to change significantly. So both the, right from the rod formation to the melting to the growth of the crystal, I think every time we change the parameters, we would have to do some amount of optimization in this. So this is what we've tried on the growth front. And the other thing which we've been doing in the past couple of weeks since we started up our labs is, one of the big reasons for gallium oxide was it's good for high power devices, and high power devices would operate at high temperature. And the last time I was at IWGO, there was a lot of sort of informal chat saying that people do see degradation at high temperatures, particularly in some orientations, etc. And there has really not been a lot of work on high temperature, or at least not a lot of published work on high temperature characterization of gallium oxide. And over the last year, we actually got a hot stage for our Rigaku XRD system, which can go up to about 800 degrees. And we decided we would start with just trying to understand and measure X-ray scans at high temperature. Now, this turned out to be a little bit more challenging than we thought, because unlike the goniometer that you use at room temperature, where you can optimize in many different axes, tilt and psi and everything else, these hot stages don't really allow you too many options to optimize your, you can move omega, omega 2 theta, but not, there's very little room you have to play with when things tend to, if they shift a little bit. So getting these peaks optimized has been very tricky. And here we started with the Tamura's 2bar01 substrates, because they are probably the best. And again, we are trying to see what happens to this is omega 2 theta scans, where we can see a clear shift, which is expected. As you heat it up, your unit cell is deforming, your peak position will change. This is what we see when we look at the 2bar01 all the way to 8bar04, the things, and we are trying to figure out from this, what can we say about the material, and also if the FWHM changes are significant or not. The omega scans are much more trickier, because the omega scans obviously are not, as the position means very little. I could zero them all in the same thing, but we do see some strange changes in the peak widths, which we do not understand as of now, I'll be very honest. And this is just straight screen grabs from Rigaku software, so it's not even very, it's work done over the last couple of weeks. So, but this, I think, has an interesting story. We're going to compare our own material with this as well and see what we can take away from this. So that's as much as the gallium oxide work has been. In terms of the growth of gallium nitride on gallium oxide, my last student, Emroj, he spent a lot of time optimizing the growth of gallium nitride on gallium oxide. We cleave our gallium oxide rods and use them as substrates. Without any polishing or cleaning, they're just locally smooth enough for growth. And by playing around with conditions, we found that the best results we get are by a 3-step growth process using a low temperature gallium nitride layer, and followed by what we call a facet layer, which sort of helps in seeding the growth of gallium nitride, which is faceted, and then you can cover it up with a high temperature layer. And of course, we do not nitride the surface. We start off with direct growth in nitrogen. Now, this is probably been, if you've seen any talk from our group, you've seen this before. So, but just to give you a flavor for the kind of work we are doing, we have played around with the whole parameter space in an effort to optimize the material. So, for example, if you look at this diagonal going from the bottom to the top surface here is a direct growth. The bottom one here is 2-step growth, and clearly in the middle, this was the optimized 3-step growth. So 3-step growth is important. We've played around with the thickness, for example, of the low temperature layer, and there is a certain, very thin is not good, very thick is not good. There is a sweet spot in the middle for the thickness of the low temperature layer. The growth time of the facet layer as well. If you grow it for too short, you don't start off with everything. If you grow for too long, it's not good again. Again, there is a certain minimum, an optimum time at which you get this is in morphology. We can see the same thing in X-ray FWHMs as well. And we've played with the temperature again. It seems the hotter the better, so around 1040 is where we get the best results. So we can actually get reasonable gallium nitride on gallium oxide. In an AFM, you will see atomic steps on it. You'll see step flow growth. But is this good enough, right? And yeah, you see the same thing, as I said, this thing you saw with the in the morphology. You see a very, very similar trend if you look at the X-ray half-widths of the various things. So, for example, it shows you that there is a certain optimum in terms of the LT-GaN thickness. There is the higher the temperature, the better it is for your facet layer, and there is a certain optimum in thickness in terms of your facet layer growth as well. Now, even in spite of all this, the quality on gallium nitride is still not as good as that on sapphire. So it's probably as good as what other people get on 100 gallium oxide, but still it's a factor 2 to 3. I mean, on gallium, on sapphire, we are always below, 250 arc seconds typically in both symmetric and asymmetric scans, but here it's almost 600 to 700 arc seconds. And one thing which we wanted to understand, and this is probably some stuff which we haven't shown before, is the in-plane orientation and what happens at the interface. So gallium oxide is monoclinic, so that's how the unit cell would look. Gallium nitride is hexagonal. And what happens when I'm going to put this on top? Is there going to be a twist? How is it going to line up? And what we do is we look at compare the gallium oxide 710 with the gallium nitride 103. These come at similar angles. So you can do a phi scan. And based on this, you can see the gallium oxide peaks as well as the 6-fold peaks due to the gallium nitride. And at the end of it, we turn out that the orientation is such that the C-axis of the gallium oxide is oriented along the M of the gallium nitride. So this is something we figured out. Now, one thing in the field has been that, look, there is a strain. And some of the earlier groups, Viora, etc., which were the initial people on 100, who had, of course, used nitridation. So there is a difference. Their samples are nitrided, said that there is a tilt between the epilayer and the substrate. And we've actually tried to do some TEM and diffraction analysis of the interface region between gallium nitride and gallium oxide. We do not see any tilt between epilayer and substrate. However, in this process, we actually saw some very interesting defect structures in our material. So this is, we see a lot of VPITs on the gallium nitride. And if you look below that, these seem to all originate from little air gaps at the interface. And we see these air gaps across the sample. And the question is, is there something happening where these air gaps actually act like a nano mask, helping us to actually grow the gallium nitride? And we've also done some analysis of the interface region between the gallium oxide and the gallium nitride. At the interface, there is about a 10 nanometer region, which is extremely defective and has these 6. Yes, I will
5
end
minutes.
yeah, don't worry.
Yeah,
I'm almost near the end. I have a timer. There are these 60-degree dislocations that you can see over here, which are in this very, very defective 10 nanometer layer. And then this is your LT GAN, and above the LT GAN, the facet GAN layer has some of these dislocation loops that you see, and it's progressively improves. So clearly, a lot of the dislocations are getting bent in this facet layer. So yeah, so I will keep the 5 minutes for questions. So our summary so far has been that we've been doing optical floating zone growth, mainly a little bit of flux, but mostly optical floating zone growth of beta gallium oxide. We can get, when conditions are good, 10 centimeters long, 1 centimeter diameter single crystals of high quality. If conditions are not good, you will not get the 10 centimeter long. It's difficult to continue the growth. You get much shorter crystals. You get a few, maybe 1 centimeter or few centimeters only. One of the biggest parameters that controls this OFZ growth is your gas ambient, and it is hugely critical. The flow of the gas, the composition of the gas, everything seems to matter on the crystal growth. We are currently starting with doping it both with silicon and tin, as well as with cerium, vanadium, chromium, etc. Hoping to see if we can get, the ideal thing is we would like to see if we can get a magnetic response from this. If you need to make a dilute magnetic semiconductor that works at room temperature, ideally you want a wide band gap material. Nothing really seems to have worked very much, but let's see if we can find something and then again show whether it's actually in the lattice or just clusters. So we'd work on this because the good thing about TFR is we have people who are very strong in magnetism and can make the appropriate measurements. In the MOVP growth of GaN on gallium oxide, we've been looking at this facet GaN grown, 3-step growth with a facet layer. However, we are still not at the level of GaN on sapphire and would require a bit more of optimization to improve the quality further. So I'm going to stop here, and I'm happy to take questions about our work.
Thank you, Arnab, for getting all of this done in spite of your work at the COVID front. The talk is open for questions. Okay, so let me get this started like I did at the last session. So might be a naive question, Arnav, but what is your interest apart from the crystal growth aspects of it to look at growth of GaN on gallium oxide? Other than, let's say, what device aspects are you interested in?
So, I mean, the idea for doing GaN on gallium oxide was to use the fact that gallium oxide is a conducting substrate and hence make vertical devices, right? So that was the aim. Anything you can make either a vertical LED or a vertical, any device which has a vertical geometry. You're not on Sapphire, you're always limited to making both contacts from top. But I think to get there, you require a sufficiently high quality, which we have not reached as yet. So we haven't really thought about making devices so far. We did try to grow an Indian gallium nitride layer just to check whether we get luminescence from it, but we haven't made devices from it as yet.
I see.
But vertical devices is the answer.
Vertical devices, okay. And I kind of missed a little bit, but so the GaN grows on the gallium oxide with the C plane of GaN parallel to your perpendicular to your substrate. I'm sorry, the C plane of GaN parallel to your substrate.
Yes. So it is C GaN on 100 gallium oxide.
Interesting.
C GaN on 100 gallium oxide.
Right. Because when you were showing the cartoon, of course, you say GaN is hexagonal and gallium oxide is monoclinic, but it's hexagonal only if you're looking at the basal plane.
Yeah. Sorry, I should have mentioned it. No, it is C GaN on gallium oxide.
I see. Okay. All right. Any more questions for Arnav? Okay. If there are no more questions, let's move on to the next speaker. Again, just like the previous two, the next speaker needs no introduction. We have Masataka Higashiwaki, who will be telling us about his latest in the field of gallium oxide. And as we all know, he's among the leaders in the world in this area. Masataka, it's over to you.
Okay, so can you hear me?
Yes, we can hear you.
Okay.
I can hear you and I can see your slide. Please go ahead.
Okay. Good afternoon, ladies and gentlemen. My name is Masataka Higashi from NICT Japan. So first of all, I'd like to thank the organizers and the committee, broad committee of this workshop for giving me this opportunity. Thank you very much. So today, I'd like to talk about high-frequency gallium oxide FETs for the harsh environment electronics applications. So this shows the outline of my talk today. First, I'd like to introduce the material properties of gallium oxide briefly, and mainly for the power switching devices, and also additionally, and then I'd like to mention the motivation of the development of high-frequency gallium oxide transistors. So as you know, gallium oxide has a very large band gap. Therefore, it's basically strong against some stresses such as caused by the temperature and also radiation. Especially that we are focusing on the radiation hardness. This time, and then the first, and I'd like to show our previous work on radiation resistance of the lateral gallium oxide MOSFETs. We use the gamma ray irradiation in this case. And then I will move on to the main topic of this talk, highly scaled gallium oxide MOSFETs for high-frequency applications. Device structure and the DC device characteristics, and also the RF small signal characteristics, and delay time analysis. And then I conclude my talk towards the end. So, previous speaker, and then already mentioned that some of the material properties of the gallium oxide. Therefore, I'd like to introduce them briefly. So, gallium oxide, as you know, and it has 5 types of polymorphs, could be 6, including the copper phase and recently found. But anyways, most stable polymorph is a beta gallium oxide, corresponding to the monoclinic beta gallium structure as shown here. So melt-grown box only available for the beta gallium oxide because this is the most stable phase, and the other phases are metastable structures. Therefore, our work is just focusing on the beta gallium oxide right now. So this material has unique and also the interesting and the properties. First of all, and of course, and it's extremely large band gap. So beta gallium oxide has a band gap energy of 4.5 eV. It's of course and much larger than those of silicon carbide and gallium nitride. And also we can control the electron density by the impurity doping. So we've already succeeded in controlling the electron densities from 10 to the 15 to the 10 to the 19th, correspond to the resistivity of 10 to the minus to the 10 to the 12th. So these are the strong and also the appealing points. But this material has serious and two drawbacks. First, and there has been no report on P-type gallium oxide with effective Hall conductivity. I mean, confirmed by the Hall measurement. And also, it's an oxide material, therefore it has a very poor thermal conductivity. Therefore, the main direction of the development is that how to use these strong points and how to cover the drawbacks. So this is the main direction of the development, any type of the gallium oxide devices. So what I'm showing here are the comparisons of material properties between beta gallium oxide and major semiconductors. So as I talked, gallium oxide has a 4.5 eV band gap. It's much larger than those of silicon carbide and gallium nitride. And room temperature mobility, it's relatively low. It's probably up to 200 square centimeter per Bose sec. But the breakdown electric field, this is the main appealing point of this material. It should be very large, at least and larger than 7 or 8 megavolt per centimeter. And also the direct constant, it's 10, experimentally confirmed. Therefore, by using these three parameters, we can calculate the Barker's field merit. It's at least over 1500. So as you see, this value is much larger than those of silicon carbide and gallium nitride. And also, as I mentioned, gallium oxide has the poor thermal conductivity. It's just 0.27 watt per centimeter Kelvin. So this value is about one tenth of those of silicon carbide and gallium nitride. And also, as you know, beta gallium oxide has another and important material feature. So we have a bulk from melt. So we can use any type of the metal growth methods such as Chokrovsky floating zone and EFG. So this is a schematic of the EFG apparatus. It's very simple. We put the gallium oxide powder source into the crucible and heat it and melt it. And if we put the die with a narrow slit, so molten gallium oxide comes out of the slit, and due to the capillary effect, therefore, if we put the seed crystal onto it and then pull it, and we can get plate-shaped bulk crystals. So novel crystal technology, so this is the main vendor of the gallium oxide and we have right now, and they've already succeeded in producing the 6-inch diameter gallium oxide wafers by using the EFG box. And then the material qualities are really good and at least and enough good for the development of vertical transistors and diodes as shown here. Okay, let me briefly summarize the appealing points of gallium oxide power devices. First, and we can expect the excellent device characteristics from the material properties. And we have a bulk, therefore, especially suitable for the vertical transistor and then the diode applications. And also, as I introduced, we can have a melt. We can have a bulk from melt. Therefore, we can expect a simple, low-cost wafer production. So it's very important because in case of the vertical transistor diodes, more than half of the production cost is occupied by the wafer. Therefore, if we reduce it, and then I think we can install the gallium oxide devices with a low cost into the market. Therefore, these two appealing points. So now the gallium oxide has been getting much attention from the compound semiconductor communities. And then of course, and the power switching device is the main topic for the gallium oxide, but I like to propose another application. It's a harsh environment and electronics. So gallium oxide, as I talked, it has a very large band gap. Therefore, we can expect a stable device operation even at a high temperature and also the strong against radiation. So there are some typical applications. For example, the space and also the underground resources survey and also the nuclear plants. But as all of them, I think the gallium oxide devices should be very useful and suitable for this kind of application. So that's our main motivation to develop the high frequency gallium oxide transistors. So today, I'd like to introduce our primitive works on development of high frequency gallium oxide MOSFETs, mainly for the RF or logic application. Okay, before going into the RF devices, first, and I'd like to show our previous works. It's a radiation resistance of the gallium oxide MOSFETs against gamma ray irradiation. So we performed the gamma ray irradiation experiments. We used the cobalt-60 gamma ray source, and then we put a sample into this box, and it's filled with a nitrogen gas, and irradiated the gamma ray from the cobalt-60. And we increased the cumulative absorbed doses and step by step from 10 to the 1600 kilogray. 1600 kilogray corresponds to the 1.6 megagray. And also during the exposure, and we didn't apply any bias to the device. We just installed the device chip here and expose the gamma ray. And then after the exposure, we took the devices from the box and then observed the device characteristics outside of this kind of facility. And then we perform, and this is a typical, and then the data to show the radiation resistance of the gallium oxide MOSFETs. So up to the 500 kilogray, as you see, there is no degradation on the current characteristics. And even after the maximum and then the exposure of 1.6 megagray, as you see, and then we got a very small reduction of the on current, and also the devices are still and then operational. So, and 1.6 megagray is enough good and high dose and for the space applications, and also it's also okay level and for the nuclear reactor applications. Therefore, from these results, and then we confirmed that the gallium oxide MOSFETs are very suitable and strong against radiation stress. And then I like to compare the result with the silicon carbide data. So, this is a silicon carbide and the data for the MOSFETs and also the MESFETs. So as you see, and the MESFETs and provided a better performance than the MOSFET because gamma ray tolerance and basically limited by oxide dielectric. This means a gate dielectric or gate dielectric silicon carbide interfaces. It's not determined by the degradation of the silicon carbide itself. And I think it's the same to gallium oxide MOSFETs. Therefore, of course, and the gallium oxide is very strong against radiation, but we need to improve the quality of the gate directly more, especially for the normally operation. Therefore, I think that we have a same and then the task and as the silicon carbide MOSFETs, even for the gallium oxide MOSFETs. But anyway, the gallium oxide should be very strong against radiation stress. And then I'll move on to the main topic, highly scaled gallium oxide MOSFET. So basically, we developed these kind of devices for the large hard electronics. And then this is epitaxial growth and then conditions. We use the MB machine and the plasma MB, and then we glue the very simple and epitaxial structure on top of the ion dose semi-insulating gallium oxide 010 substrate. So we just glue the non-dope and gallium oxide and with a thickness of 200 nanometer by using the RF plasma MBE. So plasma power was 250 watt and the flow rate was 2.0 SCCM. And here we used the 010 substrate and bonded onto a silicon carrier wafer for the growth. And the growth temperature was 630 degrees C. It's measured by a pyrometer. And the growth rate was 0.3 micron per hour, and the thickness, as I showed, and 200 nanometers. And then we fabricated this kind of structure. It's a schematic cross-section of the device structure we fabricated. So we performed a 2-time and silicon implantation to make once for channel and once for ohmic regions. And then the channel region, and then it's a box profile with a thickness of the 17 nanometer, and then the average density of silicon was 4.8 times 10 to the 18th. And the omic region and the same 17 nanometers deep, and also the 5E19th. And we performed the activation annealing for both of the regions at the same time at 925 degrees C. And the source and drain electrodes were made of titanium, gold, and metal stack. And then after the metallization, we performed the RTA process to improve the omic properties. And also the gate direct electrode was a titanium, platinum, gold metal stack. And the gate direct film was LED aluminum oxide with a thickness of 20 nanometers. So this is a DC IDVD output characteristics. As you see, we got a beautiful and then the IDVD characteristics. We got a perfect and control of the drain current by the gate bias sink. And ID max was about 300 milliampere per millimeter at the gate bias of plus 4 volt. And also that we got a good offstate and characteristics. We got ID pinch off. And also the transfer characteristics. So Gmax was about 17 millisiemens per millimeter. So this is the reasonable value for the material properties and the device structure. And if you see the IDVG characteristics, we got a very small leakage, but it's acceptable for the, this kind of high frequency and applications. Okay, this is the main data, RF small signal characteristics. This is the data for the gate devices with a gate length of 200 nanometers, but we got a FT of 9 gigahertz and Fmax of 27 gigahertz. So these are excellent data for the gallium oxide devices, especially the Fmax. It's a new record for the gallium oxide FETs, 27 gigahertz. So from these results, and then so we can expect and then the gallium oxide devices can be used for the applications at a frequency up to and almost the 10 gigahertz. Therefore, it's a very suitable, useful for the normal wireless communications and also some of the logic circuits. Okay, and if you see more specific data of the RF small signal characteristics, these are the gate length dependencies of the FT and the Fmax. So as you see, FT increases with decreasing gate length down to about 200 nanometers, and then saturates. So on the other hand, in case of the Fmax, also the decreases with decreasing gate increases with decreasing gate length and up to down to about 200 nanometers, and then starts to drop, as shown here. So these are definitely due to the significant short channel effect for the gate lengths of less than 200 nanometers. And also we also confirmed the gate length dependencies of the capacitances and also the conductances. So as you see, CGS, CGD are proportional to the gate length. This means that the gates were successfully fabricated as designed. So we got a gate length as designed. But on the other hand, in case of the GM, similar to the FT, so down to the 200 nanometers and the GM and GD, both of them are almost constant. But after that, and then starts to decrease for GM and starts to increase for drain conductors. So these are also the another typical features of short channel effect. Therefore, definitely in case of the devices with a gate length of less than 200 nanometers, so some of the improvement of the RF characteristics were suppressed by the short channel effect. So it's probably due to the 3D and the bulk channel structure. But I think and then it's not that difficult and improves and suppress the short channel effect and to improve the RF device characteristics by modification or optimization of the device structures. Okay, next, and we performed the delay time analysis on the fabricated devices. So I'd like to explain a little bit about the delay time analysis. So total delay, it corresponds to the 1 over 2 pi ft. So this consists of three components as shown here: intrinsic transit delay and drain delay and channel charging delay. So intrinsic transit delay corresponds to a delay in carrier transport across a region under a gate. And this is the intrinsic value. This is definitely the delay time that electron pass through the region under the gate. Therefore, if we reduce the gate length, we can decrease the delay time for this intrinsic delay. Therefore, we can improve the small signal characteristics. But on the other hand, these two and then the components are extrinsic ones. And drain delay, and then this is the delay in carrier transport across the depletion region, extended from the gate edge toward the drain. It's not under the gate, therefore it's not controllable. Basically, it's very difficult to decrease the drain delay. And also the channel charging delay, it's associated with the RC time constant. Therefore, it's relatively easy to improve it by decreasing the access resistance or parasitic capacitances. Therefore, to improve the RF device characteristics, basically the shrinking the gate lengths by to decrease the intrinsic delay time, and also the decreasing the channel charging delay to decrease the charging delay time. So this is very important. And then if it's a fixed device structure, a fixed source drain and then spacing, and then the tau drain and the tau charge, and both of them can be considered as a constant, irrespective of the gate length. Therefore, if we plot the total delay as a function of the gate length, so we can estimate the effective electron density of the transistors. So in our devices, so the less than the 200 nanometer gate length, and these are the occupied, and influenced by the short channel effects. Therefore, these data should be omitted. But by using the sum and the data points for the relatively long gate devices, so and due to the extrapolation of the data points, and then from the slope, and we can calculate the effective electron density. But I'd like to mention that so this is not a saturation electron density of the gallium oxide. It's an effective electron density. It's a kind of the average electron density for the electron passing through the region under the gate. Therefore, this value is very reasonable for the selectively predicted and saturation electron density. It's about 1 × 10⁷. But at the same time, if we compare the result with the state-of-the-art gallium nitride, typically it's a 1 to 1.5 × 10⁷. Therefore, it's much smaller than the value for the gallium nitride. And therefore, frankly speaking, I don't think the gallium oxide RFFETs are comparable with the gallium nitride. Therefore, I think we need to think of the application for the gallium oxide RF devices, and by combining some of the properties and the strong against and temperature and radiation and stresses. Okay, let me conclude my talk. We fabricated the submicron gallium oxide MOSFETs for high frequency applications. And then we got decent DC device characteristics and also the excellent RF small signal characteristics represented by the record Fmax of 27 gigahertz. And we observed the significant and short channel effect for the gate length of less than 200 nanometers. Therefore, we need to solve and suppress this short channel effect, and then also to improve the RF device characteristics by decreasing the gate length. And also we estimated the effective electron density from the FT-LG relationship. It was at about 2 × 10⁶ centimeter per sec. So it's a reasonable value for the selectively predicted saturation electron density. And also it means that the gallium oxide is very difficult to compete with the gallium nitride for the general applications such as the base station or radars, etc. And by combining the strong points of the gallium oxide, strong against the high temperature and the radiation stresses. Therefore, by combining the decent RF characteristics and also the strong properties for the radiation stresses, we can expect to use the gallium oxide devices for the harsh environment electronics. Okay, I'd like to acknowledge that financial support from the scope of the Ministry of Internal Affairs and Communication Japan. Thank you very much for your kind attention. I would like to take any questions and comments. Thank you.
Thank you, Professor Higashiwaki. The floor is open for questions.
So, Vasu, can I ask a question?
Yeah, by all means, go ahead.
Yeah. Hello. Hello, Dr. Higashiwaki. Very nice talk. I have one question related to this gamma radiation work on your devices. You showed that the devices are quite, like, let us say, radiation hardened up to even 1 mega gray or something. But what happens to the metal semiconductor contact or the interface? Because the bulk material might be more like resilient towards the irradiation, but the contacts actually starts degrading very fast. So have you done some specific study on these contacts also on gallium oxide during irradiation?
So, yeah, thanks for the questions. We haven't confirmed the ohmic contact resistance, but as you see this in the linear region, so I think the slope is mostly the same even after the highest dose of the 1.6 megagray. Therefore, I don't think we got a severe degradation of the ohmic contact resistance by irradiating the high dose gamma ray.
Okay. Okay. And then another maybe related question. Do you see some size effect also? Like if the contacts are, because we have done some studies on gamma radiation effect on gallium nitride HEMTs. And we saw that it depends upon the size of the contact also. If the size is smaller, then it is more radiation hardened. And if size is bigger, then it degrades faster. So similar studies have been done in gallium oxide.
No, we haven't observed any, and then the size dependence of the contact resistance. We use the one type of the devices.
Okay, and how much was the size, like contact size of these gate size?
Gate size.
Yeah.
It's a similar to the other devices.
Okay.
Gate
Okay,
length is 4 micron, and the gate width was 200 micron or 400 micron. Yeah.
Okay, okay, got it. Thank you. Thank you.
So,
Vasu, can I ask a question?
can I ask a question from the chat box from a student? And then you can go.
Sure.
So, Masataka, you're probably the best placed person to answer this question, having worked on both gallium nitride and gallium oxide. So, student has a question. Kanika Arora is her name. That gallium nitride is out there and doing so well. So, her pointed question is, what is the point of using gallium oxide? So, you're the best placed person to answer this question.
Okay, of course, and then the gallium oxide and the advantage of the barrel crystals. Therefore, I think the gallium oxide power devices are very suitable for the vertical geometry. So gallium nitride, and they have a barrel crystal and the barrel crystal, but still they're very expensive, and also the quality is not comparable with gallium oxide. Therefore, for the power switching applications, of course, and the particle transistor diodes are main and field, and then can be competed with the gallium nitride devices. And in case of the RF electronics, and as I showed, unfortunately, the basic and device properties of gallium oxide transistors are not comparable with gallium nitride. Therefore, I don't think the gallium oxide and then the RF devices are suitable for the base station application or some of the radars. But as I showed, and then if we combine the another and then the feature of the gallium oxide, it's a very strong against radiation stress. So in this case, and then we can think of, and also that we can explore the kind of the new field for the semiconductor devices, especially the rad hard electronics. Basically, under the radiation, and then we cannot expect any type of the semiconductor devices and operational for the extended period of time. Therefore, I think the gallium oxide could be the first candidate for such kind of new and application fields. So that's my answer.
Thank you. And while we are on that overview mode, Ashok, if I may, so Masataka, since you probably have a bird's eye view of the field, so what is the latest on p-type doping of gallium oxide and the thermal conductivity related issue, which are, I'm guessing, the two issues that bedevil gallium oxide?
Okay, p-type gallium oxide, and if you say the p-type means then the whole conductive p-type gallium oxide, and then frankly speaking, it's almost impossible to develop it because deep acceptors and then also the band structures and the flat valence band top and etc. But we've already developed the deep acceptor p-type doping by using the nitrogen implantation or some artificial nitrogen doping. It's very useful to make the large barrier by forming the PN junction. So I think it's very useful for some of the device fabrication. But of course, it's not whole conductive. Therefore, we cannot expect any bipolar devices using gallium oxide. And thermal conductivity, it's also another drawback, but it's relatively okay because thermal management is not only for the issue of the device. It's not an issue only for the device. Basically, it's a total packaging and then also the bonding or etc. And then we also performed the direct bonding of the oxide substrates to the polycrystalline silicon carbide. So in this case, we got a reasonable and then the enhancement of the heat dissipation property. Therefore, I think the thermal conductivity and the heat dissipation, it's a severe issue, but can be managed by using the existing some technologies. That's my answer.
Okay.
Thank you.
Okay. Thank you. Ashok, go ahead.
Yeah. Hello, Professor Higashibaki. It was a wonderful talk. I mean, I have a question that is related to degradation. Other than the radiation-induced degradation, are there any studies on high temperature, high humidity, environmental degradation of this material?
Okay, we performed the temperature dependent measurement of the device characteristics up to 300 degrees C. And it's up to the 300 degrees C, it's okay. And we didn't see any severe degradation of the device characteristics. But we haven't performed the high humidity and then the experimental, etc. But I think I'm very optimistic about such kind of stress because gallium oxide is the oxide material. Basically, the humid atmosphere and causes oxidation of the semiconductor or something like that. Therefore, I think the oxide cannot be further oxidized. Therefore, I think the humidity and then it's probably is okay for the gallium oxide devices.
Okay, thank you.
So Masataka, thank you again for a fantastic talk. As usual, Kanika Arora, the student, thanks you for your answer. And with that, we go to the next speaker, who is Professor Mukesh Kumar from IIT Ropar. And we stay with gallium oxide, and he'll be talking about solar blind photodetectors. Mukesh, over to you.
Thank you. Can you see my slides?
Yes, we can. Go ahead.
Thank you very much. It's a wonderful talk, this session, and overall talks actually is really very good at throughout the conference. And I would like to thank the organizer to giving the opportunity to share our results on this wonderful platform. My topic is a little bit different, so I will talk about the solar blind photodetector by using gallium oxide. So first of all, I would like to acknowledge the funding agencies, the Government of India, Department of Science and Technology, IIT Ropar, and special thanks to DRDO for funding this project back in 2018. So that is a research activities in my lab. So we have function and renewable energy laboratory at Department of Physics, IIT Ropar. And we are working on a flexible and indium-free transfer connecting oxides. And we are working on a solar blind photodetectors. and earth abundant solar cells and 2D materials. So mainly my talk today is focus on the solar blind photodetector. So that's a presentation roadmap. So I'll discuss about this solar blind photodetector, current challenges, and mainly I'll discuss about the high temperature seed layer, growth of beta gallium oxide on cost-effective silicon substrate. And then I'll discuss about the how we can use plasmonics to enhance the performance of solar blind photodetector. And totally off this, I'll discuss about the growth of gallium oxide on daily use paper by using a sputting technique, and how we are use that gallium oxide thin film for photodetector. And I'll also discuss a little bit about the effect of swift heavy radiation on the gallium oxide. So gallium oxide is everybody knows. Actually, I don't need to introduce that, but it's because of this radiation that is not present on Earth and is absorbed by the Mother Nature, provided the ozone layer. So the radiation less than 280 nanometer is not present on Earth atmosphere. That's why this radiation is known as the solar blind. And any photodetector that is working in this region is known as the solar blind photodetector. These photodetector had lots of application, and especially for defense application like tracking of the missiles, because the some part of the radiation is in actually lies in the UVC region, and it's also used for other civil application like flame detection, space exploration, environmental sensor, security, and for detection of the UVC. And most recently, many other people also saw that their activities in this pandemic time develop different type of the devices. And we have seen actually this UVC recently come up with one of the application for sterilization. Okay, and this device, the UVC sources has been used to sterilize the big compartments, buses, and like all sort of equipment. And nowadays actually this this UVC radiation is easily available on different websites you can buy, and then you can use to sterilize a different day-to-day like object that you are using. But the problem is this UVC radiation that is very harmful for human being, that can change our DNA. So any small leak of this UVC is really harmful. So we have to develop a sensor that can work specifically in this region. These are the different characteristic how to quantify the performance of the UVC photodetector. That is like responsivity, that converts the current per incident power, external quantum efficiency, and like all these parameters. So what are the challenge actually if you are talking about this like other photodetectors like silicon photodetector, but because of the silicon has a low band gap or 1.1 electron volt, also it is a indirect band gap material. So even if you are using like wood filter to filter out all this radiation above than UVC, but still that is challenging because of its indirect band gap material and high dark current in the silicon material that need to be cooled down for the better performance. But if we are talking about the another material that we can tune the band gap up to the range of UVC, then we can have the like AlGaN, aluminum gallium arsenide, aluminum gallium nitride. But the higher doping of aluminum actually put a high strain in the material. But if you are talking about the zinc manganese oxide, but if you see that this is phase segregated, if you are mixing too much magnesium oxide in zinc oxide to match the band gap to absorb the correct radiation. And for the diamond, we have like the band gap is little bit higher, like 5.5 electron volt, and the cutoff wavelength is lower than 225 nanometer, which is even lower than the UVC radiation. And another challenge like the growth substrate. So whenever we are talking about the growth quality of thin film, we are not talking about epitaxial growth, but for the good quality, the people use sapphire, silicon carbide, or even a single crystalline gallium oxide. And we know that there's only one source to buy all these high quality gallium oxide substrate. So we thought actually why we cannot start the growing at least polycrystalline thin film on silicon substrate. So gallium oxide although have lots of properties, but is the main drawback actually is coming out to be is a low thermal conductivity and p-type nature to form this like p-n junction type of the structures. But with these current properties, because these are the open challenges for the scientific community, but it's like diode band gap and like the band gap that is intrinsically solar blind, so you do not need to alloy this material with another material to form like natural solar blind photodetector, and other properties make this material ideal for this solar blind photodetector fabrication. So that is the first work, like the seed layer assisted growth of gallium oxide thin film on silicon substrate. So what we have done actually, we have used the silicon substrate, and then by applying a different temperature cycle, we have optimized the growth of gallium oxide on silicon substrate. And here we have seen that the temperature cycle critically affect the quality of thin film. So here we have seen that like if we are going this temperature cycle where we have giving a substrate heating, like substrate handling before growth of the gallium oxide, and then growing gallium oxide, and then post annealing, and then coming to the room temperature, or in another scenario where we are heating the substrate but we are growing a gallium oxide seed layer which is about 15 to 20 nanometer at higher temperature, and then coming to the temperature where we want to grow gallium oxide thin film, and then post annealing of this gallium grown seed layer, and then depositing gallium oxide, and then post annealing, then we are getting the best quality polycrystalline gallium oxide thin film in this case. And as I mentioned, actually this annealing condition is really critically affecting the growth. So even if we are not hitting the substrate and then we are directly growing the gallium oxide seed layer, then the quality of thin film is not up to the mark. So that is the surface morphology and the like the XRD. So you can see that if you are growing the gallium oxide thin film with the high temperature seed layer, then the quality of thin film is polycrystalline. Okay, and if you are growing without seed layer with the same temperature 650 degrees centigrade, that the gallium oxide thin film is completely amorphous in nature. You can also see with the smooth roughness of amorphous gallium oxide and a very high roughness because of the small crystallite in the polycrystalline thin film. Then we start to like we made a MSM type of a contact on top of the gallium oxide, and these are the details of that. And we use this monochromator to just characterize this photodetector starting from 250 to all the way to 1100 nanometer. So this is the performance of this photodetector. So there is a dark current with a voltage. So you can see that the gallium oxide photodetector growing without seed layer is having a high dark current in contrast to the gallium oxide that is growing with a high temperature seed layer. And that is a photocurrent. You can see that although it is showing high photocurrent, the sample without growing without high temperature seed layer, which is amorphous in nature, but since it is showing a hard dark current, so the photo dark current ratio actually in the visible region is not good for that sample. And these are the like photo to minus dark current of these two samples, which is amorphous and polycrystalline in nature. That is a photo response. We have studied that. So at different voltage, so 1 to 5 voltage, and so at 5 volt we got about 96 ampere per watt at 250 nanometer for the sample. And you can see actually that's a very small 17 nanowatt per centimeter square at 250 nanometer. That this shows a very high performance, and the EQ actually is very high because of this optical gain in this thin film, and this is high EQE, that is because of the optical gain of this material at a different voltage. So there is a time resolve photo response, because if you are growing making a photodetector, then responsivity, how much current it is giving, and then how fast it is working, both are very important. So once we are tested this performance of this photodetector that is grown without any high temperature seed layer, which is amorphous in nature, you can see that this is like where we turn on the like voltage, this turn on this light, and then it is gradually increasing. So that means there is some portion of the persistent photoconductivity. That's why the photodetector is not coming to its natural position or the natural background current. However, if you are talking about this photodetector that was grown with high temperature seed layer, it is just showing like kind of a 0 and 1 performance. So it is on and off. Okay, and it is very fast. Like you can see that the response like time is about 32 millisecond. Okay, and we have also checked the performance, repeated performance for many thousands of hours. Like we have tested more than 2 years now, and it is showing consistent performance without any degradation. So for since we made actually the gold contact on top of that, and there is no symmetric electrode, but we observed this performance without applying any bias. So there's a self-bias performance, and we believe actually that is because of the different Schottky barrier height observed at these two electrodes. And without seed layer samples, we had many defects, and that is is kind of the carrier is tunneling very easily, and that's how we have very high dark current in these samples. However, for polycrystalline sample, there is less defect, so it is reflecting back the carrier, and that's why the dark current is very low. And since in the amorphous sample you are having other type of defect, including this oxygen vacancies, so it's doubly charged oxygen vacancies, and it is resonating with this connection band, and it's giving carriers, lot of carriers. That's why we are having also lot of photo currents. But since dark current is more, so the performance actually is not better for these samples. So we have compared our results, and you can see here that it's a rejection ratio at visible to like 280 or 250 nanometer, and there is a dark current. So we observed the lowest dark current, which is about 1.43 picoampere. Okay, and then it is actually highest rejection ratio, and the response time is here. So that's a very good performance of solar blind photodetector grown on the cost-effective silicon substrate. And you can compare the performance of this with the current solar blind photodetector available in the market, and it is the equivalent or better than that. Now the second part of my talk is a spectrally selective solar blind photodetector. So what we have done here, we have taken this optimized sample that was high temperature seed layer grown gallium oxide, and then we try to study the effect of plasmonics, and we use this silver nanoparticle that was coated on the gallium oxide, and just we got actually very interesting results. So as we know that like if you want to enhance the absorption of a material beyond its fundamental limit, then people use this plasmonic nanoparticle. So we have used this silver nanoparticle because with the motivation that we want to distinguish two bands. That is, in UV actually we have UVA, UVB, and UVC. However, the UVA is not harmful. That is generally actually required. However, the UVC is very harmful. And like a human eye that can distinguish multiple wavelengths and their intensity, but we do not have any working photodetector. If you want to have photodetector working in a multiple wavelength, generally it requires multiple band gap material, so that one material can absorb one particular radiation and the other material can absorb another radiation. So here we try to make a dual band photodetector by using these plasmonic nanoparticles. So we have as usual, we have grown this beta gallium oxide polycrystalline thin film by using a seed layer, and then grown this silver nanoparticle by using a glancing angle deposition for the better uniformity. And this is the device structure, and you can see this absorption. So we start to observe an additional absorption in gallium oxide thin film with a silver nanoparticle, and that is because of this silver nanoparticle coated on the gallium oxide. This is the performance of this photodetector. So this is again like UVC, that is having a 44 nanowatt per centimeter square, and this is a UVA and the black one actually is a dark current. So we have the black spectra, which is dark, and then once we shine with the UVA and UVC by using a monochromator, okay, and then this is again actually the UVC and the UVA, okay, and this is showing the responsivity. So we observe the very large responsivity, so that is about increased to up to 250 ampere per watt, in contrast to the control one, which was having about 88 ampere per watt. And it's a very enhanced EQE, detectivity, and linear dynamic range of this gallium oxide thin film coated with the silver nanoparticles. So just to see the time response, so this is a gallium oxide with the UVC, so that is showing actually again digitized response, like once you shine the light, then it is kind of on and then it is off. However, if you shine a UVA light with a bare gallium oxide photodetector, then there is no response. Okay, but if you are talking about the UVC, then like silver coated gallium oxide thin film, then once you are shining UVC, it is showing response, and once we are shining UVA, it is also showing response, but that is in the opposite polarity. So we will discuss this why it is happening. So once we have this gallium oxide, again once we have this contact made, so this gallium oxide, because of the band gap, can absorb only UVC radiation. So that is actually it generates electron and hole pair, and that electron actually is going over this Schottky barrier, and it is going to the silver nanoparticle and finally collected at the end electrode. However, if you are talking about this silver coated gallium oxide thin film, then this once we are shining UVC, then the gallium oxide is absorbing UVC. But when we are shining UVA, so the UVA is not getting absorbed by gallium oxide. However, the silver nanoparticle is generating hot carriers, and these hot electrons is injecting into the gallium oxide, and then it is actually giving the reverse polarity effect in the silver coated gallium oxide photodetector. That's why we can distinguish UVA and UVC band if you are having. So that is a comparison of the performance of this photodetector, the comparison of this with the other literature reports. So that's the second last part of my talk. So we are discussing about this flexible gallium oxide solar blind photodetector, and that is an amorphous gallium oxide because we are growing at room temperature. So here we use PET substrate, and we grown gallium oxide at room temperature. But instead of coating a conventional metal, so we are using a transparent indium zinc oxide thin film as a metal contact. And we observe that if you are using this oxide contact, then the performance actually is really good. So although since it is an amorphous, the performance is really not up to the mark to the polycrystalline thin film. However, if you are using indium zinc oxide, that is also amorphous in nature, and it is acting as a electrode, the performance is really good, and this is helping for this bending performance. So if you are bending this photodetector at a different radius, so you can see that the performance is not degrading too fast. However, if you are talking about the conventional metal coated gallium oxide photodetector, then after bending up to 20 centimeter, then this the photodetector is completely failed. And if you are talking about one cycle at a 30 centimeter bending, and then we have observed the working photodetector up to 500 cycles at 30 centimeter. So that is really good performance for flexible photodetector. So that is where we use this normal paper. So what we have done actually is this is the scanning electron microscopy of the paper that we use, and then the student hand sketch with the pencils, and we tried even a different pencil, as pencil, because that contains a different graphite content, and we made a asymmetric electrode, bottom asymmetric electrode. One of the electrode is graphite, another is silver. and then we put this paper inside this chamber. We sputter that at room temperature, and you can see there is a like ready photo detector, and you can bend it whatever you like. So you can bend, twist, and then finally once we are done, actually we try to burn it, and then there is nothing left. So it's completely green. So that is a like gallium oxide grown on paper. So you can see the fibrous structure of that. Even we have tried the like butter paper and different like other substrates. So the fibrous nature of the paper is very helpful for this growth of gallium oxide or even the electrode. And you can see there's this is the silver electrode, and this is graphite, and in between actually we have the gallium oxide, and then this is the mapping of the different elements from the photodetector that shows the uniform distribution. And this is a like current in the dark. Okay, so for the paper, and then this is the like IT for bare paper when we had only bottom electrode and nothing is deposited. So that shows the performance, and there is no response from the bare paper, and that is a paper. And the butter paper, although the performance for the butter paper is not up to the mark as compared to the normal paper, and we made a point that the surface roughness here is playing a role because we are doing a hand sketch of this bottom electrode. So this is the performance, and like the take home is here that the gallium oxide grown on this paper substrate is working really very good, and it shows the performance up to 100 volt. Okay, so we can apply up to the 100 volt, and the photodetector is perfectly working fine. And this is the bending test. So we bend at different radius, although the performance actually once we are bending is really decreased, but after some time actually it is saturated. And you can see here that like even if the twisted angle, if you are twisted 100 times at 180, then after some time, after degradation, about 24% degradation in the current, the performance is become saturated for this paper based photodetector. So you can see here this the current and this cyclability, like 100 cycle, 200, 400, and 500. The current little bit decrease, okay, but the performance after that is really saturated. And the one of the big question that comes for that is the like if you have grown the sample on the paper, but what happened for this wettability? So we have yes.
Okay, 2 minutes.
Yeah, please. So then we actually we coated this special paint on the paper, and then even we dip inside the water and just tested that. But this is the contact angle measurement with the water, and you can see that without paint actually this contact angle is decreasing. That means the water is going inside the paper. However, if we are coated with the paint, then the water contact angle remains same. That means the water is not going inside, and the performance with and without the paint, actually the performance is nearly same. So that is like the bottom electrode, and you can see this because of the symmetry, different work function, this is working even at zero bias. So there's the last two slides is a recent results where we have discussed investigated the effect of a swift heavy ion radiation, because this material may be highly potential for space application. So we start to test the amorphous and polycrystalline thin film under swift heavy ion, so which is silver 7 plus are having of 120 MeV energy. So here you can see that the polycrystalline thin film and the amorphous one is completely deoriented at 201 phase. So this is completely destroyed, and there is a new peak actually is appeared. Although this is shift because of maybe the stress grown in the thin film after the radiation. And this is the morphology change. So this is amorphous, and you can see there is a kind of a nanopores generated inside this thin film. How the polycrystalline thin film is completely turned to this kind of like this small crystal is completely round off. This is the last slide. So we have seen that the responsivity changes. So this is a control sample, this is radiation. So after radiation the performance is really degraded, and then we have self annealed the sample for about 3 months. After that we start to anneal the sample, at 100 degrees centigrade for 30 and 90 minutes. And then we observe that once we anneal at 250 degrees centigrade, the performance of the amorphous gallium oxide is like way better than the polycrystalline one. Okay, and we also done detailed study, like we have done photoluminescence, and we observed that this radiation is annealed the defects inside the gallium oxide. So in summary, we have grown this gallium oxide on cost-effective silicon substrate, and we use this silver nanoparticle for better performance. Also, we have shown some results on the flexible gallium oxide. So that is a team, and this work is mainly done by Kanika Arora and Damanpreet Kaur. So thank you very much, and I'll happy to take questions.
Thank you, Mukesh, for a broad overview of a variety of photodetectors from silicon to paper. Paper is even more cost effective than silicon. And so the floor is open for questions. Arnav Bhattacharya has a comment. I think he says there was a fantastic talk. Very nice work.
Thank you.
Right. Any questions for Mukesh here? If let's thank all the speakers. We have come to the end of the session. We had 4 fantastic talks.
I mean, if there are no questions, I have one.
Okay, go ahead, Arnav.
Yeah, so I mean, the paper detector seems like the way to go. So, I mean, do you have any idea of what could limit the lifetime of this?
The lifetime, the only one challenge is this. This is this is a usual paper the student taken from the printer and then just cut in the and just hand sketch with that. The main problem is the water, the humidity. So we doubt actually for a long time the water can penetrate through the edges and then it can degrade. But we have applied a special paint on that and we even dip into the water. But that is the dip actually just like for few seconds. But although the like humidity can really affect that, but we have tested for about 1 month or so and it is perfectly fine.
No, I mean, the reason I ask is, do you think something like Tyvek or non-woven fabrics, etc., might be a better substrate than paper?
Yes, that could be. Because we have tried like other substrate and we found that the surface roughness really matters. So if we can have the fibers that can even go to high temperature or humidity hydrophobic in nature, that will be really wonderful.
Great, thanks a lot.
Thank you.
Yeah, Vasu, I have a question.
One quick, Rajendra, you can go ahead just 1 second.
Yeah,
okay, go ahead. I just had a follow-up to what Arnav had said. So,
please.
no, if water is a problem, there are various packaging solutions to prevent water from coming in this day and age, right? I mean, organic electronics, you talk to those guys, they will give you 1,000 solutions because that's the standard problem there.
The main problem actually, whatever you are applying should be transparent to UVC light.
Right. Okay. Go ahead, Rajendra.
Yeah, Mukesh, very nice talk.
Yeah.
So I have a question related to your last part where you showed that the swift heavy ion radiation, in the case of amorphous gallium oxide, there is an enhancement in the photoresponsivity after some time and then doing some annealing.
Yeah.
So what you were telling is some defect annihilation due to this swift heavy ion radiation, or what was the mechanism?
The mechanism actually is there is a like a reduction in the defects, so that we observe by using a photoluminescence. But the main reason, another reason actually could be this: the nanopores kind of things actually is formed on this beta gallium oxide, amorphous beta gallium oxide. The gold actually is diffusing inside, so that may be possible reason for this enhanced performance.
I think you need to do some microstructural investigations to look a little bit more deeper into the reason, because amorphous gallium oxide, it's already like amorphous, so there is no question of
But these amorphous gallium oxide and the beta gallium oxide, after radiation, they have come up actually with a new phase. So the radiation actually completely melt and recrystallize both the phases.
Yeah, yeah. So it is, I think, a kind of recrystallization. But yeah, but recrystallization sometimes, like, it also needs some seed crystals to recrystallize. So I think a little bit, yeah, more some microstructural investigation have to be looked into. It's a good result.
Yeah. So
Okay.
we are
Yeah.
actually working on that. Even we are doing this time resolve PL just to come up with some type of a defects inside.
Okay. Okay then.
Thank you.
Yeah. Thanks.
Great. Thank you, Mukesh. And thank you all for participating in this session. And let's thank all four speakers for a very nice and good session on gallium nitride and gallium oxide. With that, I bring the session to a close.
Thank you very much.
Yeah. So I have to.
Yes.
Yeah. So I think I would like to make a kind of a grand conclusion, in the sense that today is the final conclusion of all our sessions. So I think it was a quite good symposium, quite informative, and a lot of different types of talks were there. And I think we could cover materials also, from silicon carbide, gallium oxide to nitrides, even diamond also, and the devices, from optoelectronic devices, LEDs, UVC LEDs, photodetectors, electronic devices, high power electronics. So a number of interesting research topics were presented by, I think, the leading researchers across the world. So for that, I am we are grateful to all the invited speakers for making this symposium, wide bandgap semiconductor symposium, so successful. And also thankful to the young researchers for oral presentations and their poster presentations. And finally, to all the session chairs who controlled all the sessions very well, and all the things were happening within time. So finally, I would like to thank Vasu for chairing this session today, the final session of this symposium. So thank you very much. And all of you are invited for 5:30 concluding session of this conference, ICEE conference. So we have a concluding session at 5:30. So thank you, all of you. Bye.
And on behalf of all of us, thank you, Rajendra, for putting this whole symposium together. Thank you.
Okay, thank you. Bye, Arnab.
Yeah, next time you better do a rump session online as well.
Yeah. I think, yeah, that can also be planned. Yes.
No, great. Thank you. Thank you.
Yeah. I think has already left. Sudhiranjan, you are there? I think he has left.
Rajendra.
Oh, hello.
It was a nice conference and good organization.
Oh, thank you. Oh, you are Manoj
Yeah.
from UK. Oh,
yeah.
Okay. I could not. Oh, you were also attending. I did not notice, actually. Yeah. Thanks for your invited talk. Thanks.
No, thanks for arranging the invitation. The conference was good, and also I attended today because I've seen there were some very nice topics, which is started early morning today for me.
Oh, yeah. Okay. It was too early in the morning. The coupling and again the two levels. Okay. So thank you. So thanks for attending and giving an invited talk. we will hopefully meet in some other place, some other conference, or maybe in person next year if everything goes well.
Yeah. Or maybe we can have a quick chat someday.
Electronically induced transparency.
Yeah, definitely. Yeah, there was some information to share with you. I was just waiting. So maybe I will give you a call sometimes in December. Okay. Okay. I will write an email to you. Okay. Yeah. Thank you. Thanks. Bye. Bye.
So in the non-perturbative regime, which are the ultra-strong and deep strong coupling regimes, which are of current interest, your G by omega is of the order of like 0.1, greater than 0.1 for ultra-strong. And if it is G by omega is greater than 1, omega is the resonance frequency. So here the coupling is comparable to the frequency and not to the losses. So you go to these non-perturbative regimes where your frequency shifts or the effect of coupling is as large as your resonance frequency. Right. So there are different coupling regimes which are reported. So just to show in pictorial way, in the weak coupling regime, so you can have Purcell effect. So where you see reduction in the radiative lifetimes, which means like you have enhanced emission from in the weak coupling regime. And in the strong coupling regime, you can have quantum Rabi oscillations. Right. And in the ultra strong regime, and also like splitting of the energy levels and anti-crossings are reported in the strong coupling regime. In the ultra strong regime, like so you go to cases like where you have density dependent coupling term, like so you have large number of two-level systems where the effective coupling strength can be G prime is G times square root n is the number of two-level systems. Or you can have a very high Q cavity with a single molecule. So there also like you can get a ultra strong coupling. So you can have applications in modified optoelectronics and quantum vacuum emission. So in these non-perturbative regimes of ultra strong and deep strong, so even the vacuum state is expected to be modified. Okay. So this is mostly interesting for the quantum information processing. So if you look at the literature, so this is taken from these two review articles. So basically there is a lot of work in the weak and strong coupling regime, but the ultra strong coupling regime, there are very few handful of reports so far. And in the deep strong coupling, like there is only one system that's in the superconducting qubits where G by omega greater than 1 has been shown so far. Okay. So our own work, like so we have been working in different regimes. For example, in photonic crystal microcavities with a single quantum dot, we showed by temperature tuning that like we can bring the quantum dot resonance matching with that of the cavity resonance, in which case like you'll have this Purcell enhancement and enhancement of the quantum dot emission. So here the Q factors are of the order of like 6,000. So in the weak coupling regime, we see this thing. So we're probing this for, we probe this for single photon emission from these structures. So we also have seen plasmon-mediated enhanced emission from zinc oxide, zinc sulfide nanoparticles, like where we've seen about 10 times enhancement because of encapsulation as well as the plasmon mediation. Compared to unpatterned metal, the patterned metal shows about 2.5 times enhancement and a completely linear growth with respect to the pump power. Right. So in the plasmon-plasmon interaction, so we have reported, like for example, strong coupling regime, where the interaction of the in-plane propagating modes, so they interfere with each other, they interact with each other, and the coupling leads to these anti-crossings, which are highlighted by these rectangular boxes. Okay. So you can see different areas, like the different regions where you can see these modes which are not crossing, but they are anti-crossing each other. So more recently, like we have shown that we can enhance the Purcell factor as well as the collection efficiency for quantum dots which are embedded inside the central region of a 5-layer hyperbolic metamaterial with a nano antenna on top. So this gives like very directional emission from the quantum dot emission. So these are some experimental results. These are optical images and AFM images of the structures. So each of the dot corresponds to the nano antenna, which we probed a large number of them. So initially we optically identify which are the bright antennas and then probe them for the emission statistics. So we see the expected reduction in the decay time when the plasmons when the quantum dot emission is coupled to the nano antenna mode. Okay. So we saw about 200 times enhancement in emission as well as like 40% collection efficiency from quantum dots which are embedded in these hyperbolic metal materials. Okay. So we also recently proposed a non-classical light generation because of quantum dots which are in close proximity with a metal edge. So what we showed is that like you can generate these so-called null states. So if you have, for example, two dots, we can have plasmon mediation between these two quantum dots, which leads to null state generation, which means all the photons will be either in the detector 1 or in the detector 2 path. So if you have n number of quantum dots which are close together, if they are coupled by this plasmonic mode, so then we can have all the n photons emitted in one of the two given paths. Okay. So this is the null state generation, which is plasmon mediated quantum dot coupling. Okay. So if you look at periodic structures, for example, a 1D gray a plasmonic crystal. So what you see is geometric resonances, which means like if you change the, I mean, this is a dispersion plot, wavelength versus angle or omega versus k. K is the momentum. So in this case, like what you see is like if you change your incident angle or the k direction, you're also changing your resonant wavelength. And in addition to that, you also change your lifetime. Right. So because the line width of this mode is changing. So this is calculated dispersion for the grating given by this. Right. So we also measured this and compared, but for the point of this is like if you have periodic structure, metal dielectric structures of wavelength dimensions, you have these geometrical resonances, which will depend on your dimensions of your periodic structure. Right. Now, what we showed is this periodic versus quasi-periodic. We are working on these quasi-periodic structures for almost like 5-6 years now. So where we showed that compared to if you have same density of scattering elements, which are arranged in a square lattice and a quasi-periodic lattice, we showed that the quasi-periodic lattice is a very dense K space, which leads to a band of plasmon modes, which are dispersion-less. So we designed such structures and then looked at their statistics. So which showed that like, so basically this is a hyper-uniform structure. The pattern which we are generating, the quasi-periodic pattern, is a hyper-uniform structure with 80% randomness in the structure, which we know because if we take a reference scattering element and look at the nearest and next nearest neighbor distances and the angular distribution, we see that like more and more as we go to higher or the next nearest neighbors, next to next nearest neighbors, more and more scattering elements are coming in non-pi by 5 angles, which leads to randomness in the structure. Right. So this is the SEM image of one of the pattern structures. Interestingly, like, so if you compare the optical constants N and K values of bulk gold versus PLQC or unpatterned gold versus PLQC of the same thickness, you see that like their N and K values are pretty similar. The whole distribution leads to a fill factor of error of less than 10% in this structure. Right. But if you look at the response compared to unpatterned metal, like we get about 10 times enhancement in transmission. So this is the plasmon-mediated transmission over a band of wavelengths. Right. So this red band is shows the dispersionless plasmon band. Right. And this also has interesting nonlinear properties. So we showed second harmonic generation from these structures in the entire band, which shows like plasmon enhancement. So one interesting aspect in this is like, so what are the carrier dynamics, hot carrier dynamics in plasmonic structures? So the nanoparticles have been well studied. So there are 3 time scales basically. So in the first step, so the plasmons which are excited, so they go to non-thermal hot carriers. So the plasmon mode decays into hot carriers, high energetic electrons. And then these high energetic electrons, due to electron-electron scattering, so they thermalize themselves over a time scale of 100 femtosecond. Then these thermalized hot carriers, high energy electrons, they interact with the phonons, and then they decay down in the energy scale. So that happens over 1 picosecond time scale. Right? So as I said, this is okay for nanoparticles, but if you're looking at plasmonic surface plasmon polaritons, we wanted to get the geometry independent dynamics. So we studied these dynamics in the plasmonic quasicrystal, because we have dispersionless plasmons in this. So we considered the band structure of gold, and accordingly chosen 4 different pump conditions. So in the initial 500 nanometer, we are exciting this 5D to 6sp interband excitation of electrons. This is a free carrier excitation. And in the 575 nanometer excitation at the L band, so we basically excite the high energy plasmons. This is again interband plasmons. And at 650 nanometer, we chose to excite simultaneously the interband excitations at X point and intraband excitation at the L symmetry point. Then at 800 nanometer, we have the low energy plasmon excitation. So this is the resonant condition. So the probe is always chosen to be at the low energy plasmon mode. Okay. So we looked at the dynamics. So we see linear dependence for free carrier and plasmon excitation, but for 650 nanometer, we see a quadratic dependence, showing that there is a alternate pathway for the hot carriers to decay down to. So you have 2 values to which the hot electrons can decay down to. Right? So accordingly, the rise and decay times are different, and we did all these studies in detail. Okay. So for the purpose of this talk, I'll be concentrating in the next 5-6 minutes on the plasmon exciton coupling. Right. So we have a broadband dispersionless plasmonic system, which has broadband linear transmission enhancement. The strong local field leads to harmonic generation, and the plasmon dynamics are limited only by the metal band structure. And we have very interesting near field properties, which are not covered here. But for the next step, so we'd like to look at, would this strong local field correspond to enhanced interaction between plasmons and excitons? And could we go to non-perturbative regimes, or under what conditions we can reach the non-perturbative coupling regimes between plasmons and excitons? Okay. So the structure which we studied is like this. We have a quartz substrate, a 50 nanometer thick gold, which is patterned to have plasmonic periodic structure, and we have a 10 nanometer thick SiO2, so that image charge doesn't kill the excitons in the quantum dots. Then we spin coated quantum dots on the top at different speeds, so that we can control the density of quantum dots on the top. Okay. If you look at the bare quantum dots, we get the quantum dot resonance at 665 nanometers. So we chose 2 different conditions. The pump is at 400 nanometer or at 665 nanometer. At 665, we have resonant pump probe. And at 400, we are exciting the free carriers in the quantum dot, and the probe is always at 665, matching with the quantum dot resonance. Interesting point is we have a very broadband plasmon resonance, so the 665 also corresponds to plasmon excitation. Right. So these are the SEM and AFM images from which we estimated the quantum dot densities. Here I'll report 2 different densities. One is of 150 quantum dots per micrometer square, and the other one has 2 into 10 power 5 quantum dots per micrometer square. Okay. So the interesting aspects are first we looked at the PL. Compared to the bare quantum dots, we measured the PL on plain gold, that's unpatterned gold, and on quasi-periodic pattern. We see that both of them are blue shifted compared to the bare quantum dots. and there is a redshift between the gold and the PLQC quantum dots. Quantum dots on PLQC are redshifted from those corresponding to those on the plain gold. Right? So the pump probe dynamics show something interesting like this. So there is a very long decay, but then there is a little faster component here. And when we zoomed in this region and did high resolution measurements, we see these oscillations in the time dynamics. So the oscillation period is about 0.85 terahertz, and the Fourier transform also shows at 0.5 terahertz. So the fit here is a modified 2-temperature model. And what is interesting is that like these oscillations are lasting much longer than the plasmon lifetime. The plasmon lifetime, as I showed in the bare plasmonic quasi-crystal, as well as in this with quantum dots, we have about 1 picosecond lifetime. So 1 to 2 picosecond depending on the excitation intensity. The plasmon lifetime is the order of that, but then these oscillations are lasting up to 30 picosecond or longer. So we did, this is in the transmission, is the delta T, differential transmission with and without the pump beam. And we did the simultaneous reflection and transmission measurements. So the delta R doesn't show those oscillations. There is a very weak oscillation.
5 minutes.
Yeah.
5 minutes.
So there are oscillations, weak oscillations at much longer, slightly longer frequency, but these are very weak, right? So if you go to low density quantum dots, we do not see these oscillations. And so what these dynamics show is that like, so we have different reflection and transmission dynamics. So the reflection and transmission delta R, delta T are different for PLQC as well as gold structures, because in one case you have plasmons, in the other case you do not have plasmons. And the transmission involves the plasmon mediation. Right? But the reflection is mostly governed by the exciton absorption in the top quantum dot layer, or when the free carriers are generated, like you have more metallic nature, which leads to a positive delta R compared to delta R negative when you have absorption in the quantum dot layer. Right? So you can distinguish between the process of delta R and delta T, reflection and transmission processes in these structures. Right? So we did extensive both semi-classical as well as full quantum Rabi model calculations. So the calculations involve a 3-level model. So you have a common ground state, and you have these 2 plasmons corresponding to 2 excited states, E2, E3, corresponding to the 2 plasmon modes, which are separate by this energy separation corresponding to the Rabi oscillations. And then we introduced Z2 is equal to 0. So there is no direct coupling between the excitons, because these quantum dot clusters are spatially separated. So we do not expect direct coupling between these quantum dot clusters. So the G2 is 0, but still with the dynamic the decay times and rise times taken from the experiment, like when you put in the model, what we see is we can get plasmon mediated exciton coupling. And that leads to G by omega of about 0.441, which is for the high density resonant excitation case. So we have ultra strong coupling. So the coupling is between excitons and excitons, which are mediated by the coupling is mediated by the plasmons. So the excitons which are emitted by the quantum dot clusters in the hotspot regions, so they excite couple to the plasmons, and then those plasmons basically excite other quantum dot clusters, and this leads to the coupling between these 2 excitonic clusters. So that's the mechanism which shows that like we have ultra strong coupling at 2 into 10 power 5 quantum dot density. So just to summarize, like, so the excitons are coherently coupled plasmon exciton state, plasmon exciton coupled states. These the dynamics are interesting for novel device applications, including light emitters. Now, cavity quantum electrodynamics has evolved from perturbative regime to non-perturbative regime, and more recently, like systems exhibiting ultra-strong coupling are being pursued for their rich physics as well as for applications in quantum information processing. So we are showing plasmonic phosphate crystals with the quantum dots on top, plasmon-mediated exciton-exciton coupling, which is in the ultra-strong non-perturbative regime at ambient conditions. So unlike the superconducting or other systems which have been shown so far, we have at room temperature under ambient conditions. So thank you. So these are the acknowledgements. This work is mostly the thesis work of Banuj Naik. So thank you.
Thank you, Professor Venugopal, for a very nice talk. And normally, as I understand, people should ask question on chat box, and I see right now. I have a question here because you told that you have a pump and probe wavelength varying from 500 to say 800. I suppose that you are taking this from Icee laser, right?
Yeah, it's an amplifier laser, Icee, yes.
Okay. And this the last slide you told that for novel light emitters, this study will be going to be very useful.
Yeah, I mean that's one of the applications in the because this is ICEE. I thought like I'll just show about that. Like so, there's like light emitting plexitons is one idea people are looking at. So if you go to plexitons, like so, we are basically splitting your exciton mode into two modes in the strong coupling regime. So you can generate like multiple colors because of these strong coupling features. So that's where this would be interesting to generate like new light emitting states.
Okay. So Joseph sir, what do we do? Like there is no question on chat box, so
more questions from the audience here in this hall or more? So if so, then we can go to the next speaker.
So now let me thank Professor Venugopal for a very nice talk. It is, I know this is a very recent subject and it is gaining a lot of attention. And I also know that to ask questions, this audience should at least be in resonance with that field because this is an advanced field. So thank you very much, Professor Venugopal.
Thank you, Dr. Mitchell.
Okay. Now the next speaker is Professor Dr. Amit Agrawal from NIST. Dr. Amit, yes, you are there, right? Hi. So now let me introduce Dr. Amit Agrawal. Dr. Amit Agrawal is currently a project leader at NIST at Gaithersburg, MD, USA, and an associate research scientist at the IREAP of the University of Maryland at College Park. He received his PhD in electrical engineering from the University of Utah, followed by a postdoc at NIST. He then joined the faculty of Syracuse University as the inaugural John E. and Patricia Brewer Professor in Electrical Engineering in the EECS department. His current interests are focused on developing integrated nanophotonic device architectures operating from the ultraviolet to the infrared for quantum optics applications, including atom trapping and frequency comm. I suppose this is going to be a very nice talk. Professor Amit Agrawal to give his talk. You have got about 25 minutes, and at 20 minutes, I will prompt you. Thank you. You may start now.
Thank you, Dr. Dixit, for the kind introduction. I hope you can hear me.
Yes. Okay. No, everything is okay.
All right. Yeah. Fantastic. Thank you, Professor Joseph, for the great, kind invitation and for the kind introduction. And so my name is Amit Agrawal, and I'm going to be talking about some of our recent work on using flat optics, and I'll talk about that in a second. What I mean by that, mostly from an atom physics perspective. Okay. And so part of my talk is not going to spend too much time on talking about flat optics or their applications in general, but sort of the assumption in the talk is that some of you in the audience are familiar with the work on metasurfaces, but I'll be happy to answer any questions at the end of the talk. Okay, so this is my group. It's mostly 5 postdocs. Some of them are very it always comes as a cost of ADAB. The best microwave atomic clocks work in this regime where I said that they cannot do better than 10 to the minus 13. That's their fundamental limit. But if you go to optical atomic clocks, they can do much better, but they are much, much larger in size. Okay. So the work that I'm going to be presenting today comes out of DARPA, out of number of programs that came out of DARPA, ACES, A5, and whatnot. And the idea is not to go along this diagonal, but to go along this diagonal, which is make them better and make them smaller, reduce what they call SWAP, which is size, weight, and power. And if you are in this regime, then really it is useful for commercial applications. Okay. One can look at what applications they enable. So if I can make atomic clocks that are much, much smaller, then the chip scale atomic clock that I showed you that are low power applications are typically used in navigation and undersea exploration. If you go to a little bit larger ones, then you can, such as rubidium clocks, then telecom, finance, military, and communications are applications. And then finally, the best atomic clocks, which are reference clocks for strategic applications, are typically used in like gyroscopes and interferometry and radar and studying fundamental physics, metrology, and satellite. So there are a number of very, very important technological applications that are enabled, and they will all become better if one could figure out how to make an atomic clock that is very, very small and has a very, very high stability. Okay. So we are part of a program here at NIST together with a number of partners from 10 different universities. There are it's an 11 PI program where the idea is to take this tractor trailer clock, if you would, and then make it
Hello. Good evening.
Hi. Good evening to all of you. Video change camera. Okay.
Good evening.
Good evening, Vasu. How are you?
Good, you look relieved.
Yes, you can imagine my position. Yes, I'm just recalling the 2018 December evening. All right. Okay, so I think, yeah, Mayank is also there. Hello, Mayank.
Hello.
Hi.
Yeah, as Vasu said, you look relieved,
All right.
relaxed, no more worried about IEEE business.
No, still the publication has to go.
Yeah,
One more task has to finish. Yeah.
that's a major task, I can
Yeah.
tell you.
Yes.
वो technical चा
But
का headache है वो.
No, but we are ready for that. We have made a team and people started working, so it should be okay. All
yeah,
right.
yeah.
Okay. I think Professor Rao has also joined. So hello, Professor Nokant.
Hi,
Hi.
how are you,
Hi.
Neeraj?
Yeah, fine. Today plenary was fantastic. That the Ramesh talk.
All talks were very good. Yeah.
Yeah, very good. Yeah. So we put the, I was telling that we broadcasted also all the plenary and evening talks through YouTube, ITD YouTube channel also. And there were many views. For example, for the inaugural one, I think 938 people have watched it. And so that's a good thing. I mean, people, the students, they keep on watching. So it's a good. Okay, so maybe we can start.
Yes, I think we shall start now. If you may ask Professor Ram Gopal Rao if he's here.
Yeah, that's okay. Yeah. Professor Rao?
Maybe you can call him.
Yeah, okay. Yeah, Professor Rao was telling that there is a meeting, but he said that he will join. So maybe that in office, the person would have made ready all the connections. Maybe I will try to call.
Yeah, maybe just you can call him, and if
call.
he is not available, then maybe we can go ahead.
Because there was something related with the. Yeah, he was going. He was saying that there is some engagement, but then he said that he may join. So, because his name is there on the participation list. We will call to his office. Yeah. Okay, now. So,
So how is the situation in Icee campus, COVID situation?
It's not too bad. I mean, you have the
Okay.
usual few cases here and there, but by and large, it's not too bad.
Okay, that's good. Yeah, you have to unmute, Professor Khare, unmute.
Yes, I did that. So I think Professor Rao was having another meeting, so he may not able to join. So I think we can start because in the morning I have briefed him about all the developments. So let me share my slide.
Actually, there is just a brief introduction. There is one like Professor V. Ram Gopal Rao's name. Somebody is here.
Yeah, actually, that is from his office because
Okay.
the person has made it ready. Because I told him that we're going to have, so he logged all the things, but somehow he got engaged. He could not come.
Okay. Yeah, now it is
Okay.
logged out. I think now it's logged out. Okay.
Yeah. So that's why
Okay,
he
let
made
us.
all the preparation. So with that
Yeah.
intention, because he said that he will try, but if he could not, then so because of that, the name was there. Okay. All right. Okay. So good evening to all. So now we have reached to the concluding session of 3 days conference. So every good thing come to an end. So is this conference. We had a very hectic, like all the talks and all that. And in the offline conference, we have a break, then we can have a tea, then we can have good lunch and dinner and all that. But in this online conference, all our time has been eaten up and all the talks are just neck to neck. So we didn't have time. I mean, kind of thing. One talk of the after the another talk was going on. So kind of very busy schedule. So most of the conveners of the symposia having a tough time to track all the time because you see one thing was after the other. So they have to really track in such a way that really to come to the and we have also fixed the evening lecture at 6 o'clock and then the speakers were sitting somewhere else. So we cannot say that, look, the sessions are running half an hour late, so we will start half an hour late. That was not possible at all. So if 6 is means 6. So we have to start sharp at 6 and somehow we could manage the time very well. And really the contribution goes to all the symposia conveners to maintain the time of their symposia, talks and all that. And being all the talks as a kind of online talk, it was really a tough time to maintain that. And I just want to inform you that we have almost like 157 invited talks, including all the plenary and evening lectures in this one. And out of this, only I think three or four talks have been given recorded. All talks were given online. So this was our assumption was that in maybe that people sitting in abroad may would be more comfortable to give the recorded talk, but that assumption was not correct. Everybody was ready and people came very early in the morning, like 5 o'clock in the morning or something to give the talk, and late night also they could do that. So that was a amazing experience for us to have this thing. So let me present you a summary of this one that so this is my first slide. So yeah, if you see this data, we have 1,473 registered participants who registered for this conference, and we have 158 invited talks, including the plenary invited and all that. And all the talks were very well presented and was very well in time, and it was really attended by many peoples. And the abstract that we received is like 426 abstract we received. And after the review process, which in most of the review abstracts were reviewed by two reviewers, we accepted only 338 papers. And out of this, 261 were given in posters and 77 was in oral presenter. We want to put more in the oral presentation, but the problem was that we have only 3 days conference and there were so many invited speakers that we cannot accommodate more than this oral presentation. And almost like 20% paper got rejected because we maintained high standard for this conference. And in the tutorial session, we have the 4 topics. And in the 4 topics, we have the talks, and 96 were the registration for this tutorial one. And the interesting part I found in this online business, that the portal that we prepared, in which the registered person, once it go inside, it can really go from one hall to the another hall. So there was quite a floating things were going on. An interesting thing I observed, that the tutorial session of the wideband gap, which was having 3 talks, so it was running late. So many of the participants who got registered for the photonics and this one, they entered into the hall of wideband gap and they listened the wideband talk also. So that was again an interesting experience, because if you get a flexibility, so people are not really that they have come for photonics, they will just want to listen photonics. If something interesting going on in wideband gap, they would certainly listen to that. So that was another interesting experience that we got from this thing. Okay, so before that, let me, not that one. Okay, let's just stop sharing. Stop sharing. Okay, so now before I proceed, I request Professor Rajen Singh to give a overview of this technical program. Rajen.
Yeah, hello. Thank you, Professor Khare, and good evening to all the people here, delegates here. So I think more or less Professor Khare has already spoken about the kind of technical presentations we had. Just to summarize it, we had 11 technical symposium, if you see, and they were ranging from, you see, all the important areas of electronics related activities, materials, devices, growth, and new kind of, let us say, logic, memories, and neuromorphic devices. Everything was covered actually, including photovoltaics, spintronics, and everything. So I think all the invited speakers really made very good effort, sincere effort to make the presentations. And as Professor Khare also said, that only a few people gave a pre-recorded talk, and most of them all appeared in person. And I remember that in Wideband Gap Semiconductor Symposium, one professor from Canada, he was giving the talk at 1 o'clock in the night also. So that shows actually the kind of interest it has generated among all our, let us say, speakers all over the world. And our keynote speaker, really, let us say, Professor Stuart Parking, the talk was really very, very insightful and very, very informative. And there were 3 plenary and 3 evening lectures, which were equally exciting and very, very informative, future looking. And what is going to happen in the next 10 years, we saw actually in electronics or devices. What is going to happen in the next 10 years, we saw a kind of glimpse also of that in many of these talks. And apart from that, 157 invited talks, and many of them from abroad. And oral presentations were also equally all these young scientists, PhD students, and postdocs. They prepared really very nice talks and gave their research activities, what they are doing, some kind of overview. And there were 261 poster presentations, and I felt that posters were also very, very well prepared, and systematically, sincerely, the students have prepared the posters, not thinking that okay, it is online conference. So with the same kind of sincerity that they would have done for offline conference, it was done in this case also. So I think that is what I would like to summarize, that overall the technical program of this conference was very high quality, and the talks were really let us say, what kind of talk you will hear in any international conference. So that was truly international standard. So thank you, Professor Khare, and thank you all of you. So now I hand it over to Professor Khare.
I request Professor Bhaskar just to summarize about this tutorial things. Professor Bhaskar.
Yeah, hello. I'm sorry, my video camera is not working, so I'll be only on audio.
It's okay. It's all right.
Yeah. So I think so. We had a fairly good turnout for the tutorials, and I think so. A lot of people are still going to watch the tutorial because we got a lot of requests for for the video recording later on, things like that. So when that tells you that not only did they want to attend, they wanted to attend it again and look at it. So that I think is a very good sign. I think we had so terahertz, we had Professor Gautam from JPL and Professor Prabhu from TIFR. I think that session really went out well. Similarly for photonics, we had Professor Amit Agarwal from NIST. For neuromorphic, I think there was only one talk, Professor Chetan. So that was a half tutorial. So neuromorphic and photonics were, each of them were half tutorials. Chetan Thakur from ISC, but I think again, one talk, but very well attended and appreciated by the audience. Wide Bandgap had a full day of tutorial, I think. So we had the whole spectrum, one talk, and so wide bandgap, I would say, would have been the most comprehensive tutorial. Overall, there were 96 participants, and like Professor Neeraj Khare said, I mean, we had about 20 to 25 average registration per session, but ultimately what ended up happening is 70-75 people were attending all our tutorials. So I think tutorial I didn't have, organizing wise there was no issue. Everything went off smoothly. I think we had some issues later on when everything needed to be in a particular time slot, but for tutorial, I think we didn't have that constraint, so it really went off well. I think so. I'm still waiting for audience feedback, regarding what topics they would like to cover in future ICEE and things like that. But I think these topics, I think at least the choice of topics and choice of speakers were very good, and was very well appreciated by the people attending those. Okay, so I think that would be the summary.
Okay, thanks, Bhaskar. You see, in this symposia, in this conference, we have 11 symposia, and each symposia we have 3-4 persons members helping in that particular organization of that symposia. So altogether, we have almost like 50 persons team who were just responsible for this managing the big show. So what I will do that I will invite the symposia conveners one by one, just to share the experience and the kind of overview of their particular symposia. So Professor Samresh Das, two-dimensional materials and devices.
Oh, okay. Can you hear me?
Samresh, are you there? Yeah,
Yes.
Samresh, yeah, good.
So in the 2D materials and devices, we have 17 invited talks and 10 oral presentation and 38 poster presentation. So, and out of 17 invited talk, one was only the pre-recorded talk, because in her time, like Professor Edwin, so her timeline was like in the middle of night, like 4 o'clock. So that's why she has given the pre-recorded talk. But so in this symposium, we have a talk from the growth of the 2D materials like the CVD and epitaxial growth, and then the different devices like optoelectronics and photonics devices, and also the electronics, 2D materials, and then the mechanic, like the other is the main types of devices. And also one talk was given by the Lame, is the director of the Aachen University, where he emphasized the 2D material integration with the silicon. So they have set up a center where they are integrating this 2D material for the chip level fabrication. With that, like with the fab also they are trying. So that is one direction, like they are setting the infrared detector, like array of the detector and imaging camera using this 2D material. So maybe in future also we also have to think like how in India we are doing a lot of research in the 2D materials, how to integrate that things in that is he has given nice things. So all the most I can see the online around 30 participants attending in this talk, all the talks. So it was a good response, and there is a interaction session for each session was there after the talk. So that also went well. So this is the summary.
Okay, thanks, Samresh. Now, can I request to Professor Manan Suri, who is the convener of Emerging Logic and Memories Symposium?
Hello. Yeah, am I
Yes.
audible, sir?
Yeah, Manan. Yes, go through.
Okay. So first of all, I would like to congratulate Professor Khare, Professor Singh, and all the organizers for also giving us this opportunity and having a wonderful conference. It was indeed back to back, and the symposia that we did was more on the let's say emerging logic, memories, and neuromorphic devices. So I just put together a summary slide, if I can share that. So is my screen visible?
Yes.
Yeah. So so this symposia, along with myself, couple of other faculty colleagues helped me in getting together this symposia. Professor Nihar from IIT Gandhinagar and Professor Shaibal from IIT Indore. So the highlight was that we had good international presence of very distinguished speakers, and I just tried to put it on a map over here. You can see that we had people from all over the world speaking in a single symposia. So we had 14 invited speakers from 11 countries, representing at least 10 universities, and we also had representation from industry as well as microelectronics startups and also research institutes. So overall, it was a very well balanced and well attended symposia. Now the key takeaways I just summarized on this slide were the emerging developments in the field of novel devices for computing, for neuromorphic applications, as well as for AI. And something very interesting to see was that even in the Indian context, this research is really picking up. So it's also growing domestically in the right direction and as expected. And some interesting things to see were also flexible devices or devices on flexible substrates. So that is in a nutshell. And once again, I would like to thank all the invited speakers from all over the globe who made this symposia a success. And also, I would like to specifically thank the student volunteers who worked tirelessly and who were like always on toes, trying to troubleshoot any last minute situation in a more challenging back to back presentation system. So yeah, that's the summary in a nutshell. So thank you, Professor Kharif.
Thanks, Manan. Now I request Professor Madhusudan Singh, who is the convener of the Flexible Electronic and Organic Semiconductors.
Hi, can you hear me?
Yes, Madhusudan.
Okay, so I would like to first of all thank the organizing committee for letting us organize this symposium as a part of ICEE. Also the organizing committee for the symposium, which included Professor Sundar Iyer from IIT Kanpur, Professor Subhadas Gupta from IISc, Professor Guo from Michigan, Professor Smith from Sheffield, and Professor Dahiya from Glasgow, who offered a lot of very useful advice in the initial organization and also the final conduct of the poster session, as well as many other activities. In some cases, they themselves volunteered for an invited talk. In others, they suggested others who accepted our invitations. We had a total of 8 scheduled invited lectures. Unfortunately, 2 of the speakers withdrew because of health reasons, and they are very keen to participate in the next run of the symposium,
at the future ICEE if it happens. We had 7 oral presentations, of which one person did not present because of technical difficulties. There were some significant technical difficulties on the second evening, but we were able to resolve them in time, and the last 2 lectures went off fairly well. We had 13 posters which were judged, and out of which we chose one best poster. We found a lot of cross-cutting interest from other areas, had a significant number of people trying to do either neuromorphic memory RAM-based devices or magnetic devices, magnetic sensors in one case. And then there were the more usual polymer and organic based talks, both in the oral presentation as well as among the invited speakers. Somewhat surprisingly, there was not much input from the printed side. There were only a couple of talks on printed electronics, but that might be an attestation to the fact that printed electronics is more or less well accepted part of this business, and hence may not attract a lot of cutting edge research work, at least at the university level. But overall, it went on fairly well, and we hope to have a good symposium next time, perhaps a more expanded one than was possible this time because of 2 main reasons. One was that the timing of the conference was clashing with 2 major events. One is Thanksgiving, so a lot of our invited speakers did not take up the opportunity. And the other was MRS, which is going on right now. So a lot of our speakers are involved with that. But in future, I hope that we will be able to have a more expanded presence in ICEE. Thank you.
Thanks, Masudan. Now I request Dr. Pushparaj, who is convener of MEMS.
Yeah. Okay, can you hear me, sir?
Yes, yes.
Okay, so I would like to summarize the MEMS symposia. So actually, first I would like to thank you, sir, for believing me that I can run this symposia. So, and because we know that the MEMS people in India are not many, so I was kind of curious, like how many people will be really coming to the conference. But overall, I think a lot of people has shown interest, and the work they also presented was quite good, to my surprise actually. First, I would like to thank Professor Bhaskar and Professor Dhiman from IIT Delhi for helping me organizing this symposia well, and Professor Pradeep Dikshit from IIT Bombay and Professor Prempal from IIT Hyderabad. So they really helped me to find out the invited speakers throughout the globe, and many of them from Europe and US. Actually, they personally came, and today only, as Professor Rajendra Singh said, that many of them are giving talks in the night also. So one of our speaker was speaking, and the time was 2 p.m. there, 2 a.m. actually there in Miami. So when I realized that, then I felt bad actually, because I could have arranged his talk in a better time, but he also did not actually ask me to change. So that's how I would like to thank them, to really accept our request without asking for a change. Okay, and then my students Vaibhav, Sushil, and Dharya also helped me. So when our symposia just got started, even very first talk there was a technical issue. So I was very nervous actually, and then we realized that the person who was giving an invited talk was did login from the 2 windows actually. So we asked them to ask him to please, and then after that there was no technical issue throughout the 2 days actually running. So overall, we received more than 30 papers actually, and out of that we selected 8 for oral and 20 for the posters. And many people presented very interesting ideas, mainly on, we know that these MEMS devices are having issues with the high voltage operations, right? So many papers they were presented on how to make them low voltage operations and to compete with the CMOS counterparts. And then we know that many of the sensors are also, when we go for very small gaps, then stress issues are also there. So some of the speakers, they also addressed quite well that how to control these stress issues or something. And then topics like energy harvesting, biomedical sensors, and they were also covered. And many of the invited speakers, they talked about the microfluidics. So that was like also a big surprise, because many of them, they were working in the hardcore MEMS before, and then they moved to microfluidic side. So that was a quite interesting part actually, we felt. And then in the future kind of direction, so many people, they presented their CMOS MEMS packaging technologies, which is very important to really realize the sensing, a sensors actually for the real application. And then many packaging talks was there. So I think the audience got a very good kind of conclusions, how packaging is so important to think even at the stage when you decide your sensors actually. So, and many biomedical applications were also covered in the talks. So I would like to really thank my invited speakers for their great knowledge sharing. And in the last day, there was a presentation from a speaker from Singapore, and they are starting a fab actually service that is including the universities, and they call this model as lab in fab. So this lab in fab model is involving ST Microelectronics and A Star Singapore, and they want to collaborate with the students and university professors, and they to help them realize their concepts. So overall, it was very useful actually, and many people attended this symposium. So that's the summary, and it went very well. Even the not many people are working in this area, but the turnout was quite great actually. So this is my summary.
Thanks, Pushparaj. Now I request Professor Ankur Gupta, who was the convener of device modeling and simulation. Ankur.
Hello, sir. Am I audible?
Yes, yes.
Hello, sir. Thank you very much for giving me this opportunity. And we had this talk, device simulation and modeling, and the experience was very good. We had 10 talks, and 4 of them were from abroad. And as everybody noticed, they all were present online for giving talk and question answer session. And the feedback from the speaker side was also very, very good. I received some of the feedbacks from the invited speakers. They were kind of very happy to give the talk in the session. And especially there is no technical difficulty. The session went very smooth thanks to the student volunteers who kind of managed it very well. All the links and everything they gave in advance. Another very good thing I noticed, the coverage in the track was the topics, the coverage was very good, right from the devices, circuits, simulations, like modeling, even analog, digital, and even we saw the invited talk on the hardware encryption, like using the hardware for the encryption. So the coverage was quite good. Not list out everything, but especially I would like to mention, just like talk by Professor Mayank was very informative. It was like very in-depth simulations of these GAN HAMs, and which led to India's first GAN-based power transistor enhancement mode. Another talk which was really very good was by Professor Mariam Shojai Bagini. She showed some filter design aspects, and she fabricated the devices right here in our SCL facility, and they turned out to be very good, very comparable to the devices we fabricate outside. Professor Atmesh Srivastav also provided a very good talk. He's from Northeastern University, USA, and it was on the chip design of ultra low power sensors. How the implantable chips can have a kind of long battery life, even more outlive the human life. So they are so energy efficient. So that was quite wonderful talk. So overall, we got a very good response from the speakers and attendees. I'm very thankful to everyone to giving me this opportunity. Thank you from my side. So this is the summary we have.
Thanks, Ankur. Now I request Anuj Dhawan to present a summary of the photonics and plasmatic. In fact, Professor Joby and Anuj were quite involved, so maybe they can talk a bit about their symposia.
No, I do not see Anuj here.
Acha, maybe you can tell that. Yeah. Okay.
Okay, hello. Thank you, Professor Khare. And also, I should thank organizers, including definitely Professor Khare, Professor Rajendra Singh, for this wonderful organization of this conference. Everything went perfectly smooth. And in the photonics session, we had 25 invited talks, out of which 9 were from India, all others from across the world. And as Professor Rajendra Singh mentioned, that some of them were giving talks early morning, some were in the late night. Everything went perfectly well. And one of the speaker, Professor Magnuson from US, initially he was mentioning that it is too early for me. How would I be able to wake up early to give the talk online? And he was initially asking me whether I could give the recording, but finally he decided for the conference benefit I should come online. So he came online right on time, early morning, and everything went perfectly fine. And we had 9 contributed papers presented by various students and postdocs. One had a little technical problem, but all others went very well. And also the takeaway from the photonics conference I could notice was the real integration between electronic circuits and the future photonics. And even now, it was a very apt part of the electronics conference. One could notice if you come into the photonics session that now very soon you will be able to exactly similar way you fabricate your electronic circuits, you will have a foundry making photonic circuits and nanophotonic devices. So that will be the future. It can be very well noticed from the overall photonics presentations we had during the session. So overall, wonderful experience having the online conference. And one, I could notice that the online conference sometimes are better than your offline conference to grasp the topic. Because otherwise, unless you are very well focused, you may be distracted by neighboring people looking around. And here you will be learning each and every sentence which are on the screen. You are very well focused. I enjoyed really attending each and every talk by the invited speakers. So thanking everybody for giving this opportunity. Thank you.
Okay, thanks, Joby. Now I request Professor Prashant Mishra. He was the convener of the symposia on biosensor and bioelectronics. Prashant?
Yeah, hello. Very good evening
Okay.
to all of you. And we had this symposium on biosensor and bioelectronics, where I had eight Indian speakers and 5 foreign speakers. And total there were 13 invited talk and 3 oral presentations. And the presentation some of the very new area has been covered. So initially, we have divided this into 4 sessions, and in first we had IIT Bombay, Professor Deepankar Bandyopadhyay, IIT Guwahati, and Professor Malhotra from DTU. And in these talks, they have tried to summarize biosensors. For example, inexpensive biosensor using paper and plastic. Then about the healthcare, how we can go from a lab scale to the production scale, and how we can go to the market. And then about the direction using different types of emerging nanomaterials for the biosensor application. We had 2 oral talk in this session, and one was on transition metal based cancer detection, and another was polyaniline based DNA sensing. Afternoon session, it was about the single molecule sensing, where nanopore was discussed, how we can use nanopore for biosensing. Then second talk was on U-bent fiber optic-based sensor. So it was quite interesting. So we had covered various area, and in the last talk of the session was about the using nano rattles for sensing. And in the evening, we had a recorded lecture by Professor Stewart from University of Canada. He has given photonics, how photonics can be used in biosensing. Then we had 27th, means next day, we had the three speakers, invited speakers in the morning, and one of them gave about the non-invasive cellular characterization using impedimetric sensing. Then second was on holographic. So these are quite varied area where many people, they are not aware of. For example, holographic microscopy based biosensing. Then we had another talk by Professor Sandhu, who is from UEC Tokyo, Japan. He gave talk on medical diagnostics using smartphone based optical tracking. Afternoon, we had application on theranostics. We had another talk from University of Twente where commercial biosensing was discussed during pandemic. And the last talk was on biosensor design for low resource settings. So this way we had talk on biosensor from various area, and a lot of interest was generated in among the speakers, among the participants, and I think it was a very interesting experience having online presentation where we could attract top leaders in the field, both in India as well as abroad. Of course, something which we can enjoy in the in offline presentation, that was different, but it was a really very different experience. So I thank the organizer for giving me opportunity to act as a convener of this session. Thank you very much.
Thank you, Prashant. Now I request Professor Ananjan to talk the experience of the symposia on RF, microwave, and terahertz devices.
Yes. First of all, Neeraj, it's great to see that the conference went off so smoothly. It's a new thing for all of us, I guess. And regarding our RF and terahertz, it was a relatively small session, of course. It just everything went over today. And yesterday, of course, there was on the first day, there was a very nice tutorial. Tutorial went off very well. And I think all the people enjoyed it also. I think Sunil, are you there?
Yes,
Sunil actually.
Sunil will also add after you. Yeah.
Yeah, I think Sunil can discuss all the. There was a few minor technical glitches, but fortunately, finally everything worked out. So Sunil, I think he has a better grasp of all the finer points. So Sunil, can you give the details of the papers and talks?
Yeah, sure. Yeah, so we had actually 7 invited talks in both the RF and the terahertz areas. So we had one foreign speaker, right? More than that? Yeah, we had only one foreign speaker who spoke on the terahertz spectroscopy of some polymeric material. Other than him, we had 3 speakers who spoke on RF and 4 speakers who spoke on terahertz spectroscopy. And of course, the tutorial session also went very well. Really, all the participants who had registered, they were there. Even the poster session also was, I think it also went very well. Meaning we had about 12 to 13 posters, and all the participants were there present to present their poster. So I kind of I can see from the speakers they kind of were very positive in the sense that they were quite appreciative of our efforts, that in this time of COVID we could organize this and manage to have these talks even though they were in the online mode. But I think it was an effort which was well taken by the speakers also, and all those 7 speakers were there, virtually present to deliver their talks. So this was really, I think, in fact, all those talks were attended quite well attended by I think most of them were the students in the audience. So that is what I think. We have a good feeling about this session. It went really well. Yeah. So this is what. Have I missed anything, Professor Ananjan? I think.
Yeah, so everything else worked very well. Minor glitches were there. We the poster session, we sort of ran out of time by about 5 minutes, so we had to do a little bit of adjustment. And the technical talks, we noticed several times the audio was creating problems. So I think there is some technological issue there, but it was never serious enough to really disrupt the proceedings in a manner that we need to be concerned about. So that was the only thing. Yeah.
Probably, can I add one thing which just occurred? I got reminded of one thing. So we had actually, out of the posters that we had received, we had selected few of them for oral presentation. So two could attend, and one, because of some confusion or some misunderstanding or something, the presenter was not available. So probably this fact we will have to look at somehow how to basically convey this, because the presenter thought that he has already given a talk in the some other session, so therefore the email which he was receiving, or he did not look into the details of those emails. He thought that it is related to the talk that he has to deliver in the other session. So somehow this miscommunication or confusion, because of that this oral presentation did not really did not happen. So
Okay.
yeah, other than that, all the
right.
talks were there. Yeah, they went in time. Yes.
Okay, thanks, Sunit. Thanks, Professor Ananjan. So now I request Rajen Singh, who also happens to be the convener of a symposium on wide band gap semiconductors. So maybe Rajendra, you can summarize about your symposia.
Yeah, thank you, Professor Khare. So this wide band gap semiconductors, devices and applications symposium, it attracted, I think, a lot of attention, and as is evident from the numbers also. So there were the maximum number of posters were there in this session, 43 posters, and there were invited talks, 21 invited talks, and 7 oral presentations. And apart from one oral presentation, which was given by Professor Shravanti Chaudhary from Stanford, it was a pre-recorded because actually it was deep in the night there, so she was not so comfortable due to some reasons. But otherwise, all the presentations were made like in online presence. So that showed actually how much like eager and excited the invited speakers were to give the talks in person. So this the key points I would like to highlight that this symposium covered everything in the invited talks. We can see starting from the materials. In the materials, we had gallium nitride, silicon carbide, which are actually nowadays like the very, very important wide band gap semiconductors for optoelectronic devices, for high power electronics, for RF electronics, and number of other applications. And gallium oxide, which is actually the upcoming material for high power electronic devices. And then even there was one talk from Stanford University in diamond electronics also. And in growth, we could cover like starting from MOCVD, MD, which are actually the important growth techniques, CVD also, and crystal growth was also discussed. And in the devices, starting from high electron mobility transistors, high power diodes, UV LEDs, UV photodetectors, and the MESFETs based on gallium oxide, and the reliability of gallium nitride devices. So I think the whole spectrum, whatever, like there were 21 talks only, but the whole spectrum of wide band gap semiconductors at least could be touched, although it's very difficult to cover all the topics in detail in this area of research, which is quite wide spanning. And the applications were shown that ranging from RF electronics, high power electronics, UV LEDs for sterilization, and their potential applications in 5G, electric vehicles, and so many like upcoming applications of these devices based on wide bandgap semiconductors were discussed. So I just a few highlights that it started with the talk by Dr. Seema Vinayak, the director SSPL, and she talked about wide bandgap semiconductor material growth and device processing technology, what is happening at SSPL, because at present in India, that is the biggest lab which is working on dedicatedly on gallium nitride related research activities. And Professor Mattioli from EPFL Switzerland talked about the limits of gallium nitride electronics, and Professor Tianli Wu from NCTU Taiwan talked about the reliability challenges in gallium nitride devices, power devices, and I think the next was Professor Raghavan from Bangalore, Vasu Raghavan. He talked about the growth microstructure and device performance correlations, which is very, very important now actually. We can make the material, but how its microstructure is related to the ultimate device performance. So it's going to be a very, I think, important topic in the coming future. And Professor Haiding Sun, also from China, he gave a talk about ultraviolet optoelectronics. Professor Lee from COST also talked about UV lasers, LEDs, photodetectors. And then Professor Anant Agarwal talked about the silicon carbide electronics. And then there was Dr. Harshad Mehta, who is establishing a silicon carbide fab. So that is a very good news actually for our wide bandgap semiconductor community in India, that there is a silicon carbide fab going to come up in Halol near Vadodara in the coming years. And the silicon carbide, the first silicon carbide epitaxy for 6-inch wafers has already been ordered by this company. So that is a very positive news. And Professor Higashi Baki, who is a pioneer in gallium oxide, so he also gave a talk today. And Professor Viman from Norway, talking about a very novel kind of actually Algan nanowire based UVC LEDs. And he also has a company, Cryo Nano, which is now working towards the commercialization of these devices. So I think, and there were other talks also on UV photodetectors, crystal growth by Arnab Bhattacharya, and UV photodetectors today by Dr. Mukesh Kumar. So I think it was very, very, like the level of the talks was really very high. And the kind of interest it has generated is really, like, let us say, praiseworthy. I hope the students and those who have attended this talk, all these talks, might have gained a lot after attending these talks. I'm also thankful to all these invited speakers and also to all the session chairs of this conference, and all the oral and poster presenters. And finally, I would like to acknowledge the help and the coordination that was done by Dr. Manikant Babu, my recent postdoc, and my PhD student Hardyan, who have devoted actually a lot of time in organizing this 3-day. It was running all the 3 days. So they really took care of organizing all these aspects. I hope everything ran quite well in this symposia. So with that, I would like to conclude for this symposia. Thank you, Professor Kare.
Thanks, Rajen. Now I request Professor Mudli to talk about the symposia on spintronic devices, memory, and computing.
Hello, Professor Khale. Thank you very much for this opportunity to act as a convener for this symposium on spintronics. It was a really very good symposium, and we had about 21 invited speakers, out of which 8 were Indian and the rest were all from foreign speakers. And they are really the experts in the different areas of spintronics. So we could actually invite 2 persons, namely Hansu Yang, who was a IEEE distinguished lecturer, IEEE distinguished lecturer in the IEEE Magnetic Society of 2019, and Matthias Clark, who is the present distinguished lecturer in the IEEE Magnetic Society. So both of were they presented, and they gave really high quality talks. And also we had really experts on spin orbit torque, Johan Ackermann and Pedro Gambrella from ETH Zurich. They talked about STT-MRAM, and spin Hall-based neuromorphic computing. So we also had very good high quality talks from India, from Anjan Varman, Anil Kumar from Icee Bangalore gave very interesting new results, which are really of international standard. So overall, I think it rained for entire 3 days. In fact, whoever I invited, they all agreed. So I especially took some effort to arrange the program in a manner that it is not, the timing is not inconvenient. The worst timing was probably today morning. There was a talk which the speaker had to give at 7:30 in the European time, but he had no issue. So all the lectures were live. There was no recorded lecture, and overall it went well. Only there was some technical issue in the first day. The WebEx link didn't work for about 20 minutes, and so that was a little bit inconvenient for the first speaker and the chair. But then once it started, then there was no issue, so things went well. In fact, we had so much of discussions that most of the sessions went over time a little bit. So not leaving any time for lunch. The past day, I realized that I could not take my lunch. So second and third day, I bring my lunch so that this doesn't happen. So it was very good, and a lot. In fact, I received a lot of feedback from the invited speaker that they really like the way it was organized, and so we had what the contributed. We had 6 contributed talks. Most of the PhD students, and they were also very good. And we had about 20 poster presentations. So we also had to extend the poster session to evening tomorrow. I mean, yesterday we had to extend it to 7:30 because it was not possible to complete by 5 o'clock. But we evaluated all of them, and it was a very good experience, I would say. I think I said everything. It's yeah, more or less.
Okay. Okay, thanks, Mudli. Yeah, it was good to hear from all the conveners that everything went go. I was also observing this.
Hello.
Yes.
This is Samresh. So one other convener 2D materials, Professor Ankur Goswami also here. If I miss something,
Ankur, yeah, you can also share your experience. Ankur. Vamsi also, yeah. Yeah, Vamsi, I'm not seeing. Ankur, are you there? Ankur Goswami? Name is there. Yeah, Vamsi. Maybe Professor Vamsi, you can tell about this photovoltaic symposium. Yes.
Yes, sir. Thank you, sir. Good evening to everyone. So under this session, we actually, this is energy harvesting and photovoltaics. We had 4 invited talks and 11 contributory talks and 35 posters under this. Under the energy harvesting, we really had a good talk from Korea, from Professor Jong. Talking about the vibrational energy and water droplets and how to generate basically some small amount of mechanical energy to electrical. That's people are looking for small device applications, and and also the polarization state roll up this in the composite system can do the triboelectric nano generators. So that is also one contributory talk from our ITD side. And in the photovoltaics, we try to manage because so many abstracts we received, particularly the area perovskite is a very large area. Every day, the 500 papers are appearing. So try to filter out that where it is particularly. I try to see the committee that where is the stability issues in this talk we invited and try to understand. So the talks were concluded that it is the interface which is important. Of course, everyone knows that in electronic devices it is the interface, not the bulk. which decides the properties. That was the conclusion, and we try to manage the silicon also, which is an industrial, standard solar cell. So what are the issues present? And there is a talk on how to translate into the batch process from the lab to the batch. So we had that one. That helped us, and we also have some PhD related films related to talks. I would like to summarize that we had some understanding and able to only get from my Indian side who are doing it basically on photovoltaics, and some few talks from abroad. But as sir mentioned that it really helped Professor Joby Joseph. But what I learned is because lack of this, lunch session and tea breaks, it helped to basically balance, timing. Otherwise, maybe if the lunch session should have been there, it is difficult. So whatever the gap periods really helped. So maybe the message is like in future in Indian conferences, we should avoid the lunch, big lunches, so that even after lunch, we cannot concentrate on the talks like the way Western people are doing it, just providing small snacks, teas that help you to concentrate on the talks. Thank you, sir. This is from my side.
Thanks, Vamsi. Yeah. I think Professor Ankur Goswami, I'm not seeing him here. He has also contributed in organizing this two-dimensional symposia. Anuj is also not there. Okay, Samresh, can you see the...
Sir.
Okay. All right, maybe you can call him. So, all right.
Ankur Goswami is here.
Ankur Goswami is there. Ankur?
Yes, sir.
Professor, yeah, just maybe we want to hear from you also about this two-dimensional symposia thing. That what was your experience, because you are also very deeply involved in organizing that.
Yeah, first of all,
yeah.
am I audible?
Yes, you are.
Yeah. First of all, it is thanks to you and all the whole organizing committee for giving us this opportunity to conduct this conference, this particular symposia. And overall, it turns out very good, and I believe it is a great success as a whole conference. And for the symposia also, we have, I think Shamaris has summarized already, almost 17 talks we had, and across the world, almost we have 8 or 9 lectures, and that was also a lot of late night and early morning, and people have contributed very nicely. And from thermoelectric to energy harvesting to this carbon sequestrations, catalysis, gas sensing, different perspective of using 2D materials have been shown. And almost 34 posters were there. The posters were also presented very nicely. So different perspective also came up with that. And RWTH Aken, one faculty was there. So he also talked about growth of these 2D materials in a large scale. So that was also very fascinating. So overall, it was a very good conference and very good way of organization, I would say. I think Professor Joby also mentioned about that people are concentrating more in this kind of conference rather than your offline conferences where people get distracted. But although, kind of in-person interactions were missing, that is obviously cannot be, there is no replacement for that. We believe that next years onwards we can meet. So that is overall my views about the conference. So over to you, Professor Khare.
Thanks, Ankur.
Yeah.
So Professor Vasu is there. Maybe I would like to have his remarks before I proceed further, because he was the chairman of the last conference. So he can share his experience of this one.
Oh, thank you, Neeraj. And what can I say? Congratulations to all of you. It is a fantastic job, well done under trying circumstances, right? It's never easy to run a conference, whether it's online or offline. It's not something that you do on a daily basis. It comes, once in 2 years or 4 years, and then you have to put everything aside and you have to run a conference. It's stressful. And in spite of that, I think, like I said, you guys have done a fantastic job, all of you. So congratulations. I realize that now Icee and Navkant alluded to it at the beginning. It's kind of moved into a steady state mode. So maybe from the next conference onwards, like you have these international conferences where the structure is set up, same hotel, same format, and so on. But the academic folks only come in and get the technical part rolling. Maybe it's time to move Icee on that kind of a format. So fantastic achievement. Congratulations to all of you. And if Professor Ram Gopal Rao were here, I would have recommended that he, put you on a cruise. It's that cruises are not available now. So maybe he should get a cruise for all of you. And as we've always said, it's a great platform. Yeah. It's a great platform for Indian students, and given that it's online and attending becomes cheaper, it can become an even more widespread platform. So when we did Icee back in 2 years ago, we thought, well, 600, maybe we've kind of hit the limit, but you said today 1400. So you set the bar high for Mayank and Sushoban going ahead. Maybe we can learn from you as to what are the pros and cons of this mode. I don't think it's going to go away. Actually, even back when we were going to organize Icee and a couple of speakers at the last minute said they couldn't make it, we thought, well, why don't we have it online? But it's amazing. I mean, even then it was not set up. In just 2 years, the world has changed dramatically. Now the whole conference is online and we are forced to do that. So maybe future it will be hybrid. Like Ankur pointed out, the interaction part is something that can never be replaced. Maybe it will happen through holograms, who knows, in 2 years from now. But with that, I think the bar has been set for Mayank, Sushoban, and I'm guessing Digvijay for the next one in Bangalore. So with that, congratulations once again to all of you. Fantastic job.
Okay, thanks. So now I just move to another very important thing related with this poster presentation. You see, when we were discussing how to make a poster presentation, there was quite a bit of things we have to do now. Maybe we can share our experience. It was very interesting. In the beginning, when we started thinking what to do with the posters, then we thought that let's take the poster and put it like a PDF format somewhere in the corner. But then we started thinking it will be very disappointing for the poster presenter because they will not get any audience, they will not get any questions. I mean, they will not feel good at all. Then we started experimenting on it, and then what happens that we come out to be the e-poster kind of concept where every posters can be put there, so anybody at any time of the conference can go and just browse it and can see it. But overall to this, what we decided that we'll make a poster presentation in a particular hall in which all the participant of that particular symposia can go there, and they can be called one by one, and then for 3 minutes or 4 minutes they can talk about their work and somebody can ask question. And it worked out very well, and very well in that sense. Sometimes it overshooted to time, so we have to arrange extra time for them. And it was very interesting to observe that I think first day the conference, the evening lecture ended by 7 p.m. But after 7 p.m. we had again a poster session kind of presentation, and it continued up to 9 p.m. So that was a very interesting experience. I mean, it was very interesting to observe the enthusiasm of the participants, that they were so eager to talk about their work and all that kind of thing. So that was another very interesting experience we have in this one. So now I go to the poster awards, because all the symposia conveners also did a lot of hard work to evaluate these posters, and many reviewers were involved. So maybe Rajendra, you can start telling about the result. We have given 16 poster awards on different symposia. So altogether, maybe I will share the my PPT,
Yeah,
and
you
then
can.
you can read the names.
You can display.
Yeah, I will display so that everybody can see.
Have a look into it.
The winners, yeah.
So
The
all
first
these
symposia is a wide band gap. So 3
Yeah.
awards were given. Maybe you can read the name.
So awards were given. So I will read symposium wise. Okay. So in wide band gap symposium, 3 poster awards. So first one is poster number 11, which was presented by Mr. Kapil Narang from SSPL Delhi, and the title of the poster is Growth of Device Quality Thin GaN Based Algan GaN Hemp Structure on Silicon Carbide. Then the next one is, okay, I will, okay. So the next one is poster number 26. It's by Ms. Smridhi Raut from MSIT Delhi. Investigation of single event transients on buffer free GaN on silicon carbide HEMT. And the next one is poster 40 by Mr. Surya Upadhyay from ISC Bangalore, who presented about 500 volt Algan GaN HEMT on ultra low gate leakage. So these are the 3 poster awards in wide band gap symposium. So the next one is the 2D materials and devices. So in this 2D materials, we gave two. So first one is poster number 64, Mr. Venkata Rao Sila Menani from BITS Pilani campus, who presented about WS2 quantum dot N decorated on tin sulfide P as localized heterojunctions, highly responsive flexible broadband photodetector. And then the second one was poster number 65, Ms. Abhilasha Choksi from SSPL Delhi. She presented on monolayer graphene based terahertz modulator on silicon dioxide substrate with large active area. So now the another symposium, flexible electronics and organic semiconductors, one poster award has been given. This is poster number 84 by Mr. Nitish M. Nair from IIT Madras. Simulation assisted flexibility improvement studies for flexible transparent printed touch sensors. In the biosensors and bioelectronics, one best poster award, poster number 103 by Mr. B. Chakrabarti from Indian Institute of Engineering Science and Technology, Shivpur, West Bengal. The presenter talked about graphene zinc oxide nanorod based electrochemical APTA sensor for cancer biomarker detection. In the NEMS and microfluidics symposium, one poster award.
MEMS will come the last. Is the first I've written photovoltaics. Yeah.
Okay, photovoltaics. So photovoltaics and energy harvesting, 2 poster awards. One is poster number 133 by Miss Nisika from IIT Ropar. She presented about energy band alignment and nanoscale probing of CZTS on TiO2 heterojunction in casterite solar cells. And another one is poster number 155 by Dr. Aditya N. Rai Chaudhary from IIT Bombay on the linearity and parabolicity of the PI and dark IV, the effect of series resistance. Then is photonics and plasmonics, one best poster award, poster number 169 by Mr. Jindal Tapar from IIT Hyderabad. Exceptional scattering in PT symmetric gallium indium phosphide nano antenna metasurface. In the spintonic devices for memory and computing, one best poster award, poster number 195 by Mr. Mohan Johan Rex. He is from Kyushu Institute of Technology in Japan. So thickness dependent interfacial spin orbit torques in platinum on nickel ferrite or nickel iron bilayers. This is an international contributor. Then is device modeling and simulation, 2 best poster awards. Poster number 255, Monica Sharma from University of Delhi. Effect of interface charges on in-GaN and in-gas-based doping-less TFET and its circuit analysis. And another one, poster number 229 by Marsha M. Parmar from IIT Delhi. Fabrication and characterization of indium arsenide on aluminium antimonide-based magnetic Hall sensors. And in the RF, microwave and terahertz devices, one best poster award is poster number 232, Mr. Sandeep Kumar, again from IIT Delhi, metallic spintronic ultra-fast terahertz emitters, tunability through bismuth and bi and tri-layers for intense broadband terahertz pulses. Emerging logic, memories, and neuromorphic devices. One poster award goes to poster number 253 by Mr. Anuj Kumar from IIT Roorkee. Nanofilamentary resistive switching and electrode engineering in MOS2 based memory devices. And I think there is one last one, which is this MEMS. Yeah.
MEMS
so
and
should
NEMS,
yeah, MEMS
Yeah.
and NEMS. So this was one poster award. So this goes to poster number 131. Sushil Kumar from IIT Delhi, fabrication of freestanding metallic MEMS actuator for minimal stress-induced air gap variation. So I would like to congratulate all the awardees of the Best Poster Award, and they have really displayed a very good poster and explained it also very well. But I also would like to mention here that many other posters were also of very good quality, and hopefully in the coming conferences, the other students will also learn from here, and they will make their presentations even better. So thank you, Professor Kare. Over to you.
Okay. Thanks, Rajendra. So congratulations to all the poster awardee. So we will send them the certificate and the award, of course, through post. If it would have been a offline conference, perhaps we could have seen you and all that, but that's the way it is. Okay, so before I proceed further, I want to invite to Professor Naukan. But before that, I just want to finish a very important task of giving thanks, because my list is very long, because this has been a very big conference. Many people have contributed. So I will just go through quick, and just want to acknowledge the thanks and want to give thanks to them, because without their all support, etc., such a big thing could not have happened. So first and foremost, I would like to thanks to all invited speakers of different symposia, keynote speaker, plenary speakers, and evening talk speakers for agreeing to give talk in this conference. It has been a very wonderful experience of listening to them, and all these speakers were very well in time and all that kind of thing. So I'm very much thankful to them. And you see, we started with the keynote address of Stuart Parkin, and today we have a plenary talk of Professor Ramesh, and in between we have a talk of Dr. Chang and Professor Subodh, and also the evening talk of Professor Thomas and Professor Corcliffe. All were very kind of illuminating, coverage a very wide range and all that. And we have put these talk on the YouTube also, the ITD YouTube, and they have been observed. People have been observing. For example, in the keynote address, today I noticed that even after the seminar it all ended, we have more than 900. Okay, so apart, the next thing that I would like to thank to all chairmen of different symposia who played a very important role of running the symposia in time, so that we can have everything well in time. So we are very thankful to this, all the chairmen of the different symposia invited talks and keynote speakers, plenary talks and evening talks. And then finally, I'm very much thankful to all the delegates who accepted, who submitted their papers and participated in oral and poster presentation. And apart from that, we have many delegates who were just a kind of participants because they just wanted to listen all the talks and all that. And in that category also, we have many more participants who got registered. And apart from that, to the invited speaker, we want to offer something. So we said that, okay, if you want to nominate your PhD students or postdoc who want to listen these talks, then you can nominate and we will make the registration free from them. And it was very surprising that many of the foreign speakers also nominated their PhD students and all that. And we have more than 300 kind of participants to which we made free so that they can participate in this symposium. Next one, in the organization of this conference, the steering committee members and the international advisory committee member had helped us a lot in the all kind of difficult problems and sorting it out. And especially I would like to mention the Professor Ram Gopal Rao, Director IT Delhi. Many times at a many crucial position we went to them, and out of all the way he tried to give us help in all the way so that the whole conference has come out to this shape. And then I'm also thankful to Professor Naukan Bhatt. And from the very beginning, he keep on discussing several issues and also giving his advice. And that was very, very helpful in this one. And Professor Vikram Kumar, we are very lucky to have him here. And we have been meeting and talking on phone. And with his experience, he also gave us very good advices on many occasions. And Professor Rudra Pratap also, I'm very much thankful for his advice. And Professor Ashok Kumar Ganguly, who is the Deputy Director Strategy and Planning, he also advised us on many things how to go ahead with this kind of symposia. And next one, I'm really thankful to other chairs and co-chair of this conference. Rajen Singh, he did a lot of things in making these technical programs, all this in a shape and running all these things. And Bhaskar did a wonderful job in organizing this tutorial session. And then from a distance thing, this Professor Mank, Sushobham and Digvijay, and they were very helpful in giving some of the suggestions on these online meetings. We have a couple of online meetings through them, and it was really very helpful for whatever suggestion they gave to us. And then you see we have this in these local, we have a big local organizing team, and these all members somewhere or other has contributed in organization of this conference. And then we have, as you have seen, that we have 11 symposia here, and every symposia has one convener, then they have their own team. Altogether are 55 people, and all of them have really contributed. I'm very much thankful to all of them just to giving their suggestion and efforts to make this program a really great success. So you see there are kind of all conveners and their teams are here who really contributed very significantly in making this program a great success. And then finally, you see that without the volunteers, we can't run. In the offline conference, we know that the student volunteers are very, very helpful. But here also in the offline mode also, we need their help. Without that, we cannot run. And you see, this was a big thing. And then just even for streaming the whole conference for 3 days, we have to organize a big team of 39 volunteers, including postdoc and PhD students. So for each symposia, we make a team of these PhD students and this postdoc who form a team for different symposia. You can see the name here. So, it will take a lot of time to read their name, but I really appreciate their efforts because some of the symposia were running for the whole 3 days. So they were working throughout from starting from 9 a.m. in the morning to sometimes 7:30 p.m. in the night and 8 p.m. in the night. And they were very cooperative and very helpful in sorting out the problem. They showed a great patience in listening all to this. And to this Dheeraj also, I'm very thankful because he coordinated all these team of almost like 55 students, and he was talking to everybody, making all, because they were put in on one frequency so that everything can run smoothly. And then finally, I'm also very much thankful to Hemujit because he is the one who really helped us in all at the final end, the establishing all the industry contacts, sending mails, and the sending them invoice so that we get money to run this conference. And of course, our faculty members help us to find out these sponsors so that we can get something so that we can run this conference. And then for these invited speakers, because you see, organizing this 151, 158 speakers, invited speakers, sending them mails, collecting their abstract and CV. If one is not sending, then sending him a reminder. It was a big task. And Dr. Kanan and Dr. Satyendra really was very helpful to us in writing so many emails to these invited speakers to collect all the abstract and CV. And then finally organizing this abstract book. which just before the conference, we put this in a PDF form on this our conference website. So if you see this has almost like 800 pages. So they arrange all these things well in time and put this on a kind of soft copy on this so that you can see this one. And then for the e-poster presentation, this was again a big task because we have almost like 260 posters and everybody has to send a mail because we decided that these poster presenters can also come online and make a presentation. Apart from that, they send their e-poster for this, putting this on e-poster chart. So the Dr. Prashant and Dr. Uday Dadwal has really helped in finishing this task. And Gagan also helped in sending mails to this oral presenter. And then writing to mails to this kind of participant was a very tough task, and Dr. Rohit did it very well, writing and sorting out if any problem any participants get. So he was really very, very particular, sorting out each and probably everybody should go very well satisfied. And for coordinating all the plenary and evening lectures, Dr. Mohammad Faraz has indeed helped us, and Dr. Hemojit helped us in the inauguration function and contacting all the persons who had to participate in the inauguration function and putting everything in place. And the Tamis was responsible for creating this all complimentary list so that we can include, because when we said yes for complimentary thing, everything has to be streamlined so that they can get registration number and all that. Earlier, it was possible that with one registration email, one can log, different people can log. But with the suggestion of Mank, we abolished this thing. And then it becomes a little bit difficult because then with email, one email, only one person can log. So we have to create many complementary kind of IDs and all that so that our guest can join this conference. Then our NRF staff, Kamlesh, Govind, Pradeep, and also helped in during the online streaming of the conference. And we received very good support from this Beams Conference and Management Private Limited, who was our manager kind of things for this online conference, and he really did a wonderful job in doing all these things. And then finally, I have a big thanks for this guy who's a Shiv in creating and maintaining the conference website. And he did a wonderful job in putting everything online as far as possible and working also from the home in the night and all that. So a lot of hard work he did to put everything in place. And finally, at the last but not the least, this guy was a wonderful guy, this Jagdish, in NRF, who did the wonderful job in helping me, not like anything, for the last 5 months. Even when the institute was not fully open, it was in the lockdown period, he was coming here in my office and helping me in all writing mails, answering to emails, arranging meetings and all that kind. He did a wonderful job. Without that, I really, it's not possible for me to go ahead with this one. So with this one, I request Professor Naukant to give his remark and to announce it, because now the time has come to hand over this conference to the another group. So maybe Professor Naukant, yeah.
Yeah, Professor Neeraj Khare, Rajendra Singh, and the whole team, Bhaskar Mitra, of course, and chairs of symposia, congratulations for putting together an excellent conference. I still remember in May or June, early March, I think it was scheduled for June, July, and several emails back and forth. Professor Ramgopal, Professor Neeraj, and we were wondering what we should do. And we decided to postpone, but then the question was whether in person or online, I remember the debate, and eventually we said, COVID will not end by November. Let's be, realistic and be on a safer side and go on an online mode. But saying that was easy because we had never conducted any technical conference in the country in online mode. Perhaps this is the first such conference, that is where, you were torch bearers, there was no precedence really. So you have done it in style. 500 registrants, amazing, you know. As Vasu said last year, 2 years before, previous conference when we conducted in 2018, we thought we had reached the all-time high, but you have really set a new record now, you know. This is really amazing. I think other conferences which will follow in the next few months will take this as an example to emulate, you know. The sessions were done extremely well, quality was excellent, and congratulations to again all of you. Of course, you have set a new bar, as Vasu has already said, for the next team. The next conference will be, I don't know whether it will be online or offline. 2 years down the line, hopefully the COVID will settle. We really want to do it in person in Bangalore. The team will be, led by Mayank Srivastav, who will be general chair, along with Sushobhan Avasti, who will be the technical program chair, Digbijoy, who will be tutorial chair, and I think they will put together a team going. We hope that it will be an in-person conference. If not, we will try and emulate what you did, an online conference in 2022. So that's the plan 2 years down the line. So let me, I think Mayank is on the call online right now. I'll hand it over back to Professor Neeraj, and he will take it from there. Professor Neeraj, over to you.
Okay, thanks, Nokant. Your suggestion were very helpful. We really appreciate that. Talking to you and getting all the things. So now I request Mayank to make some comment, and Sushobham and Digvijay followed.
Neeraj, this is Vasu here. Can I say one thing before we forget?
Yeah.
So I think the statistics from your conference will be invaluable. So if you have collated that, and if you have some kind of a report, that would be very helpful for the next conference.
Yeah, sure. We'll collect all the data and share with you and Mayank. So we'll do that. Yes.
Okay,
so
great.
I
Thanks.
think one point, if I may, as Vasu said, we should actually have some of these things on autopilot. For instance, there should be a conference website which should have archived all previous conferences. It shouldn't happen that you conduct a conference, all that information is lost. I think next conference committee should really think about this. So we should certainly archive all that you have done, and perhaps we have lost some of the previous conferences. This should not happen going forward, right? Yeah.
Okay, sure. I will make it sure to prepare a big detailed report of having all these things. Yeah.
Sure. Thanks a lot to everyone. Thanks, Professor Neeraj. Let me, a lot of things have been said, but let me once again congratulate Professor Neeraj, Professor Rajan Singh, Professor Mitra, and many other colleagues involved in planning and execution of ICEE 2020. I must say, despite the tough times, your team has executed the conference very well. The numbers are really fantastic, and a lot of learnings can be taken from this conference. We'll also use the learnings from our previous conference and learnings from all the failures and successes. This year was certainly a special year, because first time, as Professor Navakant also pointed out, that is the first time we tested running a conference in online mode, and that too from India. Online conference running all across the world, but I think this is the first time we did a conference of this scale from India in an online mode. Okay, we have limited data, but I think we can certainly use this experience for future. Maybe possibly the future, even if the COVID is gone, possibly the future would be of hybrid nature, because now people have experience from in-person conferences, people have experience now with online conferences, and I think going forward people would like to have benefits of both the modes. So maybe we will have hybrid kind of conference in the future. So we'll think about future conferences along these lines. I mean, the other aspect of conference is having more and more people involved and ensuring that there are enough interactions among the peers. So we need to come up with more and more innovative ways in terms of organizing and hosting future conferences, because on one hand, people want in-person kind of conferences where you can interact with people, but on the other hand, people also want the comfort of online conferences, right? So I think having the both side experience which people have, the challenge which the organizers will have in future is just going to increase. And plus, you have put a high bar with these kind of numbers that we have to certainly account for. In fact, we were thinking about this and some thoughts came, for instance, now we have very fast internet technologies like virtual reality. Maybe we can also take benefit of some of these technologies, and, you can think of future conferences where, you are at your place, but using technologies like VR, you have a feeling like you are actually attending a conference at the venue. A lot has to be thought about with these new experiences. So on this note, I thank all of you once again. As far as the next ICEE is concerned, thanks for handing it over to us. We will certainly help growing ICEE. And soon we will get back with detailed plans, timelines for the next conference, keeping in mind the situation with COVID and whatever new learnings we have. Thank you. Shishobha, you want to add something?
I mean, nothing much to add, but thank you to the current team. Maybe to some extent apologies for all the emails, but I think in the end it was a fabulous effort. So well done.
Great. Digvijay?
Nothing much. Yeah, thank you again, Professor Neeraj and Professor Rajendra Singh and team. Yeah, we shall try our best, and we'll learn from this experience, and we'll also take your advice and inputs as we go ahead, so that we can arrange 2022 ICEE in a very nice way. Thank you.
Over to you, Professor Neeraj.
Okay, thank you very much. So now we have reached almost to the end. So thank you very much for participating in the concluding session. I was thinking it will run for 1 hour, but it has run for almost like 1 hour 40 minutes. So
let's give a hand.
Yeah. Okay. Thank you very much. So let's look forward to meeting in a hybrid mode at ICEE Bangalore 2022.
Yeah.
Okay, Mank. So now, okay, thank you all. So,
Okay.
yeah.
Okay. Bye.
Thanks. Bye. Bye.
Okay.
Bye.
Thank you. Thank you, Professor Navkant Bhatt. Thank you, Professor Vasu. Thank you, Mayank. Yeah. Thanks. Bye.
Bye. Bye.
जल्दी से करके पीछे से क्वेश्चन नहीं होते रहते